Hello, welcome to our video on a crash course in chemistry. We will cover a good deal of material throughout the series of videos, ranging from the very basics of chemistry to more involved and complex chemical equations and various chemical compounds. So we'll go ahead and we'll get started with Chapter 1, Chemistry in Our Lives. Chemistry is around us all the time, every single day, no matter if we realize it or not. And we'll go over some examples here of how chemistry is a part of our daily life. For example, forensic scientists will work in crime laboratories to help analyze body fluids. This is a key role of crime scene investigators, CSIs. Also to identify tissue samples, various bones, and so on. All that cannot be done without the work of chemistry. Also, you have chemists that will help to develop and further advance the development of pharmaceutical drugs to help fight and to manage and cure disease. Alright, first of all, let's get into the actual definitions of chemistry. What is chemistry? Chemistry is the study of the composition, the structure, various properties, and the reactions of matter. And this happens all around you every single day, and also inside you. Whether you're awake or asleep, there are thousands, literally thousands of chemical reactions that go on every single minute of every single day inside of you. An example that's given here in the picture is a glass of water with an antacid tablet being dropped into it. And this antacid tablet will undergo a chemical reaction when dropped into water. That's why you see these thousands of little tiny bubbles. That is evidence of a chemical reaction, how it's reacting with that water and being broken down and forming this little tiny bubbles here. Now on the last slide we mentioned the term matter. So what is matter? Matter is another term for any substance that takes up space, no matter how large, no matter how small. All things are made up of matter. The antacid tablets on the last picture are made up of matter. The water it was submerged in is made up of matter. The glass they are sitting in is made up of matter. The air around that glass is made up of matter. So everything that takes up any amount of space at all, no matter if it's really big or really small, is made up of matter. Alright, next we'll get into chemicals. Chemicals are a substance that have the same composition and properties wherever they're found. No matter if they're found in a chemistry lab or in a grocery store shelf or in your home, they'll have the same chemical traits and chemical properties no matter where they're found. And these are often substances that you use on a daily life. An example that's used here is toothpaste. Now, toothpaste is something that you should be using at least once a day, if not more. Most people don't think of it as anything other than toothpaste, but it's a mixture of various chemicals. And here are some of those that are found commonly in toothpaste. Alright, the first one, calcium carbonate. This is used as an abrasive to help remove the plaque from your teeth. Plaque tends to be very sticky and doesn't want to leave your tooth, so it takes something very abrasive to kind of scrape it off. That's what calcium carbonate does. Sorbitol, this will prevent loss of water in toothpaste. If you've ever left a cap off of a tube of toothpaste, or if you had some spill on the counter in your bathroom, when it dries out, it gets really, really hard. And sorbitol helps to prevent that from happening. Sodium lauryl sulfate helps to loosen the plaque, so it can be brushed away faster. Titanium dioxide makes toothpaste white and solid opaque color. Triclosan, this will inhibit bacteria that cause plaque and gum disease, so it helps to basically stop the growth of bacteria on your teeth and gums. Sodium fluorophosphate, this will prevent cavities from forming, so you can imagine a very key role or key component of toothpaste. Yeah, and the last one on here, methyl salicylate, will give toothpaste that minty wintergreen flavor. And this, of course, is probably not all the chemicals found in toothpaste. These are very, very common chemicals found in almost all brands of toothpaste. Alright, next we'll move on to what's called the scientific method. Now, the scientific method is a set of general principles that help to describe how a scientist thinks. Now, even though the title is scientific method, this is something that we all do on a daily basis, very everyday things. It's not just based in the scientific lab. You don't have to be wearing a lab coat to be doing this. We all do this every single day. After we go over the steps, I'll go over a very common example of how this would work. The first one is to make observations about nature and ask the questions about what you're observing. Second step will be to propose a hypothesis, which states a possible explanation of what you just observed. Step 3, several experiments may be done to test your hypothesis. And the last step, when results are analyzed, a conclusion is made to determine if your hypothesis was proven correct or incorrect. Now, all this sounds very dry, very scientific, but here's a very good example of a way we would all use this on a daily basis. Let's say you are in your living room and you can't find your cell phone. Well, that would be step 1, the observation. You can't find your cell phone. You are observing that what you're looking for isn't there. Next, you may think, well, maybe I left it in the bedroom. Well, that's your hypothesis. Maybe I left it in the car or the bedroom or the bathroom. That is your hypothesis. You are coming up with an explanation of why it's not with you at the moment. Then you go to the bedroom to look for the phone, or to your car, or to the bathroom. That's your experiment. You are going to a room to look for it. And then if you find it, then your hypothesis was proven true. If you don't find it, it's proven not true or incorrect. So something very simple, something very non-scientific sounding, is still a part of the scientific method. You make an observation, you're forming a hypothesis to explain that observation, you perform an experiment to prove or disprove your hypothesis, and then you analyze the data and come to a conclusion on whether or not you were right or wrong. All that is a scientific. All right, next we'll move on to some key math skills that you'll need for chemistry. Now, chemistry deals a lot with math, both with the reading of charts and graphs, formulating charts from raw data, being able to use basic arithmetic and algebraic skills to use chemical formulas. So this graph here represents the relationship between two variables. On this axis you have volume, measured in liters, and this axis temperature, measured in degrees Celsius. So being able to look at something like this without ever seeing it before, and being able to pull data from that is critically important to any chemistry class or any chemistry based material. Alright, next, another key skill that you will need when it comes to math and chemistry is identifying place values. For any number, you can identify the place value for any digit given in that number. Two examples listed below, one with a decimal point, one without. So the first one, 2,518. The reason why these numbers have the names that they do is because of their place value. So for this one, the 2 is in the thousands position. So that's why it's 2,000. The 5 is in the hundreds position. That's why it's 500. The 1 is in the tens place, and then the 8 is in the ones place. That's why you get the name 2,518 for this number in this order. So starting here with the smallest number, ones, tens, hundreds, thousands. Next would be 10,000s, 100,000, million, and so on. That's how numbers get their names. Now dealing with a more detailed number, a number with a decimal point, 6.407. Of course, the 6 will be in the ones position. And anything that's beyond or to the right of the decimal point will end with the letters TH. So this first digit, the 4, is in the 10th position. Not tens, but 10th. The one after that, instead of being, this will be the 10th, next will be the 100th, this will be the 1000th. And the numbers will continue being ordered in that same pattern. So next digit would be the 10,000th, then 100,000th, and so on. And this is very, very important to understand where these digits get their names from when it comes to rounding, when it comes to calculations, when it comes to scientific notation, which we'll talk about in a few minutes. But being able to identify a place value is very, very important to chemistry. Right, another key skill that's needed when it comes to chemistry, calculating percentages. Now, to determine a percentage for anything, not just something in chemistry or in a science class, but a percentage in general, you divide the parts by the whole. The word percent literally means of 100. per means of, and then cent, think of cents in a dollar. There are 100 cents in a dollar. So the word percentage means of 100. The example that's given here, let's say you have a total of 32 books here. And of those 32, there are 8 that are chemistry books. So to find a percentage of that, 8 chemistry books divided by the overall total, 32, and multiply that value by 100%. That will give you 25% of that total are chemistry books. So 8 divided by 32 gives you 0.25. That value multiplied by 100 gives you 25%. Alright, if the percentage of red balls is 5, that means there are 5 red balls for every 100. Because remember, the percentage means of 100. So these are all equivalent values here. So 5% of red balls would mean 5 out of 100. So being able to calculate percentage will come into play when we get to more advanced chemistry equations. Alright, next, interpreting graphs, something we mentioned a little bit ago. In the following graph, the volume of a gas in a balloon is plotted against its temperature. The y-axis, which goes vertical, up and down, will represent the volume, which is measured in liters. That's what the capital L means, liters. The volume of the gas in that balloon. The x-axis, which goes horizontal, left to right, will represent the temperature of that gas. That's measured in degrees Celsius. And the title will indicate that the volume of the balloon was measured at different temperatures. And then the points on the graph will represent the volume of the gas that was measured at a specific temperature. Alright, as you can see, this is the graph that was on our previous slide a few minutes ago. Of course, the title here on top, volume of the balloon versus temperature. The variable here on the bottom, the x-axis, which goes left to right horizontally, is temperature, measured in degrees Celsius. The variable on the y-axis, which runs up and down vertically, is volume, measured in liters. So at every point you can measure, or you are given the data between what temperature it was measured and the volume of that balloon. As you can see, just by looking at these data points, as one goes up, the other one goes up. So this is a nice steady increase for both of these variables. That's what's called a direct relationship. So when one variable goes up, the other one goes up. They are directly connected to each other that way. Alright, the next topic we'll talk about, it tends to confuse students, at least in the beginning, even though it really isn't that difficult once you get comfortable with the idea. And that's called scientific notation. Scientific notation is a way to write numbers in a more efficient way. A lot of times when you deal with chemistry, you're going to be dealing with values that are really, really large or really, really small. And it gets really cumbersome to write down all those zeros. So scientific notation is the way to write really big or really small numbers in a nice, neat, shorthand way. You aren't changing the value of the number, you are just writing it in a more efficient manner. All scientific notation has two parts. You have what's called a coefficient, and that is multiplied by 10 raised to a certain power. And the key thing about the coefficient to remember, it's not listed on here, but I will go ahead and mention it anyway. The coefficient, the smallest that number can be is 1. The highest that number can be is 9.9, because you're dealing with multiplying by a power of 10. So there really is no reason why it should be any higher than 10 or any lower than 1. So here's the example that's given. If you're going to write 2400 in the correct scientific method, what you want to do is move the decimal in this number to where the coefficient is between that 1 and 9.9 range. So the decimal is usually right here where the cursor is. It's just never written for whole numbers like this. In order to get that down to that narrow window, it has to be moved this way, over here, where it falls between the 2 and the 4. So next what you do is count how many places that you moved the decimal. So the decimal is here, 1, 2, 3. So 2400, written in scientific notation, is 2.4 times 10 to the third. And the key here is the value 2400 and scientific notation represent exactly the same value. There is no difference in the value here. 2400. Decimal starts off here, so you need to move over 1, 2, 3 places. So that means that becomes 2.4 0.4 times 10, you moved over 3 places. Those are equivalent values. All right, another example is when the exponent is a negative number. The exponent can be positive or negative. It depends on the number that you're talking about. This value here, 0.00086, that's the same thing as saying 86 10,000ths. So instead of writing it this way, you can write it like this: 8.6 times 10 to the negative 4, because you're moving it this way 4 places. So the example was 0.00086. The only way you can get the coefficient between that window of 1 to 9.9 is to have it as 8.6, because you aren't changing any of these digits. You don't change any numbers. The only thing that you're moving or changing is the placement of the decimal. Alright, so that's going to be the coefficient part. That's going to be, alright, because we ended up between 8 and the 6 here. We count how many places that the decimal had to move. So 1, 2, 3, 4. This is now a negative 4 exponent. Whenever this value is larger than here, the exponent becomes negative. Because 10 to the negative 4 is 0.000. Again, the key rules here: the coefficient has to be between 1 and 9.9. Can't be any bigger, can't be any smaller. And this value is equivalent to this value. There's no change at all. This is a different way to write it. Here's another way to think of the exponential powers of 10. See for here, 10,000. That's the same thing as saying 10 times 10 times 10 times 10. But also, it represents 1 times 10 to the 4th power. That number 4 represents how many zeros there are on the number. So in a number 1,000, there are 3 zeros. So that's 1 times 10 to the 3rd. 100, there are 2 zeros in that value. 1 times 10 to the 2nd power. So it's a nice shorthand way to think of how large a value is by looking at the number. Alright, here's an example of a measurement in scientific notation. The diameter of the chickenpox virus is 0.000003 meters. Now you can write that value, but it does get kind of cumbersome, and it'd be very easy to add another 0 or to take away a 0 when you shouldn't, which of course either way changes the value. The same value this represents can be written this way: 3 times 10 to the negative 7 meters. A decimal or right after this whole number, moving it 7 places this way to make the value smaller. So when that exponent is negative, that whole number will become a smaller value. So that's an incredibly small number, but written in a much more handy way, much more convenient way like this. Alright, here's some examples of how measurements for various things can be written, either if they're really, really big or really, really small. Such as the volume of gasoline used in the U.S. each year, 550 billion liters. So another way to write that value, 5.5 times 10 to the 11th liters. Again, equal value, there's no change here. The diameter of the Earth, 12,800,000 meters. Another way to write that, 1.28 times 10 to the 7th meters. Again, the digits that are here are not lost or just cut off. This wouldn't be 1.2. This have to be 1.28. Any values of any significance are left in the coefficients. You can't just leave off the 8 because that value would make it wrong. See, the average volume of blood pumped during a normal day, 8,500 liters, or 8.5 times 10 to the 3rd. Going down to these smaller values, the mass of the stirrup bone, which is one of the bones in the ear, 0.003 grams, or equivalent to 3 times 10 to the negative 3 grams. Because you start with here, you move the decimal over 3 places that way, and you end up with 0.003. And the mass of the bacterium mycoplasma, 0.00000000000000001 kilograms. It'd be really a hassle to write this kind of value all the time. So the easy way to write this value, 1 times 10 to the negative 19 kilograms. Okay, in this chapter, we'll go over chemistry and measurements. Now, in addition to assisting physicians, registered nurses, like the one you see here in the picture, work to promote patient health and to prevent and treat disease. As you can imagine, measurements are a key role in their job and also in chemistry in general. So as you can see here, she's checking this man's blood pressure. We'll begin with basic units of measurement. Now, in a great majority of the world, the metric system is the standard system that's used for measurements, and mostly because it's far easier than what we use here in the United States, the English system. We're one of only a few countries in the world that still use the English system. But the metric system is based on powers of 10. So it's much easier to convert one unit to another because they're all based on this multiples of 10. All right, so for the learning goal of this chapter, be able to write the names and abbreviations for the various metric or the international system units of measurements for length, volume, mass, temperature, and time. So in this picture, you have the two students walking most likely to class. The temperature 22 degrees Celsius, which would be equivalent to 72 degrees Fahrenheit. The backpack here, 12 kilograms or 26 pounds. This person's height, 1.65 meters or 65 inches. This person's weight, 58.2 kilograms or 128 pounds. And they are walking 2.1 kilometers or 1.3 miles. So all these are equivalent values to each other. This one's in metric, one's in English. Metric, English. Now, scientists throughout the world have used the metric system for measurements, and there's a slight modification of that metric system. It's called the International System of Units, or SI units. And there's very little difference between the two. There are some units that are slightly different, but we'll get into some of those here in a few minutes. But these are the units that are used throughout the world scientifically for measuring length and volume, mass, temperature, and time. All right, here are some of the more common ones. This column here is what's used in the metric system, and this column here is what's used for the international system of units. For the standard unit of length for the metric system is meter, abbreviated by the lowercase m. Also for the international system unit is also meter, with the lowercase m. And something I'll mention now, be careful when you are writing these abbreviations for these units to use lowercase when you're required to use lowercase and not capital. You can't go back and forth interchangeably because a capital M means something very different than meter. And we'll talk about that a little bit later on in this chapter. But lowercase m is always for meter. The standard unit of measurement for volume for the metric system is liter, or capital L, or in the international system is going to be the cubic meter, m to the third power, a cubic meter. Now, liter is probably the only measurement in countries that use the English system, like the United States, that is used most often. So you can buy a 2-liter or 3-liter soft drink at a grocery store. That's probably the only one that, as Americans, we are most familiar with as a metric unit, is liter. The common unit for measurement for mass and metric system is the gram, represented by lowercase g, and in the SI units, the kilogram, a kg. All right, for temperature, for the metric system, it's degrees Celsius. Degrees in a capital C for Celsius. And for the international system, it's called Kelvin. We'll talk about that a little more later. And then the unit of measurement for time is the second, or lowercase s. And that's true for both SI units and metric. So you will see these abbreviations quite often when it comes to chemistry, especially when we get to the chemical equations and how to use them. All right, the length in the metric and SI systems is all based on the meter, which is just slightly longer than 1 yard. So for here, 1 meter is the same thing as 100 centimeters. You remember centi or cent. If you think of cents in a dollar, there are 100 of those. So the prefix centi always means 100 of, or 100th. 1 meter is also 39.4 inches. It's also the same thing as 1.09 yards. And then 2.54 centimeters is the same thing as 1 inch. So all these are equivalent values to another. That is the same as that. That is the same as that. That is the same as that. And that is the same as that. Alright, when we talk about volume, we'll be talking about the liter or the milliliter. Now, volume is the space that's occupied in 3 dimensions, both length and width and in depth. So the standard unit of measurement is called the cubic meter. And it's called a cubic meter because it involves 3 dimensions: length, depth, width. That's why measurements of volume are always in a cubic in dimensions. But in a metric system, the volume is based on the liter, which is slightly more than 1 quart. So we have some equivalent values down here. 1 liter is the same thing as 1,000 milliliters. 1 liter is also the same thing as 1.06 quarts. And 1 quart is also the same thing as 946 milliliters. And you see those measurements here on this image here of the graduated cylinder. Right there, about 946 milliliters equals 1 quart. So just under 1 liter. Alright, when we talk about mass, we'll be using the gram or the kilogram. And the mass of an object is its measure of quantity of stuff that it has, the quantity of material that's found inside that object. 1 kilogram is the same thing as 1,000 grams, because a kilo always means 1,000. So this word will literally break down into 1,000 grams, kilograms. 1 kilogram is also the same thing as 2.2 pounds. And 1 pound is the same thing as 454 grams. Or in the SI units for mass, you will use the kilogram or kg. That's usually used for larger masses. And in the metric system, you'll use the gram or lowercase g, which is going to be used for lower or smaller quantities of mass. Alright, next we'll move on to temperature. You'll be using either degrees Celsius or Kelvin. Now the temperature will tell you how hot or how cold something is. So for the metric system, you'll use degrees Celsius, and for the international system, you use Kelvin. Now water will freeze at 32 degrees Fahrenheit, and that's equivalent to 0 degrees Celsius. These are exactly the same temperature, just using 2 separate scales. Same thing with the boiling point of water. Water will boil at 212 degrees Fahrenheit, which equals 100 degrees Celsius. Those are equivalent temperatures, but using 2 separate and distinctly different scales. Now the Kelvin scale for temperature begins at the lowest possible temperature, the temperature called absolute zero, which is 0 Kelvin. That's equivalent to negative 273 degrees Celsius. And that scale we'll get into more a little bit later in our series of videos. Alright, next we'll talk about time. The unit for measurement for both the SI system and the metric system is the second. And then from there you can get larger and larger, but the base unit that you use is second. So you can go anywhere from years to days to hours to minutes, seconds. So 60 seconds is 1 minute. 3,600 seconds is 1 hour, and so on. Alright, next we'll move on to the rules for rounding off values. Now, this can become very significant when you're dealing with measuring quantities, because you don't want to make a quantity too less important or too more important. So when it comes to rounding, the key number to remember is the number 5. So anything that's 5 or higher will be rounded up to the next number. If it's less than 5, nothing gets changed. So the key thing that you're looking here is to where you are rounding to. So let's say for this example, 8.4234. If you're rounding off to just having 3 significant figures, these first 3, you look at the very next one next to it. This number 3 is less than 5, so nothing will change to that number. So 8.42. Everything else gets cut off. If you're rounding to just 2 significant figures, you'll have these 2 here, 8 and 4. The 2, same thing, is going to be less than 5. It won't change this, so 8.4. Okay, that's an example where nothing changes. But for this next one, things do change. The number you're given is 14.780. If you're running that to 3 significant figures, 1, 4, and 7, you look at the number just next to that one, 8. 8 is higher than 5, so that's going to cause this value to go up 1. So this number will round off to 14.8. Everything else behind that 8 is dropped. If you're rounding this number to the nearest whole number, or to just 2 significant figures, 1 and a 4, again, the 7 is going to be higher than what you need. That's going to cause this value to go up in 1, or that rounds up to 15. So it all depends on what place value you are rounding to. You look at the very next column to the right, is that value 5 or more? If it is, then the last place you round to will go up by 1. If it's less than 5, then nothing changes. Alright, next we'll move on to prefixes, something that's going to be very important, and understanding some basic prefixes will help you understand chemistry a lot faster, because the key thing about prefixes is their definitions never ever change definition. Doesn't matter if you're talking about chemistry or physics or biology or anatomy. Kilo always will mean 1,000. Centi always means 100th or 100 of. It doesn't matter if you're talking about grams or meters or liters. Those definitions never ever change. So, and some prefixes you will see much more commonly than others, like milli, micro, kilo, centi. Those you will see quite often. There are some that will pop up on occasion depending on what you're working with. But if you are familiar with some of the more common ones, being able to convert from one unit to the next gets quite simple. So for example, the ones that are given here, milli and micro, these are usually fairly common, especially in a chemistry setting or a nursing setting. Milligram or milligram, either way to pronounce it is fine. This word literally breaks down into 1,000th of a gram. Milli will always mean 1,000th. Microgram always means 1,000,000th of a gram. So microgram or micron, those terms are interchangeable, especially when you get to anatomy. Now you'll see here this has two abbreviations listed for microgram. That's because in medicine and in anatomy you'll see microgram used quite often, and the way you write micro looks like a lowercase u that's in italics and with a small tail right here. It's very often misread when a person writes it as opposed to a computer typing it like you see here. But it's very easy to misread that because it's hard to write it correctly by hand. So another way to write microgram is also mcg, or microcentigram. So these two are equal. It just depends on if a human is writing the value or not. Here are some prefixes for some of the larger values. We'll start here, then work our way up. So kilo, prefix kilo, always abbreviated by lowercase k. That means 1,000. Also represented by 10 to the third. There are 3 zeros here. So that's why the exponent is the number 3. So kilogram, 1,000 grams. Kiloliter, 1,000 liters. Kilometer or kilometer, 1,000 meters. Definitions never ever change. Mega, capital M, not lowercase m like you saw for meter, but a capital M always means 1,000,000. There are 6 zeros here in that value. That's the same thing as 10 to the 6th. Giga, capital G, means 1 billion. Again, there are 9 zeros in that value. So that quantity is 10 to the 9th power. Then tera, capital T. Then peta, capital P. And you'll see the corresponding values here, 10 to the 12th and 10 to the 15th here. So for those of you who are fairly familiar with computer measurements, a megabyte is 1,000,000 bytes, gigabyte 1,000,000,000 bytes, and you get the tera, then peta, and so on. So it doesn't matter if you're talking about computers or human anatomy or physics or chemistry, these prefixes never ever change their definitions. Alright, those were some of the larger prefixes or larger values. Now we'll go the other way, getting smaller. Deci, lowercase d, that means a tenth. Deci, think of decade, there are 10 years in decade. That's how you get to 1/10, or 10 to the negative 1. Centi, lowercase c, 100th, or 0.01, or 10 to the negative 2. Milli, 1,000th, 0.001, or 10 to the negative 3. Micro, and that's the reason why it has that asterisk here. It's explained here. In nursing and medicine, it's easily misread when handwritten. So when you see it on a computer screen, you'll see it like this. If you see it handwritten, you'll usually see that, mcg. Same equivalent value, just two different ways to express it. That will mean 1,000,000th, or 10 to the negative 6. Not 1 million, but 1,000,000th, because we're talking about fractions of a whole. Nano, 1 billionth, so 0.000000001, or 10 to the negative 9. And then pico, 10 to the negative 12, and femto, 10 to the negative 15. So of these, when you talk about chemistry, we talk about human anatomy, you will probably see the first 5 of these most often, from nano, micro, milli, centine, deci. If you're dealing with physics, then you'll get into pico and femto. Alright, prefixes and equalities, something we've already mentioned briefly already. Alright, the relationship that a prefix has with its unit can be expressed with this numerical value. Think of the prefix as the first name of the value. Just like we talked about before, kilo always means 1,000. So a kilometer or kilometer, 1,000 meters. Kiloliter, 1,000 liters. Kilogram or kilogram, 1,000 grams. And there's some equivalent values here, each of those. But again, definitions never ever change, regardless if you're talking about mass or volume or length or whatever. These definitions for the prefixes never change. Alright, next move on to the cubic centimeter. Cubic centimeter is abbreviated by CC, cubic centimeter, or cm raised to the third power. It's a cubic measurement. You're talking about a three-dimensional measurement, length and width and depth. So that's why I say cubic description, because you're talking about volume. Now, the cubic centimeter is exactly the same thing as a milliliter. So these 3 values here are equivalent. So 1 cubic centimeter is the same thing as 1 cc, the same thing as 1 milliliter. So it's important to keep that in mind, especially if you're talking about medicine and administering drugs. As you can see in the picture, this person is giving a bag full of medicine, and it says it's 1,000 milliliters. That value is exactly the same thing as 1,000 cubic centimeters, or 1,000 cc's. Right, on this image, you will see a graphical representation of a cubic centimeter. If you were to envision a cube that's 10 centimeters long, 10 centimeters deep, 10 centimeters wide, 10 times 10 times 10 gives you that 1,000 cubic centimeters, which is exactly the same thing as 1,000 milliliters, exactly the same thing as 1 liter. These 3 values are equivalent. This is represented 3 different ways using 3 separate units, but the actual quantity being measured is exactly the same. Alright, next move on to measuring mass. Visit a doctor for any kind of exam. You are usually weighed shortly after you get there. Your mass will be recorded in either pounds or in kilograms, most likely in kilograms. And then various lab reports are usually reported back in micrograms. Alright, below here are some equivalencies between different measurements. 1 kilogram, like we talked about before, 1,000 grams. Same thing as 1 times 10 to the third power grams. 1 gram is 1,000 milligrams. 1 gram is 100 centigrams. So again, all of these are going to be equivalent to each other. That equals that, which equals that. That equals that, equals that, and so on. Here are some common equalities, both for the metric system and then what we use here most often the English system in the US, and then the equivalency between those two. 1 kilometer is 1,000 meters, 1 meter 1,000 millimeters, and so on. 1 foot in the US equals 12 inches. Let's see, 1 yard is equals 3 feet. 1 mile is 5,280 feet, and then below are the measurements for mass and volume and so on. So you can see where the English system, or what we use here in America, is difficult to learn and difficult to follow for most aspects, because it doesn't follow a discernible pattern. There's no increase by 5 or increase by 10. There's always a weird number associated with each value. 12 inches in 1 foot, 3 feet in a yard, or 5,280 feet for 1 mile. There's no pattern to it, which is exactly the opposite for the metric system, where everything is based on a power of 10. 10, 100, 1,000, 1 100th, 1 1,000th. It's all based on just moving a decimal place, either left or right. For the English system, it gets a lot more confusing, so it's very easy to get confused when you're trying to express different measurements in different units. And this last column has the equivalencies between the metric and the US system. 1 inch is equal to 2.54 centimeters. 1 meter is 39.4 inches. 1 kilometer, 1 kilometer, same thing as 0.621 miles. And there are other equivalents here. 1 liter, 1.06 quarts, 1 kilogram, 2.2 pounds, and so on. Alright, next we'll talk about the chemistry linked to health and toxicology. Alright, as new chemicals are being developed and tested, one thing that has to be always taken into consideration is at what level is this chemical not safe to be used. And unfortunately, that has to be tested. That's why testing on animals is such a key role in developing chemical drugs or pharmaceuticals. Any kind of material that uses chemicals has to be tested to determine at what point people should not use it. That point is called the LD50, or the lethal dose. It's at that level of concentration that 50% or more of the test subjects are killed with being exposed to that substance. So LD50, that level of toxicity. So at that point and beyond, it will be toxic to humans. That's what's called the LD50. Lethal dose at when 50% or more of animals tested were killed. Alright, so the LD50 for something like caffeine is 192 milligrams per kilogram of that person's body mass. To give you an idea of how large this quantity can be, a male that weighs 175 pounds, that equals to about 80 kilograms, 80 kilos. So that person's LD50 would be 80 kilograms times 192, or 15,272 milligrams. That point and beyond would kill that male that weighs 80 kilograms. But 15,000 milligrams is a very large amount of caffeine. And to give you an equivalent value, the 15,272 milligrams is the same thing as 15 grams of caffeine. So that'd be a huge amount of one substance to take in. So at that point, he's probably going to be dead from other things anyway. Alright, next move on to the topic of density. A learning goal for this section of this chapter, being able to calculate the density of any substance by using a formula that we'll go over, whether it be a liquid or a solid or a gas. Now, objects that are more dense or heavier in water will sink. Objects that are less dense will float in water. That's what you're shown here in the speaker. You're shown a cork, a block of ice, the water, a piece of aluminum, and some lead. The way you calculate density is the substance mass divided by the volume that it's in. So for example, the density for cork is 0.26 grams per milliliter. That is less than what it is for water. Water is always going to be 1 gram per milliliter. So the cork and the ice are less than that. That's why they float in water. The aluminum and the lead, their densities are higher than that 1 gram per milliliter, so they will sink. This equation will explain how many things will either float or sink when placed in water, all due to its density. If it's more than density of water, it sinks. If it's less, it will float. Alright, this table has some densities of some very common substances. Some we already saw in the last picture, the cork and the block of ice. Body fat, just slightly less than water, 0.909 gram per milliliter. Bone, 1.8, so that would sink. So in this table, anything from muscle down would sink. And these are all solids. So you would imagine most of these would sink. The only ones that will not on this table are the cork and the body fat and the ice. But all these other values are going to be greater than 1. So that's why they will go down to the bottom of the container. For liquids, gasoline is 0.74, so that would float on water. Ethanol, or ethyl alcohol, would float, 0.79. Anything from this point on in the column and down would sink. Urine, just slightly heavier, or slightly more dense than water, so that would sink. Plasma, what comes from blood, milk, blood, mercury, all those are much denser than water, so it would sink. As for gases, as you'd imagine, a lot of these will be lighter, less dense than water. Okay, so of this column, hydrogen, helium, methane, and neon will be less dense than water, so they will float. And then nitrogen, air, oxygen, and carbon dioxide, from this table anyway, are the only ones that would be heavier, would be more dense than water, so they would sink. Alright, like mentioned on a previous slide, the formula for calculating density, the mass of the substance divided by the volume of the substance. So for a solid or a liquid, that can be represented by gram per cubic centimeter or gram per milliliter. The density of a gas is going to be a gram per liter. And the reason why for here you can represent these two separate ways, 1 milliliter is the same thing as a cubic centimeter. The last topic of chapter number 2 is called specific gravity. Now specific gravity is a relationship between the density of a given substance compared to the density of water. And the way you calculate specific gravity is by dividing the density of the sample by the density of water, which is 1 gram per milliliter at a temperature of 4 degrees Celsius. Now this value for specific gravity does not have a unit that goes along with it. You just get a numerical answer. For the units used in these calculations will cancel each other out. The formula for specific gravity, the density of the sample divided by the density of water. This is something that we will get into in greater detail when we get further along in this crash course on chemistry, when we deal with some very detailed chemical formulas and how to use them correctly. We will revisit this topic again in a future chapter. Okay, we'll move on to Chapter 3, the classification of matter. Now matter, something we talked about in a prior chapter, is material that makes up all things. If something takes up space and has mass, it's made up of matter. So anything that takes up space and has any kind of mass is considered to be matter. Now matter can be classified according to its composition. A pure substance is something that has a very definite composition or a fixed composition. There's also a mixture, where you have two or more different substances that are physically mixed but are not chemically combined. And we'll talk more about that in a second. Okay, we'll talk about a pure substance first. It's classified as a type of matter that has a very definite or a fixed composition. An element is a very good example of that. Any element, say on the periodic table of elements, all that is found in that element are those particular atoms. So you only have one atom, say in a mass of aluminum or a mass of carbon or so on. There's nothing else found in that sample. When you have two or more elements combining, that's when you form a compound. So a compound is two or more elements that are always found in the same proportion. Like we just mentioned, elements are a pure substance that contain only one type of material. Copper, lead, aluminum. If you have, say, in this example, a copper penny, there's no other element, no other material found in that penny other than copper. You won't find calcium, you won't find potassium, you won't find helium. All you'll find there is copper. It is a pure substance. And again, in compounds, two or more, it has to be at least two elements, and there's no limit on how many there can be, but there has to be at least two elements that combine. And they combine in a very fixed ratio. And here's some common examples. Hydrogen peroxide, H2O2, table salt, sodium chloride, sugar, C12H22O11, and then water, H2O. And here's what I mean by a fixed, definite ratio. Let's compare hydrogen peroxide and water. Very, very different substances. Water, obviously very safe to drink, H2O. Hydrogen peroxide is very dangerous, very toxic, so it's something that you would not want to drink. So the formula for hydrogen peroxide, H2O2. For water, H2O. The only difference chemically in these two compounds is there's one more oxygen here in hydrogen peroxide. So if you start with this and take away one of these oxygens, you get H2O, water. So just by removing one element will mess up that ratio and will give you a resulting totally new compound. So same thing with water. If you take away, say, a hydrogen from water, you end up with hydroxide, which is completely different than water. So compounds are in a very definite, very fixed ratio. So anytime you have H2O in a compound, this will always give you water. This will always give you hydrogen peroxide. This will always give you table salt or sodium chloride. This combination will always give you sugar. It can't be anything other than those. All right, we just talked about table salt. Table salt is a compound that combines the elements of sodium and chlorine. When they form together, sodium chloride, that forms table salt. That's a very good example of a compound. So sodium and chlorine will form the common table salt. All right, next move on to mixtures. A mixture is a type of matter that will consist of two or more substances that are combined physically but not chemically. And these are two or more substances in different proportions also. And the key thing here is that they are physically mixed and can be physically separated, but they're not chemically joined. Think of this as a big bowl of M&Ms, where you have some red, some green, some brown, some yellow. They're all in the same space. They are physically connected, but they're not chemically bonded to each other. You can separate the reds from the greens, from the yellows, and so on. All right, there are different types of mixtures. Homogeneous mixtures. Prefix homo means the same. So for this type of mixture, the composition is uniform throughout the entire mixture, and the different parts that make up this mixture are not visible. And the example that's given here is brass. Brass is a combination of copper and zinc. So when you see this picture of a brass vase, all you see is brass. You don't see the zinc. You don't see the copper. You see what results in their combination together, which is brass. All right, another type of mixture is called heterogeneous mixture. Prefix hetero means different. So in this type of mixture, the composition will vary from one part of the mixture compared to the other, and the different parts of these mixtures are visible. The example that's given here, a glass of water and copper. You can see the water, you can see the copper. They are still mixed together, but you see the individual components that make up that combination. All right, next move on to the states of properties of matter. And the first one we'll talk about are the solids. Now, solids have a very definite shape and a very definite volume. The particles that make up solids have a very fixed arrangement, and they're very, very close to each other. Anything that is solid has a definite shape. It doesn't change its shape varying on its container or where you put it. A textbook doesn't change shape because you put it in, say, a shoebox or a backpack or a suitcase. It stays the same definite shape. Volume doesn't change, the shape doesn't change because the particles are so compacted together inside it. So this block of amethyst here won't change its shape no matter where you put it. Alright, next move on to liquids. Liquids have an indefinite shape but a definite volume. A liquid will take the shape of its container that it's placed in. So for this example, you have 3 glasses of water. The glasses are different shapes, so it will take the shape of the container that it is placed in. The particles are close to each other, but they're able to move by one another, and these particles tend to move slowly. Let's say if you were to take a liter of water and pour that water into a 2-liter plastic bottle and pour that volume of water into a bathtub. The volume is still the same, but the shape will be very, very different. So again, it is the container that the liquid is in that will determine its shape. All right, gases, these have an indefinite shape and also an indefinite volume. They take the same shape as their container that they're in, just like a liquid would. These are considered fluids. So a gas and a balloon take the shape of that balloon. The particles in gases are very, very far apart, and they move very, very fast from one another. All right, next we'll talk about physical changes. A physical change in a substance is where there is a change in shape or a change in the state. We'll talk about what those are here in a second. But there's no change in the chemical makeup of that substance. Chemically, it's still the same, it just looks a little bit different. Are some common examples of physical changes? Water boiling to form water vapor. All forms of water, whether it be liquid or solid or gas, think of a glass of water or an ice cube or water vapor. Those are in 3 different states, but it's still water chemically. So it may look different, but it is still a form of water. Those are physical changes. Some other examples of physical changes: paper is cut into tiny pieces to make confetti. It is still paper. It may be really, really small pieces, but it is still chemically a piece of paper. Copper being drawn into thin wires. It may be thinner and longer, but it is still copper. Chemically the same, but physically looks different. Next, move on to chemical changes. When a chemical change happens, you are forming a new substance with new chemical properties and new physical properties. A good way to think about these are things that cannot be undone. Or you have physical changes, some of them can be undone. You can freeze water, or you can evaporate water, or melt ice. You can change the physical state of water, even though chemically it's still the same. You can change physical changes, but chemical changes can't be undone. So an example here, amount of sugar being caramelized. You can't unburn something. By caramelizing the sugar, you are giving it new chemical properties. You're giving it new physical properties. You are making something different and new. Some other common examples for chemical changes. A silver metal is shiny. Once it's exposed to air, will eventually give you a black grainy coating as silver starts to tarnish. And is chemically something different. And you can't undo that. Burning a piece of wood or burning anything makes a new compound, makes new material. So that is a chemical change. You can't unburn something. Same thing with this last example here. Iron mixing with oxygen to form rust, especially over time. You can't undo that. That is a chemical change. It may look different physically also, but chemically it is something different. It has new properties and it is a new compound. Right, now we'll move on to temperature. Temperature is a measure of how hot or how cold an object is compared to another object. And this will indicate the heat flow from an object from a higher temperature to an object that has a lower temperature. And of course a thermometer will be used to measure temperature. We've already mentioned briefly the 3 types of scales used to indicate temperature. One we'll talk about now is the Kelvin scale. The coldest possible temperature that is known is negative 273 degrees Celsius. That's known as absolute zero. At that point, the particles in that material stop moving and cannot generate heat, so there is no temperature beyond that point. This is also represented by 0 Kelvin. Not 0 degrees Kelvin, but just 0 Kelvin. One thing that's a little bit different from Kelvin compared to the Celsius or Fahrenheit, there's no negative temperature reading for the Kelvin scale. The lowest you can get is 0 Kelvin. And also has the same size units as the Celsius scale. So 1 Kelvin would equal 1 degree Celsius. And this formula here is a way to calculate a given temperature in Fahrenheit, how to convert that to a Celsius scale. What you do is you take that temperature as given, let's say it's 113, you subtract 32 from that Fahrenheit temperature and divide that total by 1.8. So 113 degrees Fahrenheit would give you 45 degrees Celsius. Alright, on this image we have the comparison of the three major scales for temperature and what goes on at key points for each. I will start here on Fahrenheit scale. The freezing point where water freezes, 32 degrees Fahrenheit. Also the same thing as 0 degrees Celsius, which is also the same thing as 273 Kelvin. Normal body temperature in the Fahrenheit scale, 98.6. In Celsius, 37 degrees Celsius. And for Kelvin, 310. The boiling point of water in Fahrenheit, 212 degrees. For Celsius, 100. And Kelvin, 373. Now it's important to remember that even though there are three different scales used, the temperature being measured is exactly the same. So the amount of heat generated, say, by 98.6 degrees Fahrenheit is equivalent to 37 degrees Celsius, which is also equivalent to 310 Kelvin. So it's exactly the same quantity being measured, but using three separate scales. Alright, next we'll move on to energy. Now, energy is what helps make objects move, makes things stop, and has a formal definition of the ability to do work. And there are different types of energy. One is kinetic and one is potential. Kinetic energy is the energy of motion. Kinetics is always a reference to things moving. Water moving or a car moving. Anything that has any kind of motion has kinetic energy. The opposite of that would be potential energy. This is where you have energy stored to be used later. Water being blocked by a dam. A spring being compressed. Pulling back on, say, a rubber band. You're storing energy that's not being used for movement yet, but it's being stored for use later. It has the potential to make kinetic energy. Moving on to heat and energy. Heat is the energy that's associated with the movement of particles in a substance. The faster the particles move, the more heat that gets generated, or the more thermal energy is generated. Alright, let's say you're given an ice cube, and because it's a solid, the particles tend to move incredibly slow. If you were to add heat to that ice cube, that will cause the particles to move much faster. And as those particles move faster, they generate more heat. That will change their state from a solid into a liquid. That's how you get from a block of ice into liquid water. The particles inside that ice cube are being moved so fast that they actually break the bonds that hold them together and turn it into a liquid. Energy is measured in the International Systems Unit by the unit called joule, abbreviated by the capital J, or can also be used in what's called kilojoules, lowercase k, capital J. Remember, kilo always means 1,000, so a kilojoule is 1,000 joules. You can also use the term calorie or kilocalorie. Those are also units of measurements for heat. Now, the actual definition of calorie in the formal sense, in the technical sense, is the amount of energy that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. To compare a calorie to a joule, 1 calorie equals 4.184 joules exactly. And here's a comparison. If you're given one, it can convert to the other. But notice that the C in calorie is lowercase, and that's important. It's something we'll talk about next. Now, when I say calorie, most people think of the calories in the food that they eat. And this is a term that gets misused all the time. In science, the calorie is what we just talked about, what it takes to raise 1 gram of water 1 degree Celsius. That's used in physics, in chemistry, and biology, that is a real scientific term, calorie, lowercase c, CAL. But when you talk about calories in food, what you're really talking about are food calories. And that's written by, or indicated by, a capital C. And what this really represents is 1,000 calories, or a kilocalorie. So when you read, say, food labels like this at a grocery store or in your kitchen, what you're really reading is kilocalories, or 1,000 calories. So kcals. So when you talk about calories from food, you should indicate that it is a food calorie, or use a capital C to indicate that it is a kilocalorie, not a regular calorie unit in science. Right, next, move on to what was called specific heat. A substance such as water has a very high specific heat, which helps keep temperatures more moderate in the summer and the winter. And this can vary greatly, specific heat by substance. And the definition of this is the amount of heat that is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. And it can vary greatly depending on the type of substance that we're referencing. And this goes into how well an object can be heated, how much it can be cooled, how much heat can be transferred from one material to the next. Here are some examples of some common elements and common compounds and their specific heat. Say aluminum, a solid piece of aluminum, 0.214 calories per gram, degrees Celsius. Copper, much lower, 0.0920. Gold, 0.0308, and so on. Of course, water is 1. When it's a liquid, and when it's a solid, like an ice, it's going to be half that amount. Alright, now we'll talk a little bit more about a changing of state. This is when a material gets converted from one state to another, from a solid to a liquid or to a gas, whenever you are changing a physical shape or a physical state. There was something being melted, something being vaporized, something being frozen, and so on. Alright, a substance is considered to be melting when it reaches its melting point, or MP. This is the temperature at which it will turn from a solid into a liquid. So when that block of ice starts to become liquid, that is its melting point. And of course the opposite of that, the freezing point, or FP, is where a liquid turns into a solid. When that glass of water turns into a ice cube, it's become moving from one state to the next, from liquid to solid. Alright, move on to the heat of fusion. This is the amount of heat that it gets released when a gram of liquid freezes. So that's freezing point. You'll have a release of heat, a release of energy. Also the amount of heat needed to melt 1 gram of a solid at its melting point. So for example, water, the heat of fusion is 80 calories per gram of water. Alright, next we'll compare evaporation, boiling, and condensation. Of course, we'll talk about water. Water will evaporate when the molecules on the surface gain enough energy where they are converted into a gas. Remember, the particles of liquid move kind of slow. So as the particles of water are heated enough, particles will move around so fast they will actually convert and change state into a gas. Now when the opposite of that happens, when that gas will start to lose energy, those particles will start to slow down and they will collapse together and form a liquid, what's called condensation. Right, when water is boiling, all of the water molecules acquire enough energy to form a gas, what's called to become vaporized. Of course, during boiling, the molecules of the liquid are converted to gas throughout the liquid as well as on the surface. So not just the bubbles you see on the surface bubbling, all the particles inside that substance of or water are boiling also. Right. Heat of vaporization. This is the amount of heat that's absorbed to change 1 gram of liquid to gas at the boiling point, and also the amount of heat that is released when 1 gram of gas changes to liquid at the boiling point. So for water, 540 calories per gram. So say you're starting with the liquid water here. When you add heat to that, the particles will start to move faster and faster to the point where they are very, very far apart and they become a gas, where they are vaporized. All because you're adding heat, making the particles move faster. When these particles start to lose energy, when heat is taken away, they will condense to form liquid. So going from a gas, water vapor, to liquid water, condensation. So it all depends on how much heat is either introduced or taken away. Alright, next we'll talk about heating and cooling curves. Here's a common example of a heating and cooling curve here. You're given information on when a substance turns from solid to liquid and from liquid to gas, and when they are basically changing states and at what temperature, and how much heat is absorbed. These diagonal lines here indicate a change in temperature for a physical state, and these plateaus here and here indicate the actual change of state. Let's say you have solid water here, a block of ice. As it starts to melt, it goes here. Then you start to introduce more temperature, more heat. So you see the temperature increase over time, and the more heat gets absorbed. At this point, it will start to boil. As more heat gets introduced, more energy to the particles, so they move faster, and it becomes a gas. So of course, the opposite of that would be the cooling curve. It shows you where the physical states change from gas to liquid and from liquid back down to solid. So for the chart on the previous slide, that shows you how heat was added over time. And for here, it's the exact opposite. How heat gets removed, which will remove energy from particles, which will make it slow down, which will make a gas turn into a liquid as it condenses here to a liquid. And from here, getting even more slow with the particles, it becomes a solid or ice. Okay, in this chapter, we'll talk about various elements and their characteristics, the periodic table, and how you're able to read the periodic table, and we'll start off with chemical symbols. Now, chemical symbols are used to represent the names of that element. The symbol will have either one or two letters. If it's one letter, you will use a capital letter. If you use two letters, only the first letter is capitalized. And here are some common examples here. For carbon, capital letter C, nitrogen, capital N, fluorine, capital F, and oxygen, capital O. For some two-letter symbols, cobalt, CO, only the C is capitalized, the O is not. Calcium, Ca, aluminum, Al, magnesium, Mg. Some very common examples of both one and two-letter symbols used for various elements. There's a table of some common elements. Some have one letter, some have two. And some of these symbols are fairly obvious what they represent. O for oxygen, C for carbon, H for hydrogen. But some symbols are completely different than what their element's name is. And that's because their symbol is based on the element's Latin name. Say, for example, copper. You would think it'd be Co, but Co is cobalt. The Latin name for copper is cuprum, so the symbol would be Cu. Gold, the Latin name for gold is aurum, so the symbol is Au, not G or Go. Mercury, its chemical symbol is Hg. Iron, Latin name is ferrum, so it would be Fe. Lead, Pb, based on the Latin name plumbum. And potassium would be P, it's going to be K, because its Latin name is kalium. So some of these symbols are pretty straightforward, but some are not. So some you just have to learn to recognize. Alright, now we'll move on to the periodic table. The periodic table organizes the 118 known elements into groups based on their characteristics. Just by a first glance at the periodic table, it looks like the elements are put there at random, but there's a reason why the elements are where they are. There's a reason why carbon is here and not over here. There's a reason why every single element is in the position that it is. And the learning goal for this chapter, or for this section, using the periodic table to identify the group and the period of an element, and to be able to identify the element as either a metal or a nonmetal or a metalloid. Alright, first we'll talk about how to distinguish between groups and periods. In a periodic table you have rows of elements, then you have vertical columns of elements. The vertical columns are known as groups, and then the horizontal rows are called periods, and they're labeled from the top of the table down, so 1 through 7. So here's a common image of a periodic table. Period 1, period 2 goes all the way across here. Period 3, 4, 5, 6, 7, and so on. And you'll see this represented a lot this way. If you look closely at these numbers here, how it jumps from 57 up to 72, and on the row down here from 89 to 104. These two rows of elements belong in here. They're just taken out to save space. So that's how it's commonly represented with the periodic table. But these two rows actually will fit into here. Alright, the group numbers are written one of two different ways, either numerically 1 through 18, or using a letter A or B. The letter A is used for representative elements, and then the letter B for transition elements, the ones on the bottom, the ones in the middle part where it dips down. These are transition elements. So we'll use both writing systems here since both are used. All right, here's a common example. Group number 2, or 2A, that vertical column here. And then period number 4, because that's the fourth row. 1, 2, 3, 4. So all of these have some common traits, and all of these have some common traits. All right, we'll start with the representative elements. One's on the far left-hand side, columns 1 and 2. Then we'll jump over to the far right side. All right, the first group we'll talk about is group number 1, or 1A, depending on what system you use. These are called the alkali metals. And these will include lithium, or Li, sodium, Na, not S or SO for sodium, but its Latin name is natrium, so that's why the chemical symbol for sodium is Na, potassium, K, rubidium, Rb, and cesium, Cs. And here are some pictures of some of those. We have lithium on top, sodium here, and potassium here. All of those are in that vertical column, that group number 1. Alright, next we'll move on to group number 2, or 2A, depending on what system that you are using. These are the alkaline earth metals. These are very shiny metals, but they're not as reactive as the ones from group 1. Group 1 elements are really, really reactive. So the ones that are found in group 2, beryllium, or Be, magnesium, Mg, calcium, Ca, strontium, Sr, barium, Ba, and radium, Ra. And that vertical column, number 2. And in the picture here, strontium is what gives fireworks that bright red color. Alright, now we'll move on to the far right-hand side of the periodic table, going on to group 17, or group 7A, again based on what system you use. These are the halogens. These include fluorine, represented by a capital F, chlorine, Cl, bromine, Br, and iodine, with a capital I. Here's some images of those. These tend to be also very reactive, just like the ones in column 1, or group 1. Alright, when you see the periodic table, it's often to see it color coordinated based on elements and their characteristics. A common way to represent that is with metals and nonmetals. So for this example here, you'll see a very thick jagged line that goes down like a stairwell here. Everything that's on the left-hand side of this, in this light blue color, are metals. Everything that's to the right-hand side of that line, this light beige, light yellow color, are nonmetals. And the elements that border this zigzag line have characteristics of both metals and nonmetals. They're called metalloids. Metals, nonmetals, and kind of a mix of both metalloids. That's why these are in like a light mint green color. Alright, we'll talk about some traits of the three of those, the metals and metalloids and nonmetals. Metals, other than hydrogen, are located on the left-hand side of the periodic table. They are going to be very shiny and very ductile, which means they're able to be bent and twisted into various shapes. These are going to be very good conductors of electricity and heat. Okay. All metals are also going to be solid except for mercury. Mercury is the only example of a metal that is liquid at room temperature. If you've ever been to the doctor and had your blood pressure taken by a manual blood pressure cuff, where the measurement is on the side on the wall, that silver liquid that goes up and down to measure your blood pressure, that is mercury inside. That's why blood pressure is measured in millimeters of mercury. Nonmetals will be on the right-hand side of the table. These are going to be very brittle and very dull, and very poor conductors of heat and electricity, but very good insulators. And nonmetals also have very low densities and very low melting points. Now the ones that kind of overlap between metals and nonmetals are called metalloids. These have properties of both metals and nonmetals. They are better conductors than nonmetals, but not as good as metals. Because of this, they're used as semiconductors and insulators, because they can be modified to function as either a conductor or an insulator. Alright, now move on to the atom. The atom is the smallest particle of an element that retains the characteristics of the element. So all elements are made up of atoms. Everything is made up of atoms. So for example, aluminum foil will have atoms of just aluminum. There are some main particles that make up the atom, and there are particles that are smaller than these that we'll mention, but we'll talk about the three principal components of the atom. They will vary in their location and their electrical charge. The first one, protons, these have a positive charge. So P for proton, P for positive. Neutrons have a neutral or no charge. So N for neutral, N for neutron. And the third one, the electron, these have a negative charge. And you'll see on the images over here, charges that are similar will repel each other, and charges that are different will attract each other. Just like if you play with magnets, if you put two of the same pole next to each other, they repel each other. They cannot stick together. There's no way you can force them to stick together. But if you have opposite poles on a magnet, they combine and they attract each other. It's the same thing here. So two positive charges will repel each other the same way as two negative charges would. So like signs repel, and opposites attract. So positive, negative, negative, positive. Alright, the structure of the atom. The atom is made up of a nucleus, which is the key center point of the atom. This is where you'll find the protons and the neutrons of an element. It has most of the mass of the atom will be found in the nucleus. And the third particle we talked about, the electrons, actually orbit the nucleus, kind of like the planets orbit the sun, in various shells or various orbitals. And for the most part, that area is a lot of empty space. Alright, so starting with a sample of lithium metal here, zooming in on these little individual circles, these individual lithium atoms. So zooming in even closer, going into the one atom here, and the nucleus would be here. These would be electrons orbiting around here, swirling around. Then the size of the nucleus of a lithium atom is approximately 10 to the negative 15 meters. So an incredibly small amount of space. And again, when you're talking about one atom, the high majority of the space occupied by an atom is done by the nucleus, where you find protons and neutrons. Alright, now we'll move on to how to read various characteristics of the periodic table and with any given element. When you zoom in on the periodic table, you'll see these individual squares, and within these squares you'll see the element's symbol, and you'll see some various numbers, and we'll talk about what all those numbers mean. The first one is it's called the atomic number. This is always going to be a whole number. It's going to be specific for that element. So these are put in sequential order. 1, 2, 3, 4, going all the way up to 118. They're always going to be whole numbers. And this atomic number represents the number of protons and electrons in an atom. And it usually will appear just above the symbol for the element. So for the example that's given here, Na, the symbol for sodium, its atomic number is 11. So that means right away, just by looking at this individual square, of the three particles that we talked about, you know right now how many protons there are and how many electrons there are in a neutral sodium atom. There'll be 11. Right, for neutral atoms, the net charge will be 0. So that means the number of positively charged protons equals the number of negatively charged electrons. They cancel each other out. So some atoms are neutral, and then some are going to be more reactive and they want to lose or gain electrons. And when that happens, their charges will change. And we will talk about that in a future chapter. So the example that's given here, aluminum, its atomic number is 13. So that means it has 13 protons, which are positive, and 13 electrons, which are negative. So they cancel each other out. A net charge of 0. All right, the mass number, or the atomic mass units, AMU, this represents the number of particles within the nucleus of an element. Now this is equal to the number of protons plus the number of neutrons. This is always going to be a whole number. You can't have a third of a particle or a tenth of a particle. This is always going to be represented by a whole number. And this is a number that does not appear on a periodic table. This is used for calculations for other formulas, but it does not appear on the periodic table along with the chemical symbol. All right, now we'll talk about isotopes. Isotopes are atoms of the same element, but they have different mass numbers. And the reason why they have a different mass number is their mass is different because there are a different number of neutrons in that version of the element. An isotope is really just a different version of that element. Most elements can be or can exist in more than one form. And a way to recognize if an element is an isotope or not is the way that it is written. The example that's given here is magnesium. The normal way you would write or you would represent magnesium is just the symbol Mg. But when you see the symbol here, along with the mass number and the atomic number, along with that symbol, that means that it's an isotope. The atomic symbols being able to determine subatomic particles. We've already talked about how to find two of the three subatomic particles, the protons and electrons. That's given by the atomic number. To find the number of neutrons, what you do is you subtract the atomic number from the mass number. And here are some examples. Let's go down here to zinc. Chemical symbol is Zn, zinc. Mass 65, and the atomic number is 30. This number here, 30, represents protons and electrons. The mass is 65. So 65 minus 30 gives you 35 neutrons. And this is the same process done for any element on the periodic table, regardless if you have heard of it or not. The atomic number always represents protons and electrons. And to find neutrons, you subtract that number from the atomic mass and then round to a whole number, because you cannot have a tenth of a neutron or a fifth of a neutron. So same thing here for phosphorus. Atomic number 15. So 15 protons and electrons, even though it's not listed on the table here. The mass is 31. So 31 minus that 15 will give you 16 neutrons. Sometimes there's only a very small number difference, 1 to 2. Sometimes there's a very big difference between neutrons and the other particles. Alright, ways to calculate atomic mass. If you look at the periodic table, you will see usually the chemical symbol, like for here, chlorine, Cl. The atomic number on top, 17. And you also see a number below the atomic symbol. And it's almost always a number with a decimal in it. So for this example, 35.45. And this represents the average weight of all the naturally occurring isotopes of that element. So for chlorine, it is found naturally to exist in two forms. Either with a mass of 35, here, or a mass of 37. It is still chlorine, that's why the atomic number doesn't change. They're both 17. So it's still chlorine, but the masses are different. So that's why they're isotopes. So there's a way to calculate the average mass, which is what this number represents. So for the example here for chlorine, 75%, or just over 75%, of all the naturally occurring chlorine has a mass of 35. The other 24% has a mass of 37. So when you average this out mathematically, you get the average atomic mass of 35.45 atomic mass units, which is how we get this value here. Alright, to calculate atomic mass, what you'll do is you will multiply the mass of that isotope by its percentage, how abundant it is, and then you will do that for every single isotope. Then you will add up all those numbers together to get the average atomic mass. Alright, this table here shows the three different naturally occurring isotopes of magnesium. Magnesium 24, 25, and 26. And the masses of those isotopes. So the mass for magnesium 24 is 23.99. Officially 24.99, 25.98. The most abundant, the most commonly occurring of these three isotopes is this one here, magnesium 24. That is found 78.7% of the time. All right, so what you'll do is you'll take the percentages that you're given, turn that into a decimal number. So this becomes the 0.7870. That value multiplied by the mass that you're given, that will give you 18.88 atomic mass units for that isotope, for that version of magnesium. You do the same thing for all the other known isotopes. Magnesium 25 is found 10.13% of the time. That converted into a decimal number multiplied by the mass, you get 2.531 atomic mass units. And this last version here for magnesium 26, which occurs just over 11% of the time, 11.17. Convert that into a decimal. That value times 25.98, its mass, gives you 2.902. Adding up all of these three together, 18.88 plus 2.531 plus 2.902 gives you the atomic mass unit for magnesium, which would be 24.31, which is the value that you will see on the periodic table under magnesium. And it's the same process for any other element with any number of isotopes. How abundant it is multiplied by its mass, and you add up all those atomic mass units for every single isotope that's known. Alright, next we'll move on to electromagnetic radiation. Now we experience electromagnetic radiation every day, all the time, in various forms. X-rays at a doctor's office, seeing the colors of a rainbow, seeing light, talking on your cell phone. Those are all examples of electromagnetic radiation. Now this radiation will consist of energy particles that move as waves of energy. So think of a wave going up, then going back down. There's the top part, which is the crest or the peak, then it dips down into a trough. So the distance between these peaks of these waves, think of waves occurring at an ocean, the distance between those tops of those waves is called the wavelength. Radiation that has high energy will have much shorter wavelengths, and radiation that has low energy has much longer wavelengths. So if you were to think of a wave going like this, right there is the peak here. And then down here will be the trough as it dips down. And distance between here and here will be the wavelength. Radiation that has higher energy will have much shorter wavelengths. These will be much closer together. Radiation that has low energy, these will be much further apart. So it may look like this. That would be low energy, and this would be high energy. Okay, now we'll move on to the atomic spectrum. When light from a heated element passes through a prism, it will separate into distinct colors of the rainbow. Any light going through a prism will separate into the standard rainbow colors. But whenever you do that with an element, you'll get a very distinct pattern that's unique for that element. So the example that's given here, if you were to heat up barium in a heated element, that light going through a prism will split up into this pattern. This is unique for barium. If you were to do this with calcium, you would get something different. Or potassium, you would get something different. Every element has a very unique atomic spectrum like this. Alright, here's the full range of the electromagnetic spectrum. Starting off here, very low energy. Here. And then getting higher and higher and higher to high energy. Now the part of this whole spectrum that we can see, visible light, is a very, very, very small piece of the spectrum, going from here to here. Now the color's red, about 700 nanometers. That's going to be on the lower end of the visible light. Then the various colors of the rainbow. And up here you get violet at around 400 nanometers. That's why anything below red is infrared. Anything that's above violet is ultraviolet. So some examples here of infrared light, from heating lamp, satellite, microwaves, cell phones, TV, and so on. And things that are ultraviolet, just beyond violet. These are getting higher and higher in energy, which means more dangerous to deal with. X-rays, gamma rays, and so on. That's why when you're getting an X-ray, the part of you that's not being X-rayed, you need to have a shield of lead in front of that, otherwise it can damage tissue. And again, this whole spectrum, which covers quite a lot, the only part that's visible to us is this small window of the rainbow colors, from 700 nanometers to 400 nanometers. Now we'll move on to electrons and energy levels. Now electrons, like we mentioned before, exist in different shells or different orbitals that spin around the nucleus. Electrons with the same amount of energy are grouped in the same energy level. And energy levels are given what are called principal quantum numbers, or the N number. So N1 is the lowest, then the next higher level will be N2, N3, 4, and so on. So think of them as like this picture indicates, like a bookshelf. The lowest level, or N1, then the level just above that, we have a little bit more energy, N2, and more energy, you have N3, N4, N5, and so on. An electron can only exist in one level at a time. Now when electrons move up or move down energy levels, energy will either be absorbed or emitted. So an electron will go to a higher energy level when they have absorbed enough energy to push them up to the next level. So if you have an electron here, and it collects and absorbs a whole bunch of energy, it gets bumped up from, say, N1 to N2, or 2 to 3, and so on. If you move up to more than one level at a time, that means the electron has absorbed a lot of energy. So it will go from, say, here all the way up to here, and then the opposite of this will be true. If an electron goes down in energy level, let's say from N3 to N2, as it falls back down, it will emit energy that's equal to the difference between those two levels. So energy is never gained or lost, it's always there somewhere. If it gets absorbed, it pushes the electron up to a new level. If the electron falls down in energy level, the energy that is the difference between those two levels gets emitted as light. Now it is the arrangement of these electrons that helps determine chemical and physical properties of any given element. And each energy level, N1, 2, 3, 4, 5, and so on, has one or more sublevels. And the number of these sublevels within an energy level is equal to the quantum number of that level. And the sublevels are identified by these letters S, P, D, and F. And these are the order that they go in. So S would be the lowest sublevel. Then a little bit more energy, you get P. After P, you get D. After D, you get F. A quick resource to summarize the energy level with the principal number of sublevels and how they're written. And we'll talk about what these boxes represent here in a second. So the lowest energy level, N1, has one sublevel because it's N1. So it'll have one box in the S sublevel. Quantum number 2, because it's a number 2, it has two sublevels, S and P. Energy level number 3, you have three sublevels, S, P, and D. And for 4, you have four sublevels, S, P, D, F. And these individual boxes have a very particular meaning, which we'll talk about here soon. Now the location of where an electron is, to what sublevel it's in, really is determined by probability. An electron can't exist in, as far as we know, can't exist in two different places at the same time. So you are predicting where it was or where it will be. Now we'll first start talking about the lowest energy levels, the S sublevels. These are three-dimensional volumes where electrons have the highest probability of being found because it's the lowest energy level. And when you're talking about these on paper, they're usually indicated by three-dimensional spheres like this, because electrons can move in three different dimensions. So think of it as like a baseball or a tennis ball, because the electron could be swimming around anywhere in there. All right, the P suborbital levels. There are three of those, starting with the n number of 2. Each p orbital has two lobes. Think of it as a long, skinny balloon that's kind of pinched off in the middle. So you have two oblong sections that are joined together. And each of these lobes can hold 2 electrons at the most. And the three p orbitals are arranged perpendicular to each other on an x, y, and z axis around the nucleus. And in what direction an electron spins, either counterclockwise or clockwise, will give it different properties as well. Images of how a p orbital would look: a long, skinny, in this case, green balloon that's kind of pinched off in the middle. Same thing here, same thing here. And then we have the combined p orbitals that look kind of like this, all perpendicular to one another. This image is a combination of these three together. The next one, the d orbitals. Each of these d sublevels have 5 d orbitals. For the most part, they have a fairly consistent arrangement, except for this last one. The first 4 of these 5 are aligned with each other, very similar to the p orbitals. But this last one has a circular orbital, looks kind of like a donut that encloses the other orbital here. So all of these indicate the d suborbital level. In this table, you have the electron capacity for these energy levels going from 1 to 4. Now starting off here in the bottom, the lowest energy level of N1 that has one sublevel. That's indicated by writing 1s, because there's one suborbital level in the S range. For N level 2, that means 2 sublevels. So you're going to write 2s and then 2p also. This one the S's can only hold 1, P's can hold up to 3. N level of 3, that means you have 3 sublevels. That's why these numbers are the same as the quantum number. So these numbers are the same as this. So 3s, and then 3p, and 3d. It's always in the same sequential order. It's always S, then always P as in Paul, then D as in David, and then F. Again, S can only hold 1, P can hold up to 3, and then D holds up to 5. And lastly, for number 4, again, the numbers are all the same. 4S, 4P, 4D, 4F. And each of these contain a set number of electrons, and that's very important because where these electrons are in these suborbital levels will determine if they are lost or if they're gained, or do they move down levels or do they move up levels to make a element more stable. So these orbitals have very consistent, very predictable patterns. And the first one can only hold 2. Then the next level can only hold 8. Then it goes up to 18, then up to 32. These electron configurations follow the order of occupied sublevels on the periodic table. Again, by looking at the table, just by knowing some basic facts about chemistry and knowing what to look for, you can tell a lot of characteristics of any element just by where it's placed on that table. So all these in the S block here, we'll have all just 1. Then the D block here, P, and then F. Now what's used to indicate these electrons and where they're placed in what orbital level is what's called an orbital diagram. Now these orbitals will be filled based on energy level, going from the lowest to the highest. The lowest energy levels are always filled up first, and then when those energy levels are filled up, then you move on to the next level. So in this example here, each arrow indicates 1 electron. And remember here, S's are the lowest kind. So the S's will be filled up first before anything gets put in the P level. After the P's are filled up, then you move on to the next one. So you're not going to go some here, and then some here, some here. The lowest energy levels are always completely filled first before you can move on to the next. Now chemists will use a particular type of notation called electron configuration to not only indicate the placement of electrons in the atom, but to show how electrons fill various energy levels and sublevels. And there's an abbreviated form using a particular noble gas to represent all the electrons preceding it. That's a shorthand way to write an agreed upon setting for all these configurations. So for an example, the electron configuration for carbon, when you write it out using this type of setup, and we'll go over an example of one here in a second also. Carbon, it'd be written just like this, and this is how it's read. 1s2, 2s2, 2p2. And here's what those numbers mean. 1, or the very first suborbital level, 1s, and there are 2 electrons there, so that means it's full. The next level will be 2, 2s, and it has 2 electrons, so that's full. Then after that you go up to the next level, which are p's, 2p, and 2 electrons in there. And here's how you would write some other common elements. Helium, H, that number only 1. So it's only going to be 1 electron. So you only fill in just half of the very first box. So that'd be written as just 1s, 1, because there's only 1 electron in this box. For helium, top number 2, the lowest box is full, so it's going to be 1s, 2, because there are 2 here. Alright, here are some other common ones. On period number 2, from lithium down to neon, the way it's the element and the atomic number, the orbital diagram, note the boxes, the electron configuration here, and also how it is abbreviated, an abbreviated electron configuration. And here's what that means. For this last column, you'll see helium in brackets and plus whatever's left over, because this is the same thing as this, 1s2. So you could also write this as 1s2 and then the rest. Instead of writing all of that, you just write helium in brackets. So that's a shorthand way to write 1s2. That's why it appears in all of these. So it's not mandatory you write it that way, but it's an abbreviated form to write the electron configuration. Alright, we talked about carbon previously, topic number 6, and how these 2 are full, these 2 are full, and these are not. And the name that we get, 1s2, 2s2, 2p2. And this is how we get to these arrows getting placed where they are. Alright, what we have here are the orbital diagrams for carbon. And I've already written out here 1s2, 2s2. All 3 of these are 2p2. And like I mentioned, when you're filling out these boxes, filling out these orbitals, you always want to fill out the lowest energy levels first. So for this one, for carbon, we have one arrow here, one arrow here. You want to fill that box up first because it's the first level, it's 1. Then 2. That would be full. That would be full. So there's 2 here, 2 here. Alright, carbon will have 6 electrons. So right now we have 4. We have 2 in here. We have 2 in here. So now we start to fill out these. 1 there, 1 there. You would not put it here. You would go here, this box next, and then fill the rest back in. So that's how we get 2, 2, 2. That's how we get to our 6 electrons for carbon. That, what I just drew by hand, is the same thing as this, just nowhere near as neat. 1s2, 2s2, 2p2, because there's only 2 here. If you look at the difference between carbon and nitrogen, this one is filled up here, or this box on the end does have an electron here, but not here. That's why nitrogen is almost the same thing, but it's 2p3, because there are 3 here. Again, the key for all this, when you're writing an orbital diagram, you fill out S level first, and then go on to P. After P, then you fill in D. After D, then you go to F. The lower levels are always filled up first before you even move on to the next. All right, for representative elements in groups 1 to 18, chemical properties are due to the what are called the valence electrons. Valence electrons are the electrons on the outermost energy level for that element. These are how elements combine with each other. Some electrons are going to be lost to make that element more stable. Some electrons will be gained to make that element more stable. And the group number that the element is in gives you the number of valence electrons for that element. Just knowing what the group number is can tell you right away about having to draw the orbital diagrams how many electrons there would be in the outermost shell and how many they are able to be lost or to be gained. For an element to lose one of its outermost electrons, that takes a certain type of energy. And that energy is called ionization energy. The energy needed to form an ion. An ion is an element that has a charge to it. So it's the energy needed to basically rip away the outermost electron and therefore leaving an ion behind. So the example that's given here, sodium plus the ionization energy will give you the sodium ion, Na+, and the negatively charged electron. This is the same thing as this, but written in orbital diagram. This right here is all for sodium. And what the ionization energy would be is the energy it would take to rip away this electron here. That's why in the product part of the equation here, this box is now empty. And the arrow is here on the outside. So that's all the ionization energy is. The energy that's required to form the ion. And by doing so, pulling away the valence electron or electron. Now as the distance from the nucleus to the valence electrons goes higher, the ionization energy will go down. It takes less and less energy to pull something that's further away from the nucleus. If it's really, really close to the nucleus, it's going to take a lot of energy to pull it away. And this ionization energy will be low for metals, but high for the non-metal. Alright, here's a quick way to just look at the periodic table and to get an idea of what ionization energy would be needed. The energy will decrease when you go down a group and increase as you go across, going from left to right. So a generic image of the periodic table here. When you go down, the ionization energy will get less and less. So something down here would not take as much ionization energy than something up here would. Also, as you go from left to right, going this way, the amount of energy will increase. So something that's, say, in this corner here, where the cursor is, will take a high amount of ionization energy compared to something down here. So going down, the energy needed decreases, and going to the right, the energy increases. And here's another way to think about it. We have 3 examples given here: lithium, sodium, and potassium. Now, of these 3, lithium is smaller, or the smallest of the 3. And sodium is a little bit bigger, and then potassium is a little bit bigger than that. So the distance between the nucleus and its outermost shell is really small here, a little bit bigger here, and a little bit bigger here. The energy you would need to take away this electron would be less than here and less than here. This is really, really close to the nucleus. So pulling away this lithium electron would take a lot more energy than it would compared to potassium, because that's further away. Not that much, a little bit more, a lot more. All due to its distance between the electron and the nucleus. Closer it is, more energy you need. Alright, an element with a metallic character is one that loses a valence electron fairly easily. And these are going to be more found or more prevalent in metals on the left-hand side of the table. It's less for non-metals on the right-hand side because they don't lose electrons all that easily. And this character will decrease going down a group as electrons are further away from the nucleus. So again, given a generic image of the periodic table, as you go down the table, the character will increase. As you go to the right, the metallic character will decrease. And the reason why that is, and it's something that we'll discuss further in a future chapter, the elements that are on this hand side of the table, especially column 1 and column 2, are really, really reactive. They are very willing to give up that valence electron. They are much more stable when they lose that 1 or 2 on the outermost shell. They want to get rid of them as quickly as they can. And the opposite is true over here. See in column number 17, fluorine, iodine, chlorine, all those. They are much more stable to gain an electron. They don't want to lose the ones on their outermost shell, because for them to become more stable, it's easier to gain one than it will be to lose the ones that they currently have. So that's why the elements on this side of the table much more eager to lose their valence electrons, because by doing so they become much more stable. Okay, in this chapter we'll talk about natural radioactivity, different forms of radioactive decay, the applications of using radioactive tools in research. Radioactivity comes from unstable nuclei, which are found in elements with atomic numbers 20 or higher. Radioactivity is defined by, in nuclei, the nucleus can't keep itself intact anymore, and the forces of repulsion outweigh the attractive forces. So these nuclei will emit particles of energy, small particles of energy. This is called radiation. And this is done so to become more stable. Now radiation will take the form of different types of particles, alpha, beta, positrons, or pure energy such as gamma rays. And you see these symbols here, alpha, here, then beta, and then positron, same symbol as beta but with a plus sign. And then gamma rays, looks like a lowercase y. Those are the Greek letters. Right, a radioisotope, this is an isotope, something we've already talked about in previous chapters. Isotope of an element that emits radiation. And there can be one or more isotopes of an element. And the radioisotope will include the mass number in its name. That's a way to indicate if something is a radioisotope or not. Alright, the example that's given is iodine. Normally the way to represent iodines with a capital I is atomic number is 53, but its regular atomic mass is 127. So if you were to name an isotope of iodine, you would include the mass number in its name. There are many forms of, or many different types of isotopes of iodine, but a very commonly used one is iodine 131. This is a radioisotope that's used to help diagnose and treat thyroid disorders. Though it still has the atomic number 53, it's still iodine, but the mass is different because it is an isotope of iodine. It's a radioisotope. That's why it's indicated by calling it iodine 131 and not just iodine. Here's a table of some stable and some radioactive isotopes. For stable here, magnesium 24 or iodine 127. Some radioactive forms, magnesium 23, magnesium 27. These are still forms of magnesium, but they have different masses, so they're isotopes, and because they emit radiation, they're radioactive isotopes. And for iodine, normal form is 127, but 125 is an isotope, and iodine 131 is an isotope, a radioactive isotope. And then uranium 238. And 235, different forms of uranium. There are different types of radiation depending on what kind of particle is being emitted. We talked about alpha, beta, positrons, and gamma rays. The alpha particles, these are identical to a helium nucleus. That's why this is here. The symbol for helium, He, atomic number 2, and the mass is 4. These values will be important later on in this chapter. Beta particles, these are high energy electrons, or these emit high energy electrons. This is how that's indicated. E for electrons, -1. Positrons, that's a same thing as beta, but positive form. And then the gamma rays, the symbol for gamma, and the zeros for here and here. Here's a summary of the different forms of radiation, and their symbol, and then how they're written, and then how it changes the nucleus, and how it will change the charge of the element. For example, the alpha particle, of course, the symbol, again, identical to a nucleus of helium. And you'll have 2 protons and 2 neutrons are emitted as the alpha particle, and it will change the mass number of the element and also change the atomic number also. And same goes on for beta particles or positrons or gamma rays. This table is really just this information but in a table form. Alright, nuclear reactions. In a nuclear equation for alpha particle decay, the mass number will go down by 4 and the atomic number will go down by 2. And these numbers are not random. Remember we talked about the alpha particle is identical to a helium nucleus. So that's why when you look over here, if you're looking at a radioactive uranium nucleus, when that breaks down and starts to emit radiation, what it emits is something that's identical to a nucleus of helium. So again, when you're looking at these notations, the symbols here, atomic number here, atomic mass is here. Well, when you lose energy and lose mass, it doesn't just vanish. There has to be a conservation of both of those components. So what you're doing is you're changing the element that you started off with. The atomic mass totals don't change before or after, and the atomic number totals won't change before or after the decay. That's what this image is showing, and that goes back to the learning goal for this part of the chapter, being able to write a balanced nuclear equation showing the mass numbers and the atomic numbers for a radioactive decay. And that's what this image is showing. Starting off with uranium, the radioactive uranium nucleus, atomic number is 92, the mass 238. When that breaks down, it will, because it's alpha decay, it will release something that has atomic number of 2 and a mass of 4. Well, that's going to change these two numbers here. That will go down by 4. So now instead of having 238, you have 234. And the atomic number will go down by 2. So instead of being 92, you have 90. Well, when you change the atomic number, that changes the element completely. So now you have thorium, which matches the atomic number of 90, and the mass will be 234. So when radioactive uranium breaks down with alpha radiation, what it emits is an alpha particle, and the result is also thorium with a mass of 234. But the totals don't change. If you add this mass and that mass, you get what you started off with, 238. If you add this atomic number, 2, and that atomic number, 90, you get 92, what you started off with. These masses and these energies don't just vanish. They have to be the same before the decay and then also after the decay. So in a radioactive decay, the nucleus will break down when it emits radiation. And we're just talking about alpha decay in this example for the uranium and the one that's on this slide. There are other forms of decay, beta, positrons, gamma rays. Those all affect the radioisotope differently. But right now we're just talking about alpha. So for example, this element here, CF, is californium. The atomic number is 98. Its mass is 251. When that breaks down with alpha decay, the atomic number will go down by 2. So that gives you 96. And the mass will go down by 4. 251 goes down by 4 to 247. Alright, so this number going down to 96 completely changes the element. You don't have californium anymore. You have the element Cm, or curium. And its mass is now 247. And of course you get the helium nucleus also emitted with alpha decay. Again, before the decay started, you had a mass total of 251. You have that still after the decay. 247 plus this 4 of helium gives you the 251. Same process for the atomic number. You started off with 98 before the decay started, and afterwards 96 of the curium plus the 2 from helium also gives you 98. So these totals should be balanced before and after the breakdown. When the nuclei of either alpha or beta or positron or gamma emitters propel their radiation out, what's produced is a new and more stable nuclei. That's the whole point of emitting radiation, is to become much more stable. That's what's indicated here in all 4 of these images. An alpha emitter will give you helium nucleus, which will give you a new element. Mass number goes down 4, atomic number goes down 2. With beta, what you'll get is a new element. The mass number doesn't change, but the atomic number goes up 1. If you have a positron emitter, you get a new element. The mass number stays the same, but the atomic number goes down 1. And for the gamma emitter, you get a stable nucleus of the same element, and neither the mass number or atomic number change. So depending on what type of radiation you're talking about will determine what happens to that mass number, what happens to the atomic number, and whether or not a new element is formed. Producing radioactive isotopes. Radioactive isotopes are produced when you have a stable nucleus that's converted to a radioactive nucleus by just bombarding it, just peppering it with a small particle. And that whole process is called transmutation. So if you were to take a stable nucleus here of boron, atomic number 5, mass of 10, and just bombard it with helium particles, so when you add these two together, this process of transmutation, you get a new nucleus, a new radioactive nucleus of nitrogen, atomic number 7, mass 13. You get this nucleus plus a neutron. Again, like we talked about on the previous slides, mass numbers are equal before and after the reaction, and the atomic numbers are equal. 13 plus 1 gives you the same number as 10 plus 4, 14. 7 plus 0 will give you a total of 7 on this side. 5 plus 2, 7. So nothing is lost in this process of transmutation. So you are really just converting something that is stable into something that's radioactive and new. Right, a Geiger counter. This is a very commonly used instrument that helps to detect forms of radiation, mainly beta and gamma radiation. The way this works is it uses ions produced by the radiation that create an electrical current. If you've ever seen or heard a Geiger counter being used, it makes that distinct clicking noise. The more clicks that it makes means more radiation is present. Alright, next topic is half-life. The half-life of an isotope, or radioisotope, is the time that it takes for 1/2 of the original value to decay. And this will vary greatly on individual radioisotopes. Some are relatively short, some are in the thousands of years. It just depends. An example is given here, the radioactive iodine we talked about earlier. So after one half-life of iodine-131, you'll get half the sample of iodine, but also you'll get new element produced, xenon. After another half-life, you're getting less and less of iodine and more xenon. And the way to represent this on the graph is called a decay curve. For the iodine-131, its half-life is 8 days. So after 8 individual days, half of your original sample will be gone. So let's say you're starting off with a total of 20 milligrams of iodine-131. After 8 days, you'll be down to 10 milligrams of iodine-131. After 8 more days after this point, you have half of this sample. So instead of having 10 milligrams, you have 5 milligrams. After another half-life, instead of having 5, you'll have 2.5. And so on, and so on, and so on. And you can never get to 0. You can't divide a number in half and end up getting a number of 0. You'll just get smaller and smaller and smaller. Now this table has some half-lives of some common radioisotopes. Probably the most common known one is carbon-14. This is used to date fossils. When you hear the term carbon dating, that's usually what they are referencing, carbon-14 dating. Its half-life is 5,730 years. And the type of radiation it emits is a beta radiation. Now, some of these are really, really short, such as technetium is only 6 hours for half-life. Radon-222 is 3.8 days. Some are only minutes long. Carbon-11, half-life is only 20 minutes long. Radium-226, 1,600 years. And then potassium-40, 1.3 times 10 to the 9 years. Yeah, so that value would be 1,300,000,000 years. So as you can see, various elements have a great variety of half-lives. Alright, some medical applications using radioactivity. Scanners are going to be used to detect radiation from radioisotopes that are given to patients that can accumulate in an organ or in various types of tissue. A very common example is one we mentioned earlier in this chapter, using iodine-131 to detect issues with the thyroid. And that's what you're seeing here. This patient is being scanned for radioactive iodine-131, and it will show up in various spots within the thyroid gland. Now, radioisotopes that have a short half-life will be used in nuclear medicine because the cells in the body don't differentiate between the radioactive forms of an atom and the non-radioactive forms. And also, once these are incorporated into the cells of the body, the radioactive forms are easily detected because they emit radiation, and normal cells do not emit radiation. So that's what's going on in this image here. The iodine-131 will show up as opposed to, say, regular iodine because it's not radioactive. A tool that can be used using radioactive isotopes is the PET scan. PET scan, positron emission tomography. It will detect positron radiation. Positron emitters with very short half-lives are used to study brain function, body metabolism, and blood flow. And some examples that could be used, carbon-11, oxygen-15, nitrogen-13, fluorine-18. These all will combine with electrons after emission to produce gamma rays, which are detected by the various scanners that your doctor uses. This will help to create a 3D image of the organ. Here's a good example of use of a PET scan. These are scanned images of a brain. The brain on the left, normal functioning brain, and the one here on the right is a brain affected with Alzheimer's. And you can see just by looking at these different colors how a normal brain is much more of a blue area here, and it's much more diminished here because that tissue has already started to decay away. So this is a very commonly used tool to help diagnose Alzheimer's disease. Another commonly used tool with radioisotopes, a CAT scan or CT scan, computed tomography. This is used to help scan organs such as the brain and the lungs and the heart. And you have a computer that will monitor the absorption of 30,000 X-ray beams directed at the brain or at the organ in successive layers. And the differences in these absorption levels are based on tissue densities and fluids. So the example that's given here, someone's brain and skull. Solid yellow mass is a brain tumor. And something like this will not show up on an X-ray or not show up all that well because this is living tissue, and you need to be able to detect how well does that tissue absorb or reflect back radiation. So all this other material is going to be regular brain tissue. Right here, which should be similar to this, around it is a solid mass. It's like the outer part of the skull is solid. So that's not a good sign at all. Another tool that's used, MRI, magnetic resonance imaging. This is an imaging technique that does not use X-ray radiation. It's probably the least invasive form of imaging that's available. It's based on the absorption of energy when protons and hydrogen atoms are excited by being induced in a strong magnetic field. And the way this works is the energy that is absorbed is converted to color images of the body. So here's a sample. This is an MRI of the heart and lungs of this patient. And again, the different colors will indicate the different amounts of energy that are absorbed. Okay, in this chapter, chapter number 6, we will talk about ions and the transfer of electrons. Now, atoms can form positively charged ions when they lose electrons, and they become more negative when they gain electrons. Now, at first that may seem counterintuitive. You would normally think that if you gain something, that's good, or if you lose something, that's bad. But think of what is being gained or lost. Electrons have a negative charge. So if you get more of those, if you gain more of those, you are becoming more negative. If you lose electrons, if you lose something negative, that's a good thing. That's a positive thing. So it's very common to get that backwards. A type of bond called an ionic bond is formed when a strong attractive force between a positive ion and a negative ion meet. And see the learning goals of chapter number 6, being able to write the symbols for simple ions of the representative elements. An easy way to tell if an element is an ion or not, a positive or negative charge written just above the chemical's element symbol. Right now, we'll talk about ionic and covalent bonds. Now, chemical bonds are formed when atoms will either lose electrons or gain electrons or actually share electrons to form a more stable outermost shell. The rule is called the octet rule. If you remember nothing else from this chapter, know what this rule means, the octet rule. That is what all elements are striving for. That's when they're the most stable. It's also called the rule of 8. So some atoms or some elements are going to be more likely to lose an electron, so they become more stable, or some elements are more likely to gain electrons, so they can become more stable. It just depends what their characteristic is. Two different types of bonds, ionic and covalent. Ionic are formed when electrons are transferred from one atom of nonmetal to another. So basically, one element is stealing away an electron from the other, and by doing so, you are forming two separate ions. Because one element has lost an electron, forming a positively charged ion. One element has gained an electron, making it more negative. And the stronger type of bond, covalent bonds, these are when nonmetal atoms are sharing equally the electrons. So they're not being stolen from one to the other, they're both being used equally. This is a very, very strong type of bond. Alright, here's a representation of both of those types of bonds. M for metal, NM for nonmetal. In this case here, this electron is being stolen to go over here, which makes this more stable, makes that more stable. But by losing an electron, the metal becomes positive, the nonmetal becomes negative, because it gained that electron. That's an ionic bond, a bond between two ions. For sharing electrons between two nonmetals, in order for these to become more stable, the outermost shell of electrons needs to have 8. That's why it's called the octet rule. You want to get as close to 8 as possible. So in order for that to happen, both of these need to gain 1 because they have 7. 1, 2, 3, 4, 5, 6, 7. Same thing over here. 2, 4, 6, 7. For them to become more stable, they need to share an electron. So by doing so, they both have 8. So they're not being stolen from one to the other, they're both being shared equally. That's a covalent bond. That's a very, very strong bond. Alright, first we'll talk about positively charged ions. This is where metals actually lose electrons. Right? Like we mentioned before, in an ionic bond, ions are going to be formed when an atom will either lose or gain a valence electron. And these will have very low ionization energies. They want to become more stable as easily as possible, so the energy needed to form that ion tends to be fairly low. Some elements are going to be much more likely to gain some, become more stable, and some elements will be much more likely to lose an electron and become more stable. And you can tell which one an element will do based on where they are on the periodic table. And the whole point is to become as stable as possible. And for most elements, that is getting to the number 8, because that's what you have in the noble gases, the inert gases, because those are incredibly stable. And all these traits here are characteristic of the metals, the elements in group number 1, and also group number 2, and group number 13. Okay, negatively charged ions, these are where nonmetals gain electrons because you're gaining something that's more negative. These traits will be true for nonmetals and the elements in group number 15, 16, and 17. Because you're gaining an electron, the energy that's going to be needed to form that ion tends to be higher because it takes more energy to steal something away and gain an electron than it would be to lose it. Now these elements in these groups will gain one or more electrons in an effort to become much more stable. And of course the goal is, just like on the previous slide, positively charged ions, to become more or closer to the group of 8 in the outermost shell for electrons, because that represents a noble gas which are very, very stable. Okay, like was mentioned before, based on the group number of where an element is on the periodic table, you'll be able to tell right away what charge an element will have as an ion, just based on where it's placed. See, for example, the elements in group number 1, or 1A, lithium, sodium, potassium, rubidium, cesium, they're in group 1A. That means they have 1 electron in the outermost shell. And again, the key thing for the majority of this chapter is the octet rule, number 8. So they only have 1. It is much, much easier for these elements to lose 1 than to gain 7. So these are going to be very, very eager to lose that 1 in the outermost shell. So when they do so, by losing 1 electron, they become a positively charged ion. And sometimes you may see this as written as +1. You don't have to write the 1, it's understood. Just like in math, x is the same thing as 1x. You don't have to write the 1. Right, moving on to the next column, 2, or 2a. Column number 2, or 2a. They have 2 electrons in the outermost shell. Of course, the goal is to get to 8, or as stable as possible. It is much easier for them to lose the 2 outermost ones than to gain 6. Because when they lose those 2, they become much more stable. The next lowest shell is already full. And that's what all elements want to do. They want to get their outermost valence shell of electrons to be completely full as much as possible. All right, so for those elements that are in column 2, or group 2, magnesium, calcium, strontium, and barium, when they lose their 2 outermost electrons, they become positively charged ions, but their charge is now +2, because they have lost 2. For every electron that you gain or lose, the charge will be changed by 1. So they have lost 2, so they are now positively charged 2. And same pattern for number 3, or group 3, aluminum. They have 3 electrons in the outermost shell. Much easier to lose those 3 than to find and gain 5 more. So when they lose 3 electrons, they become an ion with a charge of +3. Now as you get to the other end of the periodic table, this process switches the other way. For 5a, I say nitrogen and phosphorus. They have 5 electrons in their outermost shell. It is much easier for them to gain 3 than to lose their 5 in order to become more stable. So as they gain 3 electrons, they become negatively charged by 3. So their charge is 3 minus. So for group number 16, or 6a, oxygen and sulfur, they have 6 in their outermost shell. So much easier for that column to gain 2 than to lose 6. So the elements in this column, as they gain 2 electrons, will have a charge of -2, or 2 minus. And then the halogens, 7a, or group 17, they have 7. Much easier to find 1 more than to lose the 7 that they have. so they will gain 1 electron. As they do so, they form a negatively charged ion, and their charge will be -1. And then the noble gases, very, very end, already have their outermost shell filled at the number 8. So they are very stable. They don't lose or gain electrons because there's no point for them to gain or lose electrons. They're already stable like they are. So neon, argon, krypton, xenon, that whole column is fairly inert, fairly stable. So again, just by where an element is on the periodic table, you can tell what its charge would be as an ion. All right, next we'll talk about properties of ionic compounds. Like the name implies, ionic compounds are compounds made of ions, so they're going to have positive and negative ions. The bonds that form them or hold them together will be ionic bonds. Remember, opposites will attract. So the positively charged ion will be attracted by the negatively charged ion. These kind of compounds also have very high melting points, and they're going to be solid at room temperature. So a common example of an ionic compound is sodium chloride, more commonly known as the simple table salt. When you have these two together, sodium is much more likely to lose an electron, and chlorine is much more likely to gain the electron. So when they hook up together, the way you'd write sodium ion Na+, because it's +1, or chloride Cl-. So these are two ions being formed, and that's how you get sodium chloride or common table salt. Now we'll move on to the formulas for compounds. In a chemical formula, the symbols and the subscripts are written in the lowest whole number ratio of the atoms or the ions. The sum of the charges needs to be 0. The number of positive charges will equal the total number of negative charges, so they can balance out. So for the example we just talked about, sodium chloride, the sodium will lose that one outermost electron to fill out chlorine's outermost shell to make that full. So by doing so, the sodium side of this compound has a +1 charge, the chloride side has a -1 charge, so those added together balance out for a net charge of 0. So sodium chloride is a neutral compound. Now we'll move on to naming and writing ionic compounds. Iodized salt contains potassium iodide, written as Ki. This is used to help prevent iodine deficiency. And the learning goal for this portion of Chapter 6, given the formula of an ionic compound, be able to write the correct name and also give the name of an ionic compound and also to write the correct formula. All right, when naming an ionic compound, there are certain rules and certain protocols that you have to follow in order to name them correctly. So for an ionic compound, the name of the metal is always written first, and it's the same name as the element. The name of the nonmetal part of the compound is the first syllable of that nonmetal's name, and the ending "ide." And there is a space between those two words, the nonmetal and the metal part. And we'll go over some examples here. Alright, this table has some very common examples. One we just talked about with the picture of the salt, Ki. K is the metal, that's potassium. The nonmetal ion would be, the element would be iodine, but when you're forming an ionic compound, it becomes iodide. So these two together, when you're reading this as a compound, potassium iodide. So not iodine, I-N-E, but iodide, I-D-E. Magnesium and bromine together. So when you are saying their name as a compound, magnesium, that's the metal, that comes first, and then bromide, Al2O3. The metal part would be aluminum. Non-metal will be oxygen, but you're dropping the ending of the word oxygen and adding the ending "ide." This is the same process for all ionic compounds. Metal first, non-metal second, and the ending will always be "ide," I-D-E. A step-by-step process on how to name ionic compounds. You need to identify the cation and anion. The cation is the positively charged element, so that'd be the metal. So identify which is the metal, which is the non-metal, or which is positive, which is negative. Name the cation or the metal by the element's name. And then for the anion or the negatively charged portion of the compound, you drop its ending and add the suffix IDE, ide. And form those together. The metal goes first, or the positive part goes first, and the negative or the non-metal part goes second. Here's another example. If you're given this formula, K2O, so step 1, identify which is the cation or the anion, or the metal and non-metal. So the cation is going to be the positively charged portion, while potassium is the metal. Where this lies in the periodic table is in group 1. So that, just by knowing where it's placed in the table, will tell you that will be an ion with a positive charge, so that part of the name will come first. So oxygen will be the negative part, so that would be the second part of the name. Alright, because we're forming an ionic compound, the name would not be oxygen. You would drop the ending of oxygen and turn it into oxide. And then step 4, we put all that stuff together. Middle part goes first, potassium, then oxide. Now the transition metals, except for zinc and cadmium and silver, form 2 or more positive ions. So 2 or more cations. Help to distinguish between those is to use a Roman numeral as equal to the ion charge that's in place in parentheses just after the metal's name. So for example, copper can either have a charge of +2 or just +1. So in order to use it correctly or name it correctly, in this example, copper with a charge of +2, you'd write the word copper and then the Roman numeral 2 right after that word. Copper with a charge of this +1, you'd write the word copper and then the Roman numeral 1 just after the name. Iron, another example, could either be +2 or +3. So iron 2, iron 3. Lead can be a +2 or +4. So lead, Roman numeral 2, and then lead, Roman numeral 4. And the last pair of examples, chromium can be 2 or 3 positive. So chromium 2, chromium 3. Now knowing how to use these correctly will help you determine how to write a formula correctly. Because if you don't know what the correct charge is for these transition metals, you won't be able to name or write a correct formula. Alright, here's a quick summary of the last few slides. So all the elements in group 1, for 1A, will form an ion with a positive 1 charge, because they lose that 1 electron. Group 2, or 2A, will lose 2, so they are positively charged 2, so 2 plus. Going over here, group 13, or 3A, these will have a charge of +3. 15, or 5A, will have a charge of -3, because they are more likely to gain 3 than lose their 5. Group 16, or 6A, so their charges as ions will be -2. 17, or 7A, they're only going to gain 1. Their charges are -1. And the transition metals, examples we talked about here, lead, cobalt, nickel, copper, can either be +1, +2. Nickel can be +2 or +3. Iron, 2 or 3. It just depends. That's why you must use the Roman numeral after the name to identify which form of the ion that you're talking about. So again, another step-by-step flowchart to naming an ionic compound with a variable charge with the metal. Step 1 is just the same. Determine what is the positively charged or the cation, what is the negatively charged or the anion. Name the cation by its element's name, and then use the Roman numeral after that name for clarification. Name the anion, dropping the ending of its word, adding the suffix IDE. And step 4, putting all that together. Alright, here's an example. These steps broken down. Let's say you're given the formula FeCl2. Same thing here, FeCl2. And that 2 should be a subscript. You have 2 elements. You have Fe, which is iron, or chlorine, which would be Cl. Now chlorine, because it's in group number 7A, or 17, will gain 1 electron and become more stable. So that is the negatively charged part of this compound. So if this part is going to be negative, then of course this part has to be positive. The positively charged cation would be the iron portion, and the negatively charged anion of the compound would be the chlorine. Okay. In the given formula, you have 2 chlorine ions, so that means that portion of the compound will have a -2 charge. Each chlorine has a -1 charge, and you have 2 of them, indicated by this number. In order for this compound to be neutral, there must be 2 positively charged iron ions to balance it out. 2 positives here for iron will balance out the 2 negatives of the chlorine. So that must mean that you're using iron number 2. And because this is a ionic compound, you would not use chlorine as a name, you would use chloride as the name. So putting all that information together, the formal name for this compound, FeCl2, would be iron 2 chloride. If you leave that portion off, the 2 in parentheses, that makes the name incorrect. You must have the Roman numeral after the name iron to make this specific enough to be correct. Alright, now we'll move on to polyatomic ions. Now poly means more than one, so these are going to be ions that have more than one atom. As an example that's given here first, sodium chlorite, NaClO2. This is used in bleaching of pulp from wood and also used to recycle cardboard. So for this next section of this chapter, we'll talk about how to write the formulas for polyatomic ions and how to name formulas if you are given them. Here are some common examples of polyatomic ions and their names and their formulas. The nonmetal hydrogen, its ion would be hydroxide, or OH minus. For nitrogen, you can have multiple forms of an ion. NH4 plus would be ammonium, NO3 minus, nitrate, NO2 minus, nitrite. And there is a difference between these endings. It's very easy to get those confused, so make sure that you are being very careful when it comes to these names. Some other common examples of the carbon. An ion could be CO3 with a charge of 2 minus, carbonate, HCO3 negative, or bicarbonate, or hydrogen carbonate, CN with a negative 1 charge, that's cyanide. So these are some very common polyatomic ions in this chart, both with its nonmetal, ion formula, and then also the correct name. Now, names of most of your common polyatomic ions will end in the suffix ate, 8, like sulfate, phosphate, nitrate. And here are their formulas. So SO4 with a charge of 2 minus is sulfate. This has to be the number 4, and the charge has to be negative 2 to be sulfate. If it's anything different, it's a different compound with a different name. Phosphate, PO4 with a charge of negative 3, and nitrate, NO3 with a negative 1 charge. If a related ion has one less oxygen, the ending of the name changes. So instead of being 8, it becomes ite, I-T-E. So instead of being up here, SO4 with a charge of 2 minus, if you lose one of these, SO3 with a charge of 2 minus, that is sulfite, not sulfate. PO3 with a charge of negative 3, phosphite. Up here it's PO4 with a charge of negative 3. NO2 with a negative 1 charge, nitrite. All because you're losing one oxygen. And there are some exceptions to this rule, just like in everything else. The compound CN with a charge of 1, cyanide, and OH charge of negative 1, hydroxide. And lastly, when you add a hydrogen ion, H plus, to the polyatomic ion, you add a positive 1 to its overall charge based on how else the other bonds are formed. Alright, halogens will form 4 polyatomic ions with oxygen, and each of those has a charge of negative 1. So for example, ClO4 with a charge of negative 1, that compound is commonly called perchlorate. If you have ClO3 with a charge of negative 1, that's chlorate. ClO2 with negative 1 charge, chlorite, and ClO with a charge of negative 1, hypochlorite. So those are all examples of the halogen chlorine, the element chlorine, forming a polyatomic ion with oxygen. Depending on how many oxygens are there, will determine the compound's name. Now, writing the compound for a polyatomic ion follows the same process as a simple ionic compound. The charges have to equal 0. So for example, if you are combining the magnesium ion and the nitrate ion, magnesium as an ion has a charge of positive 2. The nitrate has a charge of negative 1. So in order for that to balance and equal a net charge of 0, you need to have 2 of this whole unit, because you have all this has a charge of negative 1. So getting 2 of those will give you a overall charge of negative 2. Those negative 2 charges plus the positive 2 for magnesium balance out. So you need to have 2 of this entire thing here to balance out the positive 2 for magnesium ion. And the way you would write that is this: magnesium, and then this whole unit, NO3, is nitrate, but you want 2 of those. So just this has a negative 1 charge, but you have 2 of those to get negative 2, adding that to the positive 2, net charge of 0. But you must have parentheses around that ion and the subscript on how many that you need of that ion. So we're not talking about just nitrogen or just oxygen. All of this together is nitrate. Alright, some steps when you're naming an ionic compound with polyatomic ions. First, you need to find the positive ion, usually a metal, and then write the name of the polyatomic ion second. So here are some common examples. Na2SO4. The sodium will be the positively charged ion, so that'd be the first part of the name, so it's going to be sodium. SO4, that whole unit that's in this box, is sulfate. So this compound, sodium sulfate. FePO4, iron. Iron would be the positive part of this. The first part of the name would be iron. Phosphate, PO4, it's all of that, not just phosphorus, not just oxygen, but that whole unit together is phosphate. In order for these charges to be equal, you need to have iron with the Roman numeral 3 after it, because PO4, phosphate, has a -3 charge. So this whole thing in the box has -3. So in order for that to balance, you need to have 3 positive charges. So iron 3. And again, if that number isn't there, then the answer is wrong. If you have iron 2, it's wrong. This is the only way to correctly write this formula's name. Iron 3 phosphate. The last one, Al2, and then CO3 in parentheses with the subscript 3. Aluminum would be the metal part of the name, the positively charged ion, so Al2. And the CO3 is carbonate. You need to have 3 of these to balance out with the positive charges of aluminum. So aluminum carbonate. Right, now we'll talk a little bit more about covalent bonds. Now, again, this is formed when 2 or more nonmetals share electrons equally to form a very strong type of bond, covalent bond. And it's done so by sharing the electrons in the outermost shell, the valence electrons. There has to be at least 2 to form a compound. There's no limit on how many that can be in a compound, but you must have at least 2 to form any type of compound. Now, when naming a molecular compound, the first nonmetal in the formula is named by its element's name. Then the second nonmetal is named by using the first syllable of that name, and then the ending IDE. A subscript is used, then that prefix is used in front of its name. So here's some common examples. Mono will mean 1, di means 2, tri means 3, tetra 4, penta 5, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. And it's this process that is used for any type of molecular compound, for any type of compound between 2 or more nonmetal. Some common examples. CO2, the first nonmetal in this example would be carbon. So the first part of the name is carbon. This is oxygen, but because we're forming a compound, we drop off the ending of oxygen, turn it into oxide. And because the number 2 is here, you add di in front of that. So carbon dioxide. Carbon with 2 oxygens there. CO, carbon monoxide, because there's only 1. When there's no subscript, you just assume that the number 1 is there. You don't have to write 1 all the time. See, whenever you have vowels that are right next to each other, like O and O or A and O, you just drop the first vowel, because it would just look really weird and sound really weird. So look for here, CO, you would not have mono, M-O-N-O, and then oxide, O-X-I-D-E, because you have 2 O's right by one another. Same thing here, NO, nitrogen monoxide. You would not have 2 O's right here. So if you have 2 O's together, you drop the first one. If you have an A and an O together, you drop the first one. Right, here's some common formulas and names for molecular compounds. CS2, carbon, that's the first nonmetal in the name. Carbon disulfide, because there's 2. CO2, we just talked about, carbon dioxide. NO, nitrogen oxide. N2O, dinitrogen oxide, there are 2 nitrogens. SO2, sulfur dioxide. SO3, sulfur trioxide, because there are 3 oxygens. And SF6, sulfur hexafluoride. Hexa means 6. Think of hexa like a hexagon, has 6 different sides. Alright, now we'll move on to double and triple bonds. Everything we talked about so far has just been regular single bonds. Now, a double bond will occur when atoms between 2 pairs of electrons. And this is usually formed when there aren't enough electrons to complete the outermost shell. So sometimes these bonds will double up in order to fulfill that outermost shell to make it more stable. And with a triple bond, when atoms share 3 pairs of electrons. And just like with the double bond, usually formed to help make the atom much more stable, and when there aren't enough electrons to go around to make the outermost shell full. Alright, next we'll talk about the polarity of bonds. Now, the difference in electronegativity of the atoms that are bonding together can help you predict the polarity of that bond. So for example, that's given here. Hydrogen. Hydrogen, when it naturally occurs, what's called a diatomic element that has 2 atoms, is always going to be represented by H2, because there are 2 of them here. So in this example, the electrons are shared equally by both of these atoms. So when they're shared equally, the bond will be nonpolar. In this example, hydrogen chloride, but there is a difference in the electronegativity between hydrogen and chloride. So when you look at this compound, the chloride side will be more negatively charged than the hydrogen side, just by comparing the parts of that compound. So not the overall charge, but the region of chlorine is more negative, in the region or the area of the hydrogen would be more positive. Because these electrons are not shared equally, there's going to be a difference of electronegativity. So that bond will be considered to be polar, because there's a difference there. All right, now we'll talk about some different types of covalent bonds. A nonpolar covalent bond. This will occur between nonmetals, and is either going to be equal or very, very close to equaling the sharing of electrons. So there's a very, very small difference in electronegativity. So here are some common examples. Nitrogen is another example of being a diatomic atom. There are two nitrogens whenever it's found naturally. It's like with hydrogen. There's going to be no difference in electronegativity. That's nonpolar covalent. Chlorine and bromide, very, very small difference. That's also going to be nonpolar covalent. And hydrogen and silicon, a very, very small difference also. So because that difference of electronegativity is either very, very small or almost zero, that's considered to be a nonpolar covalent. A different type would be a polar covalent. These occur between nonmetal atoms. In this type, there's an unequal sharing of electrons. So in this example, because you have unequal sharing, there's going to be a moderate difference in electronegativity. So for oxygen and chlorine, only 0.5. That's going to be polar covalent. Chlorine and carbon, 0.5. Oxygen and sulfur, 1. So these are all more than these values. These are very, very small, no more than 0.3 or so. When the difference gets a little bit higher, that's when it becomes a polar covalent bond. Now that polar covalent bond can become more polar as those differences get higher and higher and higher. Now the separation of these charges in a polar bond is called a dipole. Di meaning two, and pole meaning polar ends. So think of this as almost like a bar magnet, where you have two separate ends with totally different charges. So like for a bar magnet, you have a north and a south. So for these kinds of bonds, one part of the compound would be much more negatively charged, the other end would be much more positively charged. And you can indicate this by using some Greek letters and also by using some arrows. Now the lowercase Greek letter delta is used to write or to indicate positive, negative. This example here, the bond between carbon and oxygen. When you have this compound, the oxygen side is more negative compared to the carbon side, which is more positive. Delta with the plus indicate positive, delta with the minus indicate negative. You can also draw these arrows here. The arrow will point to the more negative end of the dipole. Same thing with nitrogen and oxygen. When these two form a bond together, the oxygen side will be much more negative compared to the nitrogen side. So positive for here, negative for here. The arrow going toward the O. And when chlorine and fluorine get together, fluorine side is going to be much more negative, and the chlorine side will be much more positive. The arrow going toward the negative end of the dipole or the fluorine. All right, talk a little bit more about the traits of a ionic bond. These will occur between metals and nonmetals. These are formed when you have a result of an electron transfer, either gaining an electron or losing an electron. And these bonds have a very high electronegativity, 1.8 or higher. Some common examples: chlorine and potassium. That difference is going to be 2.2, so that forms an ionic bond. Nitrogen and sodium, 2.1 difference, ionic. So a big indicator of if a bond is an ionic bond is the high difference in the electronegativity between the two elements. Alright, next section of chapter number 6, the attractive forces in compounds. So the shape of a protein can be twisted and bent based on how amino acids and various other side chains interact with one another and how they're attracted to one another. So this will help a protein form a three-dimensional shape. If a protein's its shape helps to determine its function. Learning goal for this portion of chapter 6, describe the attractive forces between ions, nonpolar covalent molecules, and also polar covalent molecules. Alright, for covalent compounds and polar molecules, these have attractive forces called dipole-dipole attractions. Because you have attractions between ions that are dipoles. You also have very strong dipole attractions called hydrogen bonds between hydrogen ions that are bonded to either fluorine or oxygen or nitrogen. The hydrogen bonds are the strongest force between molecules and play a very major role in the shaping of DNA. DNA has a very helical or a spiral staircase shape to it, and the reason why you get that shape is due to hydrogen bonding between amino acids and the side chains within the DNA. So here's some examples. Hydrogen chloride, nitrogen chloride. The bond between the hydrogen here and the chloride here is a dipole-dipole attraction because you have an attraction between two dipoles. Positive end here is attracted to the negative end here. Because remember, opposite charges attract. That's how they're able to combine together. For here, the hydrogen end here, and then the nitrogen end here. The positive part of the dipole attracted to the negative end of the dipole here. That's a hydrogen bond. Alright, dispersion forces. These will be very weak attractions between non-polar molecules. And these are caused by what are called temporary dipoles that will develop when molecules bump into one another. But they don't last that long, so that's why they're considered to be temporary. And these forces are going to be weak, but it's also what makes it possible for nonpolar molecules to form solids and liquids. So with this example here, this nucleus and electrons floating around here and this atom are equally distributed. One on that side, one on that side, one on that side. Over here for this atom, they are not equally distributed. The nucleus at different locations, the electrons aren't equally distributed. Or if these two were to bump into one another, you have the negatively charged end over here being attracted to the positive charge end over here. This is a temporary dipole, so a temporary weak attraction. Alright, next we'll move on to melting points and attractive forces. The melting point of a compound is related to the overall strength of the attractive forces between molecules of the compounds. The higher the melting point, the more energy, the more heat would be needed to break those apart to melt that compound. And these are going to be lower due to weak forces, such as dispersion forces. So if the attractive forces between the atoms are relatively weak, it won't take that much to melt that sample. So that melting point will be fairly low. And melting points will be higher if you'll have the stronger types of attractive forces, such as hydrogen bonding. The highest melting points are going to be found in ionic compounds due to the strong attractive forces between the ions within that compound. Here are some common examples. First two here, ionic bonds. Magnesium fluoride, melting point 1,248 degrees Celsius. Sodium chloride, basic table salt, 801 degrees Celsius. A compound has a hydrogen bond like water. Melting point is 0 Celsius. And NH3, negative 78 Celsius. So we're getting a lower and lower melting point. Compounds that have a dipole-dipole attraction. Hydrogen bromide, negative 89 degrees Celsius. Hydrogen chloride, negative 115 Celsius. And some examples where the attractive force is only a dispersion force. Chlorine atom, Cl2, negative 101. And fluorine, just F2, negative 220 degrees Celsius. Here's a chart that describes the weakest up to the strongest types of bonding between atoms and between ions. So we'll start with the weakest one here at the bottom. Dispersion forces. These are going to be very temporary, very weak. So the next strongest would be dipole-dipole attractions, where you have attractions between nonmetals. Next strongest would be hydrogen bond. So those are the attractive forces between molecules. The next two, or the top two, will be between atoms or between ions. Covalent, where you have a bond between two nonmetals. And then ionic, where you have two or more ions that are formed. Okay, in this chapter, chapter number 7, we'll talk about chemical changes. Now, a chemical change occurs when a substance is converted into one or more different substances, and they have different chemical properties and different chemical formulas. Now, some of these are easily observed: formation of bubbles, a change in color, a change in odor, production of heat or production of a solid. So anytime you get a new set of chemical properties or a new chemical formula, then you have undergone a chemical change. An example that's given here: a silver fork that's been tarnished. The silver, Ag, is turning a different color because you're adding sulfur to it. And that's why rust has a different color to it. You're actually forming a new compound through a chemical change. The tarnished on silver is a different product that is being produced. It is a chemical change. All right, next we'll focus a lot on the writing of a chemical equation. All chemical equations, no matter how simple they are, no matter how complex they are, all boil down to two main components. You have the reactants, and the products. This stuff here is reacting or combining together to create a product. So no matter how involved these reactions can get, it all boils down to those two main categories. Stuff reacting together to form one or more products. And you'll see that this arrow is here. This arrow means this stuff will yield or give you this product. An example here, carbon plus oxygen. These react together and give you or yield carbon dioxide. That's the product. Alright, to write a chemical equation, that arrow is what will separate the reactants from the products. Everything to the left-hand side of the arrow are reactants. Everything to the right-hand side of the arrow are the products. And if you have multiple of either one, they are separated by a plus sign. One plus another. Sometimes above the arrow, you will see a triangle shape. That is the delta sign. And when you see this with a chemical reaction, that indicates that heat is used in that reaction. So for this example, this reactant plus that reactant combined together with heat added will give you these two products. Now some elements can exist in more than one physical state, solid, liquid, gas. So you have to indicate what form of that element or compound that you're talking about so you can be as clear as possible. So for example, water, H2O. If you see water in an equation, well, that could mean liquid water, it could mean water vapor, the gas form, or it could mean solid ice, the solid form. So you need to indicate those physical states just behind the compound you're talking about. So to indicate solid, you would put S in parentheses, liquid, lowercase l in parentheses, gas, lowercase g, or aqueous, which means being dissolved in water. And there's a good summary of all these symbols that you would see with any chemical equation. Plus, separating two or more reactants, two or more products on the equation. The yield or the arrow sign, the arrow with the triangle or the delta symbol shows that reactants are heated to give you the products, and solid, liquid, gas, aqueous. Alright, now we'll move on to identifying a balanced equation. In a balanced chemical equation, no atoms are either lost or gained. The number of atoms you start off with in reactants will equal the same number of atoms in the products. So you can't have mass just disappearing for no reason. You can't have mass just appearing for no reason. What we start off with is what you'll end up with. It may be in a different form, but the number of atoms does not change. So in this example here, you have one atom of carbon, two atoms of oxygen. When they combine together, they form one product, carbon dioxide, but you still have one carbon here and two oxygen. This is a balanced equation. Even though there are two reactants, one product, the amount of stuff has not changed. There's still one carbon on both sides of the arrow. There's still two oxygens on both sides of the arrow. So nothing has changed. Alright, now we'll move on to balancing a chemical equation. And some of these can be fairly straightforward, but when you get into fairly involved chemical reactions, especially those involving polyatomic compounds, it can get really complex. The reaction we're talking about, aluminum in a solid form plus sulfur in a solid form, these are the reactants. They combine to give you Al2S3 in a solid form. Now just looking at this is a unbalanced equation. Over here you have one atom of aluminum on the left hand side, but two on the right as a product. For sulfur, there's one on the left hand side, but three on the right hand side. These are not balanced. So in order for an equation to be balanced, you have to find a way to rewrite this equation where you aren't changing the core of the reaction, but you're changing how it's written, so the numbers do balance out. And the way you do that is you add what are called coefficients to the beginning of each element. And you do that until all the atoms of every element are equal on either side of the arrow. So for this example here, if you added 2 before aluminum, now on this side there are 2 atoms of aluminum, and there are 2 atoms of aluminum on the right hand side. That is balanced. For sulfur, you need to add a 3 as the coefficient before it. 3 atoms of sulfur on this side, and 3 on this side. These are balanced. And again, you aren't changing the the whole core, the whole process of the reaction, that hasn't changed. The only thing that you're changing are the coefficients in front to make it a balanced equation. Now here's what I was talking about with how involved it can be. We're talking about polyatomic ions. Given this very involved, very complex equation, the way it's written now, it is not balanced. This is a quick glance. Sodium over here has 3, but sodium over here only has 1. What can make this time-consuming and complex is that every element has to be balanced. If one element is not balanced, that means the whole equation is not balanced. So you could get all of these, but maybe say sodium, but if that sodium is off, then the whole thing's wrong. So everything has to be balanced. But it's the same process that we did with the previous reaction. You can break it all down. So again, sodium, there are 3 of those here, but only 1 over here. You can break these down by individual elements, like for example, phosphorus and oxygen. But if they are forming a ion together, like they do in this case, you can do it that way also, and that usually will save time. So PO4 is one ion. So there's only 1 of those on this hand side of the arrow, but there are 2 on this hand side of the arrow. That is unbalanced. Magnesium, there's only 1 on this side. There are 3 on this side. And then for chlorine, 2 on this side, only 1 on this side. So there are 4 components of this reaction that are not balanced. All 4 need to be balanced for the full equation to be balanced. You can't just do this one, and this one, and ignore sodium. If one of these isn't balanced, the whole thing is wrong. And the best way to do this is really just trial and error. Keep adding coefficients until you get equal numbers of all elements on either side of the arrow. And the way you would do that here, for sodium, we start off with 3. If you add the 2 in front, 2 of these 3, 2 times 3 gives you 6. Then add a 6 over here to balance that out. Alright, for the PO4, there are now 2 groups of those on this side, because this 2 is applicable to both components of this compound. So 2 over here on the left-hand side goes with the 2 that was already here on the right-hand side, so they're now balanced. You add the 3 in front of magnesium, so that equals 3 on this side. And the 3 that were already on this side, so now they're balanced. For chlorine, 3 times the subscript of 2 gives you 6, and it goes along with the 6 that you just added over here for sodium, so now they're balanced. And again, you aren't changing any part of the reaction given to you. All you're doing is adding coefficients to make the equation balanced. And again, for the final step, going back and making sure all the coefficients match up. And again, if one number or one element is off, then you need to go back and recheck. Sometimes coefficients need to be changed, but you can't change the subscripts. You can't change the 3 for the sodium, or the 4 for the oxygen here, or 2 for the chlorine, or 2 here. Subscripts you cannot change. What you can change are the coefficients. The 2 here, 3 here, and a 6 here. Those you can add. Alright, now I'll move on to different types of reactions. There are multiple forms of reactions, and any reaction can be more than one of these categories. It just depends what is going on. The first one, a combination reaction. Sometimes this is called a synthesis reaction. This is where you have 2 or more reactants forming one product. You are combining 2 things to make one product, or you're synthesizing one product. The opposite of that would be a decomposition reaction. When something decomposes, it breaks down. So you're taking one larger reactant that breaks down into smaller components. So the exact opposite of decombination. Single replacement reactions is where you have one element will take the place of a different element in the reaction. And you'll see an example of that on the next slide. Double replacement. The positive ions in the reactants are switching places with one another. And for the last one on this page, combustion reaction, this is where you have compounds that have carbon in them that will burn in oxygen gas to help form carbon dioxide, which is CO2, and then water, H2O. It's a nice way to visualize both a simple way how to write those types of reactions and an example that's given. The first one, combination or synthesis. This reactant plus that reactant gives you one larger product. So calcium plus chlorine gives you calcium chloride. For these types of reactions, there's more items on the left-hand side of the arrow versus the right-hand side, because you're forming one larger product. The opposite of that will be decomposition. The reactant AB is breaking down into A plus B. So for this type, you'll have more items on the right-hand side of the arrow versus the left-hand side. So this example, Fe2S3 breaks down into iron and sulfide. A single replacement, A plus BC, those reactants will break down to give you the products AC plus B. So we're just using this is regular letters. A is by itself, and you have BC together, but as a product, A and C now are together, and B is by itself. You are switching places here. One element has been swapped out. So an example that's given here, Cu plus AgNO3. As a product, copper is now joined with NO3, and now silver is by itself. This has swapped places here. So Cu and NO3 are now together. So one element is swapping or switching places with another. And for double replacement, AB plus CD gives you AD plus CB. Instead of one element switching places, you have two switching places. An example that's given, BaCl2 plus K2SO4. As a product, Ba is now joined up with SO4. And then chlorine is now joined up with potassium. The elements are still there, but they're switching places. And for both of these, single and double replacement, you have the same number of items on the left-hand side versus the right-hand side. Because you're not breaking anything down, you aren't forming something larger, you're just switching places with various elements. And for the last one, combustion, a carbon-based compound, here methane, added to oxygen and then burning, because you're adding heat, gives you carbon dioxide and water and energy. Alright, next we'll move on to a different class of reactions, oxidation reduction reactions, or redox reactions. Now these are incredibly important, incredibly common. This is how we get energy from the food that we eat, that turn into glucose that we eat into a usable form of energy for our cells. It will help provide energy in batteries, and also what will give you rust with iron. And that's what this equation is showing. The solid form of iron, say on the bumper of your car, plus oxygen in a gas form, that over time gives you iron oxide, a different compound, which is that reddish brown color, which has undergone a chemical reaction. Now in any oxidation or reduction reaction, electrons are going to be transferred, either by losing an electron or by gaining an electron. So oxidation is the loss of electrons, and reduction is a gain of electrons. So for oxidation, the compound will get more positive, and for reduction, you're getting more negative, because you're gaining electrons. Now it's very easy to get these two situations confused, and there is a common saying that's used, or common mnemonic used to help remember what goes with what. Fairly simple, it's kind of silly in a way, but it's also very effective. And that phrase is, Leo goes grr. Leo, the lion, when the lion roars, he goes grr. So the first one, Leo, losing an electron is oxidation. The opposite of that, grr, gaining an electron is reduction. Leo goes grr. So again, pretty silly, pretty simple, but also very effective. A famous example of an oxidation-reduction reaction is the Statue of Liberty, and how it has that very distinct kind of a pale mint green color to it. The outermost layer of the Statue of Liberty is a version of copper called copper carbonate. Now as this layer oxidizes, it forms a green solid, copper oxide. And here's how the Statue of Liberty gets that color. You have the solid form of copper. As it breaks down and it becomes oxidized, that combines with oxygen gas, and those two components combined together gives you copper oxide. It's the same process as iron rusting, like on an old car. It forms a new compound that has a different color. That's what gives rust its distinct reddish brown color, is a new compound being formed. It's the same thing with the Statue of Liberty. It's how it gets that greenish hue to it. It's forming a new compound, copper oxide. Next we'll talk about characteristics of oxidation and reduction. Now the particular definition of these types of reactions depend on what is occurring in the reaction. For oxidation, it always involves a loss of electrons. Remember that phrase Leo, losing electron is oxidation. It may also be seen as the addition of oxygen, and may also be seen as the loss of hydrogen atoms. For reduction, it will always include the gain of electrons. Remember, Leo goes ger, GER, gaining electron is reduction. Reduction may also be seen as the loss of oxygen, and may also be seen as the gaining of hydrogen atoms. Alright, next we'll move on to what's called the mole. Now this is a very important term to understand, and it really is just a counting term used in chemistry. Counting terms that are very, very common, such as dozen, and case, and gross, and so on. Examples that are used here: 24 cans equals 1 case, 144 pencils equals 1 gross, 144 of anything equals a gross of something, 500 sheets of paper equals 1 ream, 12 eggs equal 1 dozen. So the mole is a counting term in chemistry. Now very small particles like atoms and molecules and ions are very, very high in number. So there has to be an easier way to count them, or an easier way to represent such a large quantity. Small particles such as ions and molecules and atoms, because they exist in such high numbers, there's a counting unit called the mole that's used to represent them. And that mole is represented by what's called Avogadro's number. That number represents 6.02 times 10 to the 23rd power. Very, very large number. And here it is written out. This is an excellent example of why scientific notation is a much easier way to represent really, really big numbers or really, really small numbers. Trying to write this number out all the time would be incredibly cumbersome, would be a waste of time, and be very easy to leave off 1 or even 2 of these zeros. But just like we talked about in a previous chapter with scientific notation, for this whole number, the decimal will be right here. So 3, 6, 9, 12, 15, 18, 21, 22, 23. This very large number is exactly the same value as this. So that is called Avogadro's number, named after the Italian physicist from the 19th century. So 1 mole of anything represents 6.02 times 10 to the 23rd power. Here are some examples of what I'm talking about. So 1 mole of any element equals 6.02 times 10 to the 23rd atoms of that element. So 1 mole of carbon equals 6.02 times 10 to the 23rd atoms of carbon. 1 mole of sodium, 6.02 times 10 to the 23rd atoms of sodium. So the mole value is a constant value that doesn't change. And now we'll move on to calculating moles and elements in any given formula. Now the chemical formula and their subscripts will specify the number of atoms and also the number of moles that are found. So this example that we're given, aspirin, C9H8O4. This example, the 9 that goes along with carbon represents 9 atoms of carbon, but also represents 9 moles of carbon. For the 8 for hydrogen, that represents 8 atoms of hydrogen and also 8 moles of hydrogen. And for oxygen, the 4 that goes along with it, 4 atoms of oxygen also represents 4 moles of oxygen. Now the subscripts are going to be used to help you write conversion factors for each mole and each compound. And this is something that we'll talk about in greater detail here in a few minutes. So for 1 mole of aspirin, C9H8O4, don't think of these as fractions, think of these as ratios, because that's what you're talking about. You're comparing mole to mole. So for every 9 moles of carbon, you get 1 mole of aspirin. For every 8 moles of hydrogen, you get 1 mole of aspirin. And so on and so on. And we'll revisit this topic again in a few minutes. But all you're really doing here are having a mole to mole ratio. Alright, now we'll move on to molar mass and calculations. The molar mass of an element is very, very useful to convert moles of an element to grams, or the other way, from grams to moles. And it's simply represented by the atomic mass found on the atomic periodic table of elements. So for example, zooming in on information for sodium, the symbol Na, atomic number 11, the atomic mass 22.99. So 1 mole of sodium will have a mass of 22.99 grams. And this process is true for any element in the periodic table. 1 mole of that element equals its atomic mass. So for the molar mass is what we just talked about regarding sodium. So we'll zoom in on carbon, atomic number 6. 1 mole of carbon is 12.01 grams. This is what this ratio is representing. 1 mole of carbon is the same thing as 12.01 grams of carbon. For lithium, atomic number 3, 1 mole of lithium is equivalent to 6.941 grams of lithium. That's its atomic mass. So don't think of these as fractions, think of these as ratios. Again, this is true for any element in the periodic table. If you know the atomic mass, you know how many grams there are in 1 mole of that element. So 1 mole of silver will be represented by 107.9 grams. 1 mole of carbon, 12.01 grams, and 1 mole of sulfur, 32.07 grams. In this flow chart here, all three of these values are equivalent. 1 mole of carbon is the same thing as 12.01 grams, which is the same thing as 6.02 times 10 to the 23rd atoms of carbon. Those are equivalent values. It's using different units. Because 1 mole of anything equals Avogadro's number here. So these are, all three are equal. Alright, so to show you some comparisons of what 1 mole of various things would look like and how they would compare to one another. In this picture you have sulfur, iron, salt, potassium dichromate, and sucrose. In each of these beakers you have 1 mole of that sample. So 1 mole of sulfur, 32.07 grams. 1 mole of iron, 55.85 grams. Table salt, sodium chloride, 58.44 grams. Potassium dichromate, 294.2 grams. And then sucrose, which is a form of sugar, 342.3 grams. These are all based on atomic mass also. That's why the numbers of grams are higher for compounds that are larger like this, because what you're doing is adding up the atomic masses for each individual component. So for sucrose, for example, you're adding up 12 carbons, you're adding up 22 hydrogens, 11 oxygens. So if you add up the atomic mass of 11 of oxygens, 22 of hydrogens, and then 12 of carbons, all that total together gives you 342.3 grams. Now we'll move on to the law of conservation of mass. This indicates that in a normal chemical reaction, matter can't be destroyed and can't be created. It doesn't just vanish, it doesn't just appear somewhere. There has to be no change in total mass. Now the versions of those products or reactants may vary, but the mass of the reactants must equal the mass of the products. All right, here's an example of what I'm talking about. The reaction you're given, silver plus sulfur, silver sulfide. So if you're looking at just the atoms, there are 2 silver atoms on this side, and there are 2 on this side, so that's fine. 1 sulfur over here, 1 sulfur here, so they're balanced, they're fine, they haven't changed. Then we get down to the bottom, where you're comparing the mass of both reactants and products. The mass of 2 moles of silver plus the 1 mole of sulfur, that added together gives you 247.9 grams. If you add up the mass of the products, Ag2S, 2 silvers plus 1 sulfur, also gives you 247.9. Even though there are 2 reactants and only 1 product, the masses are equal. Alright, now move on to the mole-mole factors of an equation. And these are ratios based on are given to you in an equation. The example that's given here, the coefficient 2 along with iron, coefficient 3 for sulfur, gives you Fe2S3. When you're comparing the ratio between iron and sulfur, for every 2 moles of iron, you get 3 of sulfur, 2 and 3. Or if you're comparing it the other way, for every 3 moles of sulfur, you get 2 for iron. All you're doing is writing the coefficient. Right, comparing iron, and then Fe2S3. For every 2 for iron, you get 1 mole of this whole thing, Fe2S3. If you're looking at it the opposite way, 1 mole of this, because there's an understood 1 here, is equivalent to 2 moles of iron. And lastly, sulfur and Fe2S3. For every 3 of this, there's 1 of this. And for every 1 of this, there's 3 of this. All you're doing is writing a ratio of the coefficients for that compound, or for that element. Now being able to do this is critically important when you're asked to calculate the number of moles in a reaction, calculate the amount of mass for a product or a reactant. And here's how you would go through that. So if you're given a balanced equation, if you need to convert the mass of substance A to substance B, what you do is convert the mass that you're given for substance A to moles by using the molar mass of A. You convert that to a mole for B by using the mole-mole ratio. Once you get that, you convert the amount of moles for substance B into grams for substance B. And we'll go over an example of how that kind of question would look and how you would solve it. Here's a flow chart on how that last slide would look. You're given the grams of substance A. You convert that using its molar mass to get the moles for A. You do the mole-mole ratio comparison between B and A. Give you the moles for substance B. Use the molar mass to get the amount of grams for substance B. Here's how a typical question asking about moles and grams would be presented to you. So this example here is a fairly common one. All right, here's a sample question. You're given the reaction here. Now, C12H22O11, which is sugar, plus oxygen, will give you carbon dioxide and water. So what you're given is 10 grams of sugar, and you're going to be asked to find how much in mass of oxygen is used. Following our slides, this part here is for our example here. This will be A, and then that will be B. Okay, and here's how you do that. Okay, the 10 grams of the sugar that you're given, and you multiply that by the equivalent value of 1 mole of sugar times the molar mass. If you take 12 masses of carbon, add that to 22 masses of hydrogen, add that to 11 atomic masses of oxygen, you get a total of 342.3 grams of sugar. So these are equivalent. And the reason why you have mole on top and grams on bottom, that way the grams here will cancel each other out. So what you're left with is 0.02921 moles of sugar. That's how much 10 grams of sugar will give you. Alright, that's the first part. Now you need to take this and do a mole comparison. Alright, starting with the value we just found, 0.02921 moles of sugar. And the equation up here, 12 moles of oxygen, because the coefficient is 12, so 12 will go there, versus the 1 mole of sugar. And again, the reason why you want moles of oxygen on top, because that's what you're wanting. What you want to cancel out and get rid of, you put on the bottom of these ratios. So for here, the moles of sugar will cancel each other out. So what you're left with is moles of oxygen. So 0.3505 moles of oxygen. And now we have one more step. Right, starting with the value that we just found, 0.3505 moles of oxygen. To convert moles to grams of a sample. The atomic mass of oxygen is 16, but we have 2 of those. So 2 of those will be 32 grams. Again, we want the unit that we want to get rid of on the bottom of this ratio, so it can be cancel each other out. So our final answer, 11.22 grams of oxygen. So this whole process, the substance A will be the sugar, substance B would be the thing that we're trying to solve for. In this example, grams of oxygen, so 11.22 grams. Okay, and here are all 3 steps. Put side by side by side. 10 grams of what you're given. You convert the grams that you're given to how many moles of what you're given. Take that value, do the mole-mole comparison in the equation that you're given. What you want to solve for is the substance B. In this example, it would be the oxygen. So that value to go on top. 12 versus 1. That gives you the moles of oxygen. That value, convert that to number of grams per oxygen, which is what you want on top, and gives you your final answer. And that's a very typical, very common question when you're asked to find grams versus moles or vice versa. Alright, now we'll move on to the heat of reaction. And the heat of reaction is the amount of heat that is either released or absorbed during a reaction that takes place at a constant pressure. Now, the change in energy will occur when bonds are broken, or products are formed, or reactants combine with one another. And the heat of reaction is also called enthalpy, and it's written by the symbol delta, and then H, capital H in italics. Whenever you see that symbol delta, or that triangle, that means the change of. So this is literally written down as, can be translated into the change of enthalpy or the change of the heat of reaction. And this is really just the difference between the enthalpy of the products and the enthalpy of the reactants. This is a mathematical way you would write this. So enthalpy equals enthalpy from the products minus the enthalpy of the reactant. There are two main types of reactions, either or based on if you release energy or absorb energy. The first one, exothermic. Exo means outside, so exothermic. Thermic means heat, so this will translate into releasing of heat. So in this example, the energy of the products is less than the energy of the reactants because heat is a product. This is where energy gets released. So for here, hydrogen plus chlorine gas, hydrochloric gas, and also energy, 185 kilojoules of energy. Whenever you release heat as a product, as an exothermic reaction is, you'll have a negative enthalpy. The opposite of that would be endothermic. Endo always means inside, and again, thermic means heat. So this is where heat gets absorbed. So the energy of the products is higher than the energy of the reactants. So heat is a reactant. Heat gets added to the reaction. So for example here, nitrogen gas plus oxygen gas plus energy, 180 kilojoules, will give you nitrogen monoxide. So because you're adding heat to it, heat is being absorbed as a part of the process, as a part of the reaction. It's going to be endothermic, so a positive enthalpy, so 180 kilojoules. Alright, in this chapter, chapter number 8, we'll discuss the properties of gases. In general, molecules that have 5 or fewer atoms from the first two periods of the table, the periodic table, will be gases at room temperature. And in addition, this list here are also gases at room temperature. They include hydrogen, nitrogen, oxygen, fluorine, and chlorine. And if represented by the subscript 2, that's because all of these are what are called diatomic atoms. So when they're found naturally, it's rare that you find them by themselves with one atom. They're always found or in a pair of two. That's why it's H2, not just H, or N2, not just N. That's how they naturally are found. Right, oxides of the nonmetals, the upper right corner of the periodic table, will also be gases at room temperature. They include carbon monoxide, carbon dioxide, nitrogen monoxide, NO2, SO2, SO3. And also the noble gases, the elements that are very, very stable on the far right edge of the periodic table. All right, now move on to the kinetic molecular theory. A gas will consist of very small particles that move randomly but move very, very quickly with a lot of velocity. These will also have very small attractive forces between each other. Sometimes they'll even have repulsion forces with each other. And they will occupy a much larger space than what the molecules have just by themselves. And here's what I mean by that. If you look at this image here, these circles represent the atoms whizzing around rapidly to form the gas, but the entire gas will take up the entire container. But if you were to add up just the size of each individual atom, much, much smaller amount of space than what the gas will give you because of the motion of the particles all over the container. Right, these particles that are found in gases are in constant motion and will move rapidly in straight lines. And they have a Kelvin temperature that is proportionate to their average kinetic energy of the molecule. Our gases are described in terms of 4 basic properties: pressure, volume, temperature, and amount. You'll see how they're represented here. Pressure, capital P; volume, capital V; temperature, capital T; and amount, lowercase n. Now here are those properties and their definitions, and what units are used to represent their measurements. For pressure, this is the force that is exerted by the gas against the walls of its container. There are multiple units of measure that you can use for pressure. Atmosphere, which is represented by ATM. Millimeters of mercury, mm for millimeters, and Hg, the elemental symbol for mercury. Torr, the actual word torr, and then pascals, Pa. Any of these units can be used to represent pressure. Volume, of course, the space occupied by that gas, can be measured in liters or milliliters, so capital L or ml. Temperature, the determining factor of the kinetic energy and the rate of motion of all the particles in the gas, can be measured in degrees Celsius or in Kelvin. And for the amount, of course, the quantity of gas that's present in the container, can be represented by grams or moles. When it comes to the amount and the temperature of gases, those measurements are required to complete the gas law problems that we'll discuss here in a few minutes. If you don't have those measured, or if you're using the wrong unit, you'll get the equation wrong. So it's very important that you keep track of these units and use them correctly. Alright, first we'll discuss volume. Of course, the volume of the gas is the shape of the container that gas occupies. It will be represented by either milliliters or liters. Alright, the volume of a gas will increase as the temperature increases, as long as there is a constant pressure. There's a direct connection between volume and temperature. Alright, speaking of temperature, the temperature of the gas is the average kinetic energy of the molecules, and will be measured in Kelvin, not Celsius, but usually on the Kelvin scale. When that temperature of the gas goes down, the molecules have fewer collisions. There's less energy there. When that temperature goes up, that means there's more energy there, so there's going to be more collisions between the particles. Pressure. Pressure is the measure of the gas particle collisions on the sides of the container, and measured in units such as millimeters of mercury, torr, atmospheres, pascals or kilopascals, or even psi, pounds per square inch. For this picture here, the atmospheric pressure is the pressure of the atmosphere pushing down on the top of this person's head. A barometer is used to measure pressure. Anything that ends in the ending meter is a reference to being measured, or being measured by, and baro is a reference to pressure. So a barometer will measure the pressure exerted by the gases in the atmosphere, and it's indicated by the height in millimeters of the liquid mercury. So what you have here in this image, a small container filled with liquid mercury. The gases of the atmosphere will push down on this liquid. That will cause the liquid mercury to rise up exactly a height of 760 millimeters. So that's why this is referenced as millimeters of mercury. It is literally talking about a specific height of a element. So millimeters of mercury. And these three values here are all equivalent. So 760 millimeters of mercury is exactly the same value as 1 atmosphere, which is exactly the same thing as 760 torrs. So all three of these represent exactly the same value. The only difference is using 3 different scales. So being able to convert from one unit to the other is critically important when you're given sample problems using the gas laws, which we'll go over in a few minutes. If you use the wrong scale, you won't be able to use the formulas correctly and you won't get the right answer. Alright, atmospheric pressure is the pressure exerted by the column of air on top of the atmosphere onto the surface of the Earth, and this will decrease as you go higher in altitude. So the standard measure of atmospheric pressure is 1 atmosphere, 1 atm. So that's at sea level. Let's say at this water level here. As you go up to the top of this mountain here, the pressure will get less and less and less. So at the top of this mountain, it is 70% of normal atmospheric pressure. So instead of being 760, it's now 530 millimeters of mercury, 0.7 atmospheres. So the higher you go, less pressure. Alright, next we'll talk about the relationship between volume and pressure, also known as the Boyle's law. Now the relationship between the two is known as an inverse relationship. What that means is when one goes up, the other one goes down. They are inversely related. And here's a good way to think of that, or a common example of a way to think of this, is how you breathe with your lungs. If you take a deep breath in, the volume of your lungs and your chest increases. But when that volume increases, that causes the pressure to go down. That's how air gets forced into your lungs. And the exact opposite happens when you exhale. When you breathe out, your lung volume will decrease, which causes the pressure to increase. So air gets forced out of your lung. Alright, and here's a graphic to illustrate that. Of course, the pressure of a gas inversely related to the volume. When the temperature is constant, that's a key component of Boyle's law. The temperature must be a constant value. So this container, you have a volume of 4 liters, and the pressure is 1 atmosphere. When the volume goes down, the pressure now goes up, because you have a much smaller space for the same amount of volume. So the pressure has to go up to correspond to that decrease. So inversely related. Volume went down, pressure goes up. And here's the equation that's used to represent this. P1 V1 equals P2 V2. And when you see numbers like this, 1 and 2 in equations, 1 is always a reference to the initial setting or the initial reading or the initial value, and then 2 always represents the final value. So the way you look at this equation is the initial pressure multiplied by the initial volume is equal to the final pressure multiplied by the final volume. And the way you'll see questions referencing this equation, You'll be given 3 of these 4 values, and you need to solve for the 4th one. And we'll go over an example of that here next. Alright, here's a typical way a Boyle's Law question would be asked. If I have 5.6 liters of a gas in a piston at a pressure of 1.5 atmospheres and compress the gas until its volume is 4.8 liters, what will the new pressure inside the piston be? So going back to the Boyle's Law equation, you have P1 equals P2 V2. Okay, and of these 4 values, P1, V1, P2, V2, you are given 3 of them in the sample problem. You're given initial volume, initial pressure, final volume, and then you're asked to find the new pressure, or P2. So all you are really doing is using basic algebraic skills, rearranging the equation and solving for the variable that you do not have. Now there are 2 ways you could really do this. It really just boils down to a personal preference. Some people like to rearrange the equation first and then solve for the variable that they don't have, or others will like to go ahead and plug in all the information first and then rearrange. It really doesn't matter. As long as you do it correctly, you will get the same correct answer. What I always like to do is I like to rearrange the equation first and then start plugging in values. That's just my personal preference. So we're asked to find the new pressure, or P2. To isolate P2 here by itself, you need to divide this side by volume 2. And whatever you do to this side of the equation, you have to do to this side of the equation also. So when you do that, the V2's cancel out here. So what you're left with is P2, what we're trying to solve for, and then what we have left over here, P1, V1, all of that divided by volume 2. Now it's just a matter of plugging in all the values. Alright, P1, which is 1.5 atmospheres, multiplied by the initial volume, which is 5.6 liters. All that divided by volume 2, 4.8 liters. Do all that math, you get 1.75 atmospheres. And that will round up to 1.8 atmospheres. Alright, now we'll move on to Charles' Law, which is the relationship between volume and temperature. So if we increase the temperature of a gas, the kinetic molecular theory will state that the motion, or the kinetic energy of those particles, will also increase. So if the pressure of a gas is constant, the volume will increase. So that's how temperature and volume are related. So if temperature goes up, volume goes up. Here's another graphic to illustrate that. So the Kelvin temperature of the gas is directly related to volume. If one goes up, the other one goes up. If one goes down, the other one goes down. That's assuming that the pressure and the moles of the gas are constant. In this container, you have the initial temperature of 200 Kelvin, and the volume is 1 liter. If that temperature goes up to 400 Kelvin, the volume will also go up to 2 liters. So these are directly related. One goes up, the other one goes up also. One goes down, the other one goes down also. So this is the equation for Charles' Law. The initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. And just like in Boyle's Law, a standard way to ask a question like this is you're given enough data to figure out 3 of the 4 of these values, and you need to solve for the 4th. And we'll go over an example of that here now. Okay, here's a pretty standard sample question that you see for a Charles' Law question. A sample of nitrogen occupies a volume of 250 milliliters at 25 degrees Celsius. what volume will it occupy at 95 degrees Celsius? And there's one thing I need to point out right away, and it's something that always throws off students if they're not paying attention. That is these. When you're solving problems with Charles' law, the temperature must be in Kelvin, not Celsius. So you cannot plug in 25 degrees Celsius or 95 degrees Celsius and get the correct answer. A lot of people will just kind of gleam over the data in the question and just plug in temperature 1, temperature 2, and thinking that they're going to get the right answer. But if you aren't using the correct scale, you cannot get the correct answer. So you need to convert both of these. So for these, to convert Celsius to Kelvin, all you do is add 273 degrees to them. So for this one, that now becomes 298 Kelvin. And then this one here, we add 273 to that, 368 Kelvin. That's something that's very important to remember when you're doing Charles' law questions. You must use the Kelvin scale for temperature, not Fahrenheit, not Celsius. Alright, so now you have 3 of the 4 values that you need, and just like with any other gas law, you have all the variables that you need except for one. You need to rearrange the equations to solve for that unknown variable. So again, the initial starting equation for Charles' law, initial volume divided by the initial temperature equals the final volume divided by the final temperature. So now you're trying to find the volume, because it's asking what volume would it occupy. So it's asking for volume 2, so we need to rearrange everything to solve for this. Alright, by going ahead to plugging in the values, initial volume, V1, 250 milliliters, that's what you were given here in the question. Initial temperature is not 25 degrees Celsius, but 298 Kelvin. You have to use Kelvin, otherwise these equations don't work. V2 is what we're solving for, and then divided by the final temperature, not 95 degrees Celsius, but 368 Kelvin. So now you just rearrange this and solve for volume 2. To isolate volume 2 by itself, you would multiply this side of the equation by 368 Kelvin. And what you do to this side, you must do over here also. Multiply all that by 368 Kelvin. You have to do the same thing over here. Kelvin. And when we do so, these values cancel each other out. They're just left with V2. It's V2 over here. 368 Kelvin multiplied by 250 milliliters. That quantity divided by 298 Kelvin gives you a total of 308.7 milliliters. And depending on how specific that you need to get with your answers and significant figures, just by doing the math, you will get 308.7 milliliters. But if you are going by just the number of significant figures, you're only going to have 2 significant figures in this final answer, or you should only have 2 significant figures. So that answer will become 310 milliliters. There's only 2 significant figures in this answer, the 3 and the 1. Alright, now we'll talk about the relationship of temperature and pressure. It's also known as Gay-Lussac's law. Temperature, or the Kelvin temperature of a gas, doubles at a constant volume. The pressure will also double. So they are directly related. So there's a graphic that's given here. The temperature is 200 Kelvin, and the pressure is 1 atmosphere. If that temperature were to double up to 400 Kelvin, the pressure will also double. So there is a direct relationship between those 2 variables. And as that graphic again is a little bit bigger, a little bit clearer, doubling the temperature from 200 to 400 Kelvin will double the volume from 1 liter to 2. And here's the equation for Gay-Lussac's law. The initial pressure divided by the initial temperature is equal to the final pressure divided by the final temperature, assuming that the volume is constant. And just like the Charles law, just like Boyle's law, the way to ask this kind of question normally is to give you 3 of the 4 variables and ask you to find and solve for the 4th. Alright, now we'll talk about vapor pressure and the boiling point. When liquid molecules with sufficient energy break away from the surface of the liquid, they become a vapor. So in an open container, all of the liquid will eventually, at some point, evaporate. In a closed container, the vapor will accumulate and build and build and build and create a pressure called the vapor pressure. A liquid will exert its own vapor pressure at a given temperature, and it will boil when its vapor pressure becomes equal to the external pressure. Now we'll talk about the boiling point altitude and how they're related. But as you get higher in altitude, the atmospheric pressure will go down, and also the boiling point of water will become less than what it would be at sea level. At sea level, at 1 atmosphere, it's going to be 100 degrees Celsius. But the higher you go in elevation, that boiling point goes down. In a closed container, like a pressure cooker, the pressure is greater than 1 atmosphere, and also the water will boil at a higher temperature than 100 degrees Celsius. And here are some common examples. The normal sea level here, 760 millimeters of mercury, which is equal to 1 atmosphere. Water will boil at 100 degrees Celsius. The higher in elevation you get, the lower the air pressure gets. So let's say you're down here. So instead of being at 760 millimeters of mercury, down to say 270, the boiling point of water is now 70 degrees Celsius, not 100. And the opposite of this will be true also. If you get a higher pressure than the 1 atmosphere, say 2 atmospheres here, the boiling point for water is now 120 degrees Celsius. Now we'll talk about an equation called the combined gas law. The combined gas law will use pressure and volume and temperature relationships from the equations we just talked about. Charles' law, Boyle's law, Gay-Lussac's law. If combining all of them together in one equation, that's called the combined gas law. Here's the way it's represented. P1 times V1, all that divided by T1. So the initial pressure times the initial volume, all that divided by the initial temperature, will equal the final pressure times the final volume, all that divided by the final temperature. All this is a combination of the 3 equations we just talked about. Gay-Lussac's, Charles, and Boyle's. Just like any of the other equations we talked about, you may be given all these but one, and you need to solve for the one that's not given to you. Alright, now we'll move on to Avogadro's law. This shows a connection between volume and moles. In Avogadro's law, the volume of the gas is directly related to the number of moles of that gas. This is assuming that the pressure and temperature are constant. So the example that's given here in the graphic, if you have 1 mole of a gas, it occupies 1 liter. If the amount of moles goes up, the amount of volume will go up also. And the equation for Avogadro's law, the initial volume divided by the initial amount of the gas will equal the final volume divided by the final amount of moles of that gas. And following our pattern of all the other equations, you're usually given 3 of these values or enough data to solve for all 3, and you're asked to find the 4th. Alright, next we'll move on to something called STP, standard temperature and pressure. Now the volumes of gases can be compared at STP when they have either the same temperature, or they have the standard temperature of 273 Kelvin or 0 degrees Celsius, or if they have the same pressure, or if they have the standard pressure of 1 atmosphere. Now at the standard temperature and pressure, 1 mole of a gas occupies a volume of exactly 22.4 liters. So this value is called the molar volume. Again, these are equivalent values. So 22.4 liters is the same thing as 1 mole of a gas. And here are some ratios to compare. 1 mole of gas equals 22.4 liters. And depending on what unit you're trying to get rid of and what unit you're trying to find will determine which one of these will be on top, which one of these will be on the bottom. Alright, next we'll move on to a very important equation in chemistry called the ideal gas law. And the ideal gas law is the combination of 4 properties used to measure a gas: the pressure, the volume, the temperature, and the amount, to give a single expression. And it's written as this: PV equals nRT. So pressure times volume will equal the amount of the gas times R, which is a constant, which we'll talk about next, times the temperature. If you take a chemistry class, you will see this equation quite often. Now, I mentioned how the value of R is a constant value, and here is what that number represents. And it really just depends on what unit you're using for pressure. If you're given pressures in atmospheres, you need to use this value: 0.0821 liters times atmospheres, all that over mole times Kelvin. If you're using millimeters of mercury, you need to use this value: 62.4 liters of millimeters of mercury, all that divided by mole times Kelvin. All the other units will be the same: liters, moles, Kelvin. And this is what I was referencing earlier in the chapter. You have to be very, very careful to use the correct units. If you're given a question and you're given millimeters of mercury, and you're asked to use this equation, and you use this value instead, not only will the values be completely wrong, but the units won't cancel out correctly. That's why these units are listed how they are. If you are given a measure of pressure in, say, torrs, but don't convert it to atmospheres or millimeters of mercury, you're going to get the wrong answer, and you can't use this equation properly. If you don't represent the volume in liters, you'll get the answer wrong. Or if you're not using moles correctly, or if you use Celsius and not Kelvin. These units are part of that identifier for that value. What happens quite often for students is they focus on the numerical value of the question and not the units. They just add on the units at the very end. But the unit is a part of that identifier for that value. If you're asked to find a measure of volume, and the final unit you come up with is grams, well, obviously you did something wrong. Gram is a measure of mass. For volume, it should be liter or milliliter. So the units should not be ignored. Units are a key part to any chemistry question answer. But again, the value for R in the ideal gas law is a constant value. You use either one of these, depending on what you are given in your question. And we'll go over an example of a question like that here now. Okay, here's a typical question when it comes to the ideal gas law problems. And we'll go over some common mistakes that people make when it comes to this equation also. Question: if I have 4 moles of a gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? So just in this question, you already have all the information that you need to solve for the equation. So we'll start off with our generic equation. PV equals nRT. Alright, we have pressure, we have volume, we have N, number of moles, and then of course the R is a constant value. R will equal 0.0821 liters, atmospheres, all that over Kelvin times mole. Now this is the most common way to represent the value for R, that constant 0.821 liters, atmospheres, all that divided by Kelvin mole. There are other values, but this is the way that you will often see it represented. And this is important because you must use these correct units. You have to use liter and atmosphere and Kelvin and mole. A lot of times for chemistry classes, you're given questions just like this one that we're going over now, but you're given the pressure in torrs or in pascals or in millimeters of mercury. You must be able to convert all of those to the correct units, otherwise the answer you get will be wrong. You can't just plug in values from the question and what you think is temperature, what you think is moles, what you think is pressure, and expect to get the right answer. If you use the wrong units, these units won't cancel out. So a good indicator of if you're doing it right or not, if you're asked to solve temperature like we are in this question, if you come up with an answer as a measurement of volume, then you did something wrong. If you came up with a measurement for moles, that's obviously wrong. So always look at what you're given in your question and look at what you have to solve for. And then if you use the units correctly, they will cancel each other out. Alright, this question we need to solve for temperature. So we need to isolate temperature over here. To isolate temperature here, we need to divide this side of the equation by NR, so we can cancel out. And whatever you do to this side of an equation, you must do to this side of an equation. Divide that by NR, that by NR. So those will cancel each other out on this side. So what you're left with is T by itself, what we're looking for. And now you have PV over NR. And now it's a matter of plugging in the values and the units and seeing what you have left. So pressure, 5.6 atmospheres. times the volume, 12 liters. All that over N, which is 4 moles. And then the value for R, 0.0821. That's what you have. 67.2 for the top. At the bottom, 0.3284. So 67.2 divided by 0.3284. (204.6 Kelvin), and that would be your final answer. But again, the key problem that people have with the ideal gas law, even though it is pretty straightforward, PV equals nRT, you must use the proper units when you're using the value for R. If this question had the pressure in, say, torrs, you couldn't use this value, because torrs and atmospheres would not cancel each other out as units. So make sure that you are using Kelvin temperature, you're using liters for volume, and you're using atmospheres when it comes to the pressure when using this value. Alright, now we'll talk about the gas laws and chemical reactions. Now, gases are involved as reactants and products in countless chemical reactions. And typically the information that's given for a gas is its pressure, volume, and temperature. And you can use the ideal gas law to determine the moles of the gas in the reaction, as if you're given the number of moles for one of them, and the moles of the other substance using the mole-mole ratio. Alright, next we'll move on to what's called partial pressure, or also known as Dalton's law. And the image that you see here is the heart sending oxygen both to the cells of the body and also receiving oxygen from the tiny air sacs in the lungs called the alveoli. Alright, all cells in our body are constantly producing carbon dioxide and have the constant use and need for oxygen. So both gases are moving in and out of the lungs at the same time, all based on simple diffusion and what's called partial pressure. And that will determine how much and how quickly oxygen will diffuse into the blood to be delivered to body tissues, and how quickly carbon dioxide can be eliminated from the lungs to be breathed out. Now, partial pressure is just the pressure that a gas would exert on a container if it were in a container by itself. So it is the pressure of that part of that gas. And here's what I mean by that. Let's say you have a container here. It's filled with argon and helium. Let's say that the total pressure in this entire container is 6 atmospheres. If you were to look at just the pressure of just the helium part, that's going to be measured at 2 atmospheres in this example. So the partial pressure of helium is 2 atmospheres. The pressure of the argon by itself, just the argon, would be 4 atmospheres. All right, so if the total pressure of both of those together is 6 atmospheres, just a portion of helium is 2 atmospheres, just a portion of argon would be 4. So that's what the partial pressure is, just focusing on just one component of the overall total. And that leads us to Dalton's law of partial pressures. This indicates that the overall pressure of a gas is indicated by the total number of gas particles and not on the types of the particle. The total pressure exerted by a gas of a mixture is the sum of all the partial pressures. It's like we saw on the last slide. The total container was 6 atmospheres. That was the total of the pressure of the helium plus the pressure of the argon and so on. That's what this equation represents. The total pressure equal to the pressure of the first part plus the pressure of the second part and so on. So helium would be, say, the first pressure, argon would be the second pressure. So you keep adding all the individual components of that mixtures of gas to get the overall total pressure. Okay, in our next chapter, chapter number 9, we will talk about solutions. Now, a solution is a homogeneous mixture of 2 or more substances. There has to be at least 2, but there's no ceiling, no limit in how many there can be. Now, a solution will form when there's a sufficient attraction between the solute and the solvent molecules. Now, those terms, solvent and solute, are what make up a solution. The solvent is the substance that's present in the higher amount. In almost every case in chemistry, the most likely solvent will be water. And then the solute is the substance found in a smaller amount. So for example, the image that's given here, you have a beaker filled with water and salt is being added to it. So that is forming a solution. You have a mixture of two or more substances, the water and the salt. And in this example, the salt is present in the lesser amounts. The salt would be the solute, and the water would be the solvent. Now solutes can be either liquid or gas or solid, just like in the previous example with the grains of salt. They will be evenly spread out throughout the solution, and they will mix with the solvent so the solute and solvent have the same physical state. Another key factor about solutes, you can't separate them by filtration. For the beaker of salt water from the previous slide, you couldn't filter out that salt just by using a normal filter of any kind. But the way you can separate the two is by evaporation. If we were to take that beaker of salt water and evaporate the water away, the salt would remain behind. So that's how you can separate the two. It has to be by evaporation of the solvent. And solutes are also not visible, but they can give a color change to the solution in general. So going back to this image here, salt water tends to be cloudy. Even though you can't see the individual grains of salt, the presence of the salt as the solute gives the overall solution a very cloudy or very turbid appearance to it. So it does result in a color change, even though you cannot see the individual components. Alright, here's a table of some common solutes and solvents, both in a gas, liquid, and solid. For gas solutions, a gas and gas. So for example, air is a very good example. Primary solute would be oxygen, solvent would be nitrogen, because nitrogen is present in the higher amount that oxygen is in the general air. For liquid solutions, a gas and a liquid, say soda water or household ammonia. So for household ammonia, the primary solute would be ammonia, and the solvent would be water. Say vinegar, this would be primary solute, and water, primary solvent. Seawater, sodium chloride or salt, with the solute, of course water would be the solvent. So in almost every case we're talking about a liquid solution, in most cases, not all, but in most cases, especially in chemistry and biology, the solvent will almost certainly be water. Now water is probably the most common solvent found in nature, and it's a polar molecule due to the bond between the oxygen and the hydrogen. And the molecules that will form hydrogen bonds like this are very important in many biological compounds. This is a very commonly found type of bond found in biology in particular. Alright, some solutions can have ionic solutes, and a good example of that is salt water, like we talked about before. Salt, the sodium chloride. These crystals will undergo hydration as water molecules surround each ion and basically pull it apart into the solution. So what you have here is the solid particles of salt, sodium chloride. When added to water, it will break that up into the sodium ion, sodium plus 1, and the chloride ion, chloride minus. So that's what's happening here. You're getting the separation of the solute, but what you're forming is ions, the positively charged sodium and negatively charged chlorine ion. All right, now we'll talk about solutions that have polar solutes. A polar molecular compound, such as methanol, which is really just a carbon surrounded by 3 hydrogen atoms, and that's joined to an hydroxide ion, or OH ion, is soluble in water because methanol has a polar OH group that will help form a hydrogen bond with water. Polar solutes require a polar solvent in order to form a solution. So here's how this would look. Methanol solute, and then you have the water solvent. So when you add these two together, you get the methanol water solution due to the hydrogen bonding. Alright, next we'll talk about electrolytes, what's considered a strong electrolyte, what's considered a weak electrolyte, and what's considered a non-electrolyte. Alright, for the first one, a strong electrolyte, this is a compound that will completely dissociate or break up 100% in water, and by doing so it will produce a positively charged ion and a negatively charged ion. And these will form solutions that are able to conduct an electric current strong enough to power a light bulb. An example of one of these is one we've already talked about, sodium chloride or salt. When you have sodium chloride being broken down with water, it will completely separate, so every crystal is broken, forming either a sodium ion or a chloride ion. And these are a very, very strong electrolyte solution. Other than that, you have what's called a weak electrolyte. These will only dissociate slightly in water, so the compound will break up a little bit. Not all the atoms will break up. Some do, but most don't. So a good example of that is hydrogen fluoride. Added to water, some of it will break down into a positively charged hydrogen ion and a negatively charged fluoride ion. Not all of them do. Mostly the compound will stick together. That's why you'll get some ions here, some ions here. But for the most part, it doesn't really break up all that much. So this is considered to be a weak electrolyte. You still get some conductivity of electricity, but not that much. And lastly, non-electrolytes. These are compounds that will dissolve, but as molecules in water. They don't produce any ions at all. So because they don't produce any ions, they don't produce, or they're not able to conduct an electric current. A good example of that is sucrose, which is a form of sugar. So a solid form of that being dissolved in water. All you get is sucrose being dissolved in water. Now it's an aqueous form of sucrose. It doesn't break up at all. There's no loss of any particles in any way, so it doesn't have a negative or positive charge to it, so it can't conduct an electric current. Alright, next we'll talk about solubility. Now, solubility is the maximum amount a solute can dissolve in a specific amount of solvent. Now, this is usually temperature sensitive for solutes, and the way this is written is it's expressed as a measure of grams of the solute in 100 grams of solvent, usually water. So this is usually how you'll see it represented. Grams of that solute divided by 100 grams of water. Now, solutions that are unsaturated contain less than the maximum amount of solute. Some of it has broken down, but not all of it. So you can still dissolve more solute. So not everything has been completely broken down. It is unsaturated. Now, the opposite of that would be a saturated solution. A saturated solution is a solution that contains the maximum amount of solute that can be dissolved. It may have undissolved solute at the bottom of the container. And one thing that may also happen is in a saturated solution, you have the solute that will dissolve, but it may also recrystallize and then break down again, then recrystallize and break down again. So this is how that would look in an equation. Solute plus a solvent. It completely dissolves, so you get a saturated solution, but some of it may recrystallize to go back to here, and then go back and forth. This is a reversible reaction. That's why you have the double arrows here. So we're getting comparing the two, unsaturated versus saturated. For unsaturated solutions, some of the solute has been broken down, but not everything. There's still more to be dissolved. And in a saturated solution, everything has been dissolved, and you may still get some crystallization, like you do here by the bottom of the beaker. So it may dissolve, then recrystallize, then dissolve, then recrystallize, on and on and on and on. But this has the most you can get. This one has only some of what you could get. Alright, now we'll talk about the effect that temperature has on solubility. Solubility will depend on temperature. Now, of most solids, the solubility will increase as the temperature increases. Any type of solid material, the higher the temperature, the more that you're able to dissolve away. And for gases, the solubility will go down as the temperature increases. Okay, in this chart here, you have temperature on this axis here, and then solubility on the vertical axis. So for, say, glucose, for example, as the temperature goes up, solubility gets much, much higher. Potassium iodide, a nice steady incline based on temperature increasing. And again, the solubility of gases will go down as the temperature increases. Right, here are some common examples. Oxygen here, carbon monoxide here, nitrogen here. As you can see, as the temperature increases, the solubility of each gas will go down. And that's true for every gas, not just these three listed here. But as temperature goes up, solubility will go down. Alright, now we'll talk about the connection between pressure and solubility. And a good way to explain this is what's called Henry's law. Henry's law states that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. And at higher pressures, more gas molecules will dissolve in the liquid. So when the pressure of a gas above a solution goes down, the solubility of that gas also goes down. So example that's given here, a typical can of soda, you have carbon dioxide under high pressure because it's closed. So you'll have more gas dissolving in that liquid. But once you open it and that pressure gets released, it's going to be much lower pressure on the liquid because the pressure of the gas above it has decreased. Alright, next we'll compare soluble versus insoluble ionic compounds. Only ionic compounds that contain a soluble cation or anion are soluble in water. In an insoluble ionic compound, the ionic bonds are way too strong for the polar water molecules to break apart. So we can use the solubility rules to predict whether or not an ionic compound would be expected to dissolve in water or not. Alright, here's a table for the solubility rules for ionic compounds in water. For positive ions, say lithium, sodium, potassium, rubidium, cesium, and ammonium. An ionic compound is soluble in water if it has either one of these positively charged ions or if it has negative ions. Now, if an ionic compound does not have at least one of these in this table, it is most likely insoluble because the ionic bonds are just too strong for the water to break apart. Alright, next we'll talk about a property called molarity. Now, molarity is the moles of a solute per liter of solution. And it's usually written in this way. Capital M for molarity, moles of a solute per every liter of solution. A solution of sodium chloride is defined as having 1 mole of sodium chloride per 1 liter of that solution. Alright, next we'll talk about some various properties of solutions. The image here is antifreeze being poured into a radiator, and the compound that's found in that is ethylene glycol. This will help form an aqueous solution that will help lower the freezing point. This will help form a solution that actually has a freezing point that's lower than water. That's why it's called antifreeze. It takes a lower temperature in order for it to freeze. For the learning goal for this section of the chapter, be able to identify what is a solution versus a colloid versus a suspension, and describe how the number of particles in a solution will affect that solution's freezing point and boiling point and the osmotic pressure of the solution. Next we'll contrast solutions and colloids. Solutions will be transparent. You cannot separate the components and will contain small particles or ions or molecules that can't be filtered through a semi-permeable membrane. A good example of this is the salt water that we've been talking about this chapter. You can't separate the salt from the water. The only way you can separate the two is by evaporating the water. That's not a filtration process, that's evaporation. Now that compared to colloids, a colloid will have medium-sized particles within the solution. It also cannot be filtered, but it can be separated by a semi-permeable membrane. And in this table there are some examples of some common colloids. Cheese, butter, milk is another good example of a colloid, shaving cream, soap suds, and so on. Next we'll talk about suspensions. Suspensions are heterogeneous and non-uniform mixtures. These will have very large particles that will settle out of the solution. When the solution is not moving or when the solution is standing, not being stirred, the larger particles will settle down at the bottom. These can be filtered, and they must be stirred in order to remain suspended. Once you stop stirring, say a glass of water where you add dirt to it, if you keep stirring, they will all mix together. But once you stop stirring, the dirt will settle down to the bottom of the glass, or bottom of the beaker. That is a suspension. Other examples, platelets that are found in blood, muddy water, and calamine lotion. Alright, next we'll talk about freezing point lowering and the boiling point elevation. When a solute is added to water, physical properties can change. And also the vapor pressure above the solution can go down, the boiling point can increase, and the freezing point can also decrease. Now, these types of properties are called colligative properties. They only depend on the concentration of the solute particles of the solution. So the higher the concentration of the solute, the higher the impact you'll have on the solution in general. Alright, first we'll talk about vapor pressure lowering. Increasing the concentration of the solute particles in the solution decrease the number of solvent particles at the surface of the solution. This will prevent some of the solvent particles actually leaving the solution. So let's say this example here is one we've talked about before, the water and then adding the salt to it. So in this beaker would be just a pure solvent, just a pure water. And in this beaker here we have the solute plus the solvent. Before our example, adding the salt to the pure water. And by doing so, since you're adding the solute to the solvent, you're actually lowering the vapor pressure. And by doing so, this also prevents some of the particles of the solvent from escaping the solution. Alright, next we'll talk about boiling point elevation. Increasing the concentration of the non-volatile solute particles in a solution will raise the boiling point of that solution. And because you're increasing the concentration of the solute, that will actually lower the vapor pressure and also will increase the boiling point of that solution. Alright, somewhat related to that is the freezing point lowering. And a good example of this is when you add salt to a road or say a sidewalk or a driveway that's covered in ice. And by doing so, that ice will melt. And what you're doing here is actually lowering the freezing point of the water. So instead of freezing at 32 degrees Fahrenheit, it may now freeze at 28 degrees or so. So it takes a lower temperature in order to freeze. An example that we've seen before, or we saw earlier, adding the antifreeze to the radiator. By adding the ethylene glycol to the water in the radiator, you are forming hydrogen bonds between the water and the ethylene glycol, and because of that process, you are lowering the freezing point, which is why it's called antifreeze, and also you're raising the boiling point of that solution. Alright, now we'll talk about particles in solution. A solute that is a non-electrolyte will dissolve as a molecule. We've talked about this earlier. Whereas a solute that is a strong electrolyte will entirely break up as ions. So for example, the solute in antifreeze, ethylene glycol, C2H6O2, is a non-electrolyte, so when it dissolves in water, it just dissolves as an aqueous molecule. So 1 mole of ethylene glycol in a liquid form, when it's dissolved in water, will just become 1 mole of aqueous ethylene glycol. It doesn't break up at all. So that's why it's a non-electrolyte. An example of a strong electrolyte that we've talked about previously, sodium chloride, NaCl. When that's in water, it will completely dissociate. So you have the sodium ions, which are positively charged, and you have the chloride ions, which are negatively charged. So this breaks up completely compared to ethylene glycol, which doesn't break up at all. But when you're comparing the number of moles in that solution as it breaks up, 1 mole of sodium chloride will break up into 1 mole of sodium ion and also 1 mole of chloride ion. You don't get a 50-50 split. You don't get half a mole here and half a mole here. You get 1 mole of each individual component of that solution. So 1 mole of sodium chloride in solid form will actually give you 2 moles of particles in solution because you have 2 ions being formed here, and here. Alright, now we'll move on to osmosis. Hopefully you remember this concept from general biology. This is the movement of water across a semi-permeable membrane. And here's an example of how that would look here. This is a beaker, and it's divided in half by the semi-permeable membrane. You have these yellow circles here are the solute. In this example, they're going to be sucrose. And when you have a higher concentration of solute on this side of a membrane versus this side, water will always rush toward the higher concentrated side in order to balance everything out. That's a big theme in nature, is to become more stable, become more balanced. So there's too much more sucrose on this side of the membrane than there is here. So water will leave here to go across the membrane here to balance it out. And when that happens, this water level on this side will drop, and the water will keep moving until there's an equal concentration on both sides of the membrane. A nice equilibrium is what nature is always striving for, a balance. We'll move on to osmotic pressure. Now the osmotic pressure is equal to the pressure that would prevent the flow of additional water into the more concentrated area side. And of course the osmotic pressure is greater as the number of dissolved particles increases. In order for this water to be slowed down from going from here to here, the osmotic pressure needs to be higher, basically to put the brakes on the flow of water across the membrane into the higher concentrated side. Alright, next we'll talk about solutions that are either isotonic or hypotonic or hypertonic. And those concepts are very important when it comes to biochemistry in particular. Because cell membranes in biological systems, like human cells, are semi-permeable, osmosis is an ongoing process. It doesn't just happen once and it's over. It's constantly going on. You have water moving into a cell and also water moving out of a cell. So the solutes in biosolutions like blood or lymph or interstitial fluid or blood plasma all exert some type of osmotic pressure. And most IV solutions that are used in hospitals are going to be isotonic solutions. And iso means equal. Isotonic solutions exert the same osmotic pressure as the body fluids. Now solutions can either be isotonic, hypotonic, or hypertonic. And those terms reference the concentration of the solute versus the solvent. And what you want is an isotonic solution here. And the common example that's used to represent these three situations are red blood cells, as what these three are. In a normal, balanced situation, there's no net movement of water into the red blood cell or out of the red blood cell. There's water moving in and out, yes, but the net movement is zero. The amount that goes in equals the amount that goes out. So there's no change in volume there. So the red blood cells remain their normal shape and are able to function. Now, if a red blood cell were put into a hypotonic solution, the blood cell fills and fills and fills with water until it eventually pops like a balloon. There's only so much you can fill any kind of structure. It will eventually rupture. And when that happens, the cells are dead and they can't function. And the opposite of this is a hypertonic solution. The red blood cells will shrivel or crenate. By doing so, they become non-functional. So this is the situation that you do want, isotonic, but you don't want either one of these. In both of these situations, these cells will eventually become non-functional and then die. Right, in the hypotonic solution has a lower solute concentration than the red blood cells. Hypo always means lower or less than. So there is less solute in the solution than there is in the cell. And the way you can predict what direction these cells or the water moves, the water will flow toward the hypertonic side. So in this situation, the cell is hypertonic, the solution is hypotonic. So water will leave the solution and enter the cell. But when that happens, the cell will fill up with water and eventually will pop like a water. And that process is called hemolysis. Hemo because it's a blood cell, and lysis means to rupture or to break open. Okay, the opposite of that situation, hypertonic. The solution has more solute than the red blood cells do. Water will leave the red blood cells and enter the solution. But when that happens, these cells will shrivel up, a process that's called crenation. And when that happens, the cells become non-functional and then they will die. This is the same thing as if you ever were to put salt on a snail or on a slug. There's more salt outside of that snail's body than there is inside of that snail's body. So water will leave the snail in order to balance it out. But when that happens, the snail will shrivel up and then die. It's the same process here. So the situation that you do want the red blood cells in is an isotonic solution. There's no net movement of water. So the cells are able to stay their normal shape and be able to function normally. If they're a hypotonic solution, they will eventually be ruptured and they can't work. If they're in a hypertonic solution, they will eventually shrivel up and then die, and then they can't work. Now we'll move on to the process of dialysis. In dialysis, you have solvent and small solute particles will pass through an artificial membrane, basically functioning as an artificial kidney. The larger particles are retained inside and are filtered out of the blood. And so during dialysis, the products that are retained are common waste products, excess water, toxins, urea, and so on. The things that your body does not need or want inside it that the kidneys would normally function or normally filter out, dialysis do that for you. Okay, in this chapter, chapter number 10, rates of reactions. Now, reaction rates for everyday processes can vary greatly in their time. A banana may only ripen in a few days, a piece of silver may tarnish within a few months, and while a person ages over the course of many years and many decades. So there are various factors that impact the rate of reaction, and we'll focus on those for the learning goal for this chapter. We'll discuss how temperature and concentration and catalysts all can affect the rate of a reaction. Molecules that are reacting to one another must collide, and they must be oriented in the proper way, and also have enough minimum energy present in order for them to react to one another and form a product. That's what these graphics are showing you. So for this example, nitrogen and oxygen must be oriented this way in order to form the product of nitrogen monoxide. If they hit each other and don't have enough energy, then nothing happens. They just bounce off one another. If they bump into each other but they're not facing the right way, nothing happens. They bounce off one another. Same thing here. If they hit each other but aren't facing the right way or aren't oriented in the correct way, then nothing will happen. Now, even if a collision does happen in the correct orientation, there still has to be enough energy there to help break the bonds and to help the reaction complete and to form a product. So there are three conditions that are needed for any reaction to occur. The molecules must have a collision, first of all. They must be oriented in the correct way. And there has to be a sufficient level of energy for the product to be formed. And that level of energy is called the activation energy. It is the minimum amount of energy needed to break bonds between atoms of the reactants and to therefore form products. These two reactants, nitrogen and oxygen, oriented in the proper way, the energy is sufficient enough, this activation energy, then you will get the products. If this is too low, then nothing happens. Now, the speed of a reaction or the rate of a reaction is determined by either the amount of reactants that are used over a certain amount of time or by the amount of products that are formed over a certain amount of time. So here's a mathematical way to write this. The rate of reaction is equal to either the change in concentration of a reactant or a product over a set amount of time. There are various factors that can impact the rate of a reaction. Reactions that have lower activation energies will go faster than reactions that need higher activation energies, which just logically makes sense. If you don't need as much energy to complete a process, then it will happen much faster. For any reaction, three main factors that can affect its overall rate: a change in temperature, a change in reaction concentration, and also by adding a catalyst. And the first one we'll talk about is temperature and how it has a role with the rate of reaction. At higher temperatures, the reactant molecules will be hitting each other more frequently because they're moving much faster. So if you have particles moving faster, they're going to hit each other harder and with more energy. An increase in temperature will cause a reaction to happen faster because you have an increased kinetic energy. And for every 10 degrees Celsius of increase of temperature that you have, the reaction rate will approximately double. Another factor that can impact the rate of reaction is the concentration of reactants. If you have more reactants present, more reactant molecules present, the higher the possibility that they will collide with one another and make the reaction happen faster. If you have, say, just one blue ball and one red ball, not much possibility for reaction. But if you have two hitting with one, you have more possibility here. If you have two here and two here, you have much more possibilities for collisions. So the more reactants you have present, or the higher the concentration of the reactants, the faster the rate of the reaction will go. Another factor that can impact the reaction speed is something called a catalyst. A catalyst is something that will speed up a reaction, and it does so by lowering the activation energy. And like we talked about before, if something only needs a lesser amount of energy to happen, it will happen much faster. The good things about a catalyst are a catalyst is never consumed in the reaction. It's always going to be there, and it doesn't get changed. So it's there to be used over and over and over again. By lowering the activation energy, increasing the rate of speed for that reaction. Alright, next we'll move on to chemical equilibrium. Now in most chemical reactions, reactants are not completely converted to products because a reverse reaction can take place in which the products collide to form reactants. This is called a reversible reaction, and it's indicated by these double arrows. If a reaction is going this way, it's called a forward reaction. If it goes from here back this way, it's called a reverse reaction. These reactants combine together to form this product. This will break down and form these, and it goes back and forth, forward and backward, forward and backward. So when a reaction will proceed both in the forward and backward direction, it's called reversible. As these reactants collide, hydrogen and iodine, the forward reaction will complete. So what you're really getting with a reversible reaction is a synthesis reaction going forward, and then a decomposition reaction going backwards. And it goes back and forth, back and forth. Now as the reaction progresses, the rate of the forward reaction will get slower and slower and slower, and then the rate of the reverse reaction will increase. And then when you're at an equilibrium, the rates of both forward and reverse reactions are equal. Neither direction is faster or slower than the other. They're both at an equal rate. That's what's happening here. When you progress with the reaction, the forward direction will get a little bit slower, and the backward direction gets a little bit faster until they meet at an equilibrium. Equilibrium is reached when there are no further changes in the reactant or product concentration. For this chart, it has the progress of reaction over here versus the concentration. So reactants will get a little bit less and less in the very beginning, and the products will get higher and higher in the very beginning, and then they get to a point where they're at an equal level, an equilibrium. Alright, next we'll talk about equilibrium constants. Equilibrium constant for a reversible chemical reaction multiplies the concentrations of the products together and then divides that total by the concentrations of the reactants multiplied by each other. And this is a generic way of how it's written. A, B, double arrows, C, and D. In this generic form, C and D are the products, and then A and B are the reactants. And this is a way that you would write this mathematically and how you would solve problems when it comes to this. The equilibrium constant is represented by K and then lower subscript C. So constant, the K for equilibrium. The concentration of this product raised to the power of the coefficient in a balanced equation. That concentration multiplied by concentration of the other product raised to that power. All that divided by the concentration of the reactant A raised to the power of its coefficient multiplied by the concentration of reactant for B. A general way to think about this is the concentration of the products divided by the concentration of the reactants. That's using a generic letters to represent the products and reactants. Here's one using a real formula, and then on the next slide we'll get into real numerical values. So for our reaction we've talked about, H2, hydrogen, plus iodine will yield 2HI. If you're finding the equilibrium constant using this equation, the concentration of the product, the main product here, raised to the power of its coefficient, 2, because there are 2 of these. And you can think of this as the concentration of HI multiplied by the concentration of another HI, that's why it's HI squared, divided by the concentration of this reactant. And it has no coefficient, so it's raised to the first power. That concentration multiplied by the concentration of the second reactant, raised to its coefficient. That's how you would write it. And now here's how you would solve it with real numerical values. Say for the equation we just looked at, the concentration of hydrogen is 0.10 molar, the concentration of iodine is 0.20 molar, and the concentration of HI is 1.04 molar. So now you're just plugging in the values for the equation that we just wrote. Over here it was a concentration of HI squared, so this value squared, all that divided by concentration of hydrogen, 0.10 molar, multiplied by the concentration of iodine, the other reactant, 0.20 molar. You do all this math and you get the value of 54. So a reaction at any specific temperature can only have one value for the equilibrium constant. The temperature does not change equilibrium constant. It may change the rate of the reaction, but temperature does not impact the equilibrium constant. Alright, given another reaction here, 2SO2 gas plus oxygen gas will give you 2 moles of SO3. For this reaction, your result is a higher amount of product here than there was in the first experiment that we just saw. So this high amount of product will give you a very large value for the equilibrium constant. So the values of Kc can be either really big or really small. It just depends on if equilibrium is reached with more products than reactants or more reactants than products. The size of that equilibrium constant doesn't change how fast the equilibrium was reached. It's just a comparison of the concentrations of reactants versus products. Alright, that experiment we just looked at had a value of Kc that was high. Now we'll talk about one where the value of Kc is low. In this reaction here, nitrogen gas plus oxygen gas gives you 2 moles of nitrogen monoxide. At equilibrium, you'll have a very small amount of product made. You'll have a higher amount of reactants still present. So the fact that you have a high amount of reactants present gives you a value that's going to be very low for Kc. Alright, there are going to be a few reactions that have a Kc value that's going to be close to 1, but that usually means that their concentrations of reactants and products are going to be very close to equal to one another. The value for Kc is approximately 1. The concentrations of reactants and products will be fairly close together, or fairly equal, and you'll have a moderate reaction. If you have a value for Kc that is small, you'll get mostly reactants, and you have a very little reaction take place. If you have a value that's going to be large for Kc, you'll get mostly products. What you'll get is a reaction that is essentially complete, because you have very little reactants left and a whole bunch of products made. Reactions with large Kc value will have mostly products, and reactions that have a small Kc value will have mostly reactant. Here's some examples of reactions and their Kc values, and whether or not you'll get more products versus reactants. So for this reaction here, fairly large value, 2 times 10 to the 11th power, so that's going to be mostly products. This reaction, another high value, 1.1 times 10 to the 7. High values, it's going to be mostly products. And the last two examples here, fairly smaller values, 1.2 times 10 to the negative 2, which is equal to 0.012. That's a small number, so it's going to have, you'll have mostly reactants in that reaction. And then 2 times 10 to the negative 9, that's an even smaller value, so you'll have mostly reactants for here also. Small value, reactants. If you have high Kc value, you'll get mostly products. Alright, now we'll move on to what's called Le Chatelier's principle. When the conditions of a reaction at equilibrium are changed, the forward and reverse reactions are no longer equal, because there's been a change added to that reaction. So Le Chatelier's principle states that when a stress is placed on a reaction at equilibrium, the system has to respond by changing the rate of either the forward or the reverse reaction in a way to relieve that stress. And here's what I mean by that. Let's say you have 2 tanks of water. You're at an equal level, so these are at equilibrium. Let's say that you add water to tank A, so you are changing the system. It's not at equilibrium anymore. There's a stress added here. So what that does is, in order to get back to an equilibrium, this reaction will be forced this way in order to relieve that stress. So now when the water levels get back at the same level, they're now at equilibrium again. But this change, by adding water to tank A, increases the rate of the forward reaction. So this is Le Chatelier's principle, adjusting the rate of either the forward or reverse reaction to negate the addition of the stress to that system. And here's some examples of Le Chatelier's principle with real equations. So going back to our original reaction we've talked about for this chapter, hydrogen gas plus iodine gas gives you 2 moles of HI. If you add reactants to this reaction at equilibrium, that will drive this rate of reaction toward the products. Same thing with the water tanks. You're adding more reactants here, so more products will have to be produced in order to balance out that stress that's added. So if you add any reactant, if you add more hydrogen here, that will force the reaction rate toward the products. If you add more iodine gas, that will force this rate of reaction toward the products. The forward reaction gets increased, driving the reaction toward the product. This graphic is just an illustration of that last equation, nitrogen plus iodine gas to HI. Now what happens if you remove a reactant? So let's say you take away hydrogen here. If this is at equilibrium and you take either one of these away, that's going to drive the rate of reaction in reverse toward the reactant, because you are removing a part to keep this balanced. If all this is at equilibrium and it's balanced, if you take one of these parts of it away, in order to neutralize that effect of taking away a reactant, this reaction, the reverse reaction, needs to increase. So removing a reactant will drive the reaction toward the reactants. Alright, what happens if you add product to this equilibrium reaction? If you add product here, that's going to drive the reaction toward the reactants, because you're adding a stress to the system here. In order to negate that, more reactants have to be made to balance it out. So it will drive it this way. What happens if you remove a product? Again, if these are at an equilibrium amount, if you remove some of this product, the rate of reaction will shift toward the product, because more product has to be made to balance out that negative stress, that loss of the product. So if you remove products, the rate of reaction will increase toward the product to make sure that more is made. Alright, now we'll talk about the effect of a catalyst on equilibrium. Now, catalysts will speed up the reaction by lowering the activation energy. So this will increase the rate of the forward and reverse reactions. So by increasing this rate, the time it takes to reach equilibrium is shorter, but the same ratios of the reactants and products are still there. So the catalyst will increase the rate of the reaction and it will lower the activation energy, but it does not change the equilibrium mixture of products versus reactants. Alright, now we'll talk about how the volume of a gas can impact the equilibrium reactions. And it's important to remember that when we're talking about increasing or decreasing volume, these kinds of reactions, we're only talking about gases. Alright, so if you change a volume of a gas in a mixture, that will change the concentration of those gases, either making it go up or making it go down. So for our first example, carbon monoxide plus oxygen will give you carbon dioxide. This is a reversible reaction. Let's say that we decrease the volume of the gas. When you decrease the volume of the gas, that'll make the concentration go up, and the overall system will shift in the direction of the smaller number of moles. So what you're looking for here is you're counting the number of moles on either side of the reaction. So for here, 2, and that's understood 1. So this side of the reaction has 3 moles. This side only has 2 moles. So when I say that the system is shifting toward the direction of the smaller number of moles, this reaction, if you were to decrease the volume of the gas, will be shifted toward the product, carbon dioxide, as a way to compensate. Again, we're only talking about gases. Carbon monoxide gas, oxygen gas, carbon dioxide gas. Sometimes you may get questions like this, where some of the reactants or some of the products are liquid or solid or aqueous, and you cannot count those moles when you are trying to determine what way the reaction will be driven, either forward or backward. But for here, so for this reaction, there are 3 moles on this side of the reaction, 2 plus the 1, and only 2 on this side. So if you decrease the volume of the gas as equilibrium reaction, you will cause the concentration to go up, and therefore drive the reaction toward the side with the smaller number of moles. In this case, it would be toward the product, carbon dioxide. Now for the opposite of that, if you increase the volume of gases at a equilibrium reaction like this, you will decrease the concentration of the overall gases. So therefore the system will shift toward the direction of the larger number of moles to compensate. Still have the same reaction, 2 and 1, so 3 moles over here and 2 over here. So if you increase volume, you will cause the concentration to go down, and therefore it will be shifted toward the direction of the larger number of moles, which would be over here toward the reactant. Alright, now we'll talk about how temperature changes can impact equilibrium reactions. First we'll talk about decreasing temperature. And we'll talk about decreasing temperature in an endothermic reaction. If you decrease temperature in an endothermic reaction, the system will respond by shifting the reaction toward more heat. So the shift will go toward the reactants, increasing the heat in the system. So this example here, nitrogen gas plus oxygen gas plus heat will give you 2 moles of nitrogen monoxide. But if you decrease temperature in an endothermic reaction, the shift will be toward these reactants, adding more heat to the system. So for the opposite of that, if you increase temperature in an endothermic reaction, this will cause the system react by shifting the reaction to remove heat. So the reactions will shift toward the products, and thereby using up more heat. Same reaction, nitrogen gas plus oxygen gas plus heat will give you 2 moles of nitrogen monoxide. If you increase temperature in an endothermic reaction, this reaction will be shifted toward the products, using up more heat. Those two were endothermic reactions. Now we'll talk about exothermic reactions. Let's say that you are decreasing the temperature in an exothermic reaction. The system will respond by shifting the reaction toward more heat. So the reaction will be toward the products, increasing the heat used in the system. So for this reaction here, SO2 plus oxygen will give you SO3 gas plus heat. So if you decrease the temperature in this exothermic reaction, the reactions will be shifted toward and driven toward the products, increasing the heat. And the opposite of that, if you increase temperature in an exothermic reaction, the system will respond by shifting toward the reactants, thereby removing more heat. So same reaction, SO2 gas plus oxygen gas, SO3 gas plus heat. If you increase the temperature of this exothermic reaction, these reactions will be driven toward the reactants, thereby removing heat. Alright, in this chapter, chapter number 11, we will cover acids and bases. Now, as you see in this image here, a standard soft drink will contain acids such as phosphoric acid, H3PO4, and also carbonic acid, H2CO3. This is a very common example of an everyday acid that we all encounter. Now, there are different types of acids. The first one we'll go over, arrhenius. These types of acids will produce hydrogen ions, H+, when they dissolve in water. So the example that you're given, HCl, hydrochloric acid, dissolving in water will give you the hydrogen ion, which is positive, and also the chloride ion, which is negative. And these types of acids are also electrolytes because they produce hydrogen ion in water. They tend to have a very sour taste to them. They also will corrode some metals, and they will turn a blue litmus paper red. And that's a good indicator that the substance that you're working with is an acid. Moving on to naming acids. Acids with a hydrogen ion and a nonmetal, or the cyanide ion, the Cn with a -1 charge, will be named with the prefix hydro, then end with the ending IC, or ic, acid. So for example, HCl, hydrochloric acid. Now, acids with a hydrogen ion and a polyatomic ion are named by changing the end of that name of the polyatomic ion. If the polyatomic ion ends with 8, it will be changed to the ending IC. This ion here, chlorate, if you add a hydrogen ion to it, you get chloric acid. If the ending of the polyatomic ion is ITE, that gets changed to OUS, and then acid. So for this example, this is chlorite. So if you add a hydrogen ion to it, you get chlorous acid. So all you're really doing is changing the ending, either from 8 to ic, or ite to us. Here's a table of some common acids and their anions. The acid HCl, hydrochloric acid, anion of course would be chloride, hydrobromic acid. All these are very, very common ones that you will encounter in any kind of chemistry class or chemistry lab. Alright, now we'll move on to a type of base, arrhenius base. These will produce hydroxide ions, or OH-, when they dissolve in water. They have a chalky or a bitter taste to them. There's a B for bitter, B for base. Is a good way to keep that straight. These are also electrolytes because they produce hydroxide ions when they're in water. They will have a very slippery feel, a very soapy feel to them. They will turn litmus paper blue and the phenolphthalein indicator pink. The example that you're given here, sodium hydroxide, when it dissolves in water or dissociates in water, will give you the sodium ion, Na+, and also the hydroxide ion, OH-. So this type of base will produce a cation and then also the hydroxide ion. Now when it comes to naming bases, these are named as hydroxides. So NaOH, sodium hydroxide, KOH, potassium hydroxide. So all you're really doing is naming the first part of the compound and then adding hydroxide at the end. So barium hydroxide, aluminum hydroxide. Alright, next we'll move on to a different type of acid and base. These are the Bronsted-Lowry acids and bases. And according to this theory, an acid is a substance that will donate a hydrogen ion, H+, and a base is a substance that will accept a hydrogen ion. So this example here, hydrogen chloride, adding water to that, you get hydronium ion, H3O with a plus, and also chloride ion. So in this reaction, the hydrogen chloride will be considered the acid, because it is donating the hydrogen to join up with water to form hydronium ion. And then the base would be the water. It is accepting the hydrogen ion in this example. Now in the reaction of ammonia and water, NH3, ammonia, will act as the base because it accepts hydrogen ion. And water will act as an acid because it donates that hydrogen ion. So here's the reaction. Ammonia, NH3, plus water will give you ammonium ion, NH4 plus, and also hydroxide ion, OH minus. So in this reversible reaction here, water is acting as the acid. It is donating a hydrogen ion here to join up with the ammonia to form ammonium ion. So the ammonia would be considered the base because it is accepting a hydrogen ion. And because the nitrogen atom of the NH3 has a stronger attraction for hydrogen ion than oxygen would, water will act as an acid. That's why it's donating the hydrogen ion. Alright, now we'll move on to substances that are considered amphoprotic or amphoteric. Now these terms are related, but they're not the same thing exactly. They're not interchangeable terms. If a substance is considered to be amphiprotic, that means it's able to accept or donate a hydrogen ion. If a substance is considered to be amphoteric, that means it can act as either an acid or a base. So they are related, but they're not exactly the same thing. So for water, which is the most common amphoteric substance, it acts as an acid or a base depending on what it is reacting with. So water will donate a hydrogen ion when it reacts with a stronger base, and water will accept a hydrogen ion when it reacts with a stronger acid. So it just depends what the other reactant is will determine how water will behave. Alright, here's a good summary of water and how it could act in either way. If water accepts another hydrogen, it becomes H3O+, that is acting as a base. If it donates a hydrogen ion, it becomes hydroxide, OH-, and is acting as an acid. So it just depends on what it's interacting with will determine how it behaves. Alright, now we'll move on to the strengths of acids and bases. Now, weak acids only partially dissociate in water. Anytime you see the term weak, we talked about strong electrolytes, weak electrolytes. Anytime you see the word strong, that means that substance will dissociate or break up completely. If you see the term weak, weak electrolyte, weak acid, weak base, that means they don't dissociate all the way. An example of that, hydrofluoric acid, HF, is the only halogen that will form a weak acid. So when this is dissolved in water, most of it will stay together, but you still get some ions breaking off. So it does form some acid, but a very weak acid. But for the most part, HF will stick together. A strong acid will completely ionize 100% in an aqueous solution. So hydrochloric acid, nitrogen chloride, gas plus water will give you hydronium ion and chloride ion. This is completely breaking up. That is a strong acid. But a weak acid will only dissociate slightly in water to form just a handful of ions, and for the most part it will stay together. So H2CO3 combined with water, you'll get some hydronium, but then you still get the bulk of what you get is HCO3 minus. So strong acid will break up completely, weak acid not break up all that much at all. Alright, for strong acids, in water, the dissolved molecules of a strong acid will break up completely, and you see the letters here, HA. H would be the hydrogen part of the acid, and A is a generic placeholder for the anion. So like we saw on the last example, or the last page, HCl plus water gives you hydronium ion plus chloride ion. So you get equal splitting here of those two ions. So over here, the strong acid HI, hydrogen iodide, plus water, it'll give you a nice even split. That is a strong acid. For weak acid, only a few molecules will dissociate. So the concentrations of the hydronium ion that are produced in an anion are really, really small. So for example, we talked about a few slides ago, HF. When that's dissolved in water, you get a great majority of the HF still intact, but you still get some ions produced. So this is a very weak acid. All right, in this table, you're shown the relative strengths of acids and bases. The first part of the table have the strong acids. As you get further up, the stronger they get. So hydroiodic acid is stronger than, say, nitric acid. The rest of this table are the weak acids here. And again, as you get from here going upward, you'll get stronger and stronger. And on this side of the table, you are given the conjugate base for each acid. The conjugate base is basically what is left over after the hydrogen ion leaves the acid. This example, hydrobromic acid. When you break apart this compound, if you take away the hydrogen ion part of it, you're left with the bromide ion. So its conjugate base is what's left over when you break up the acid. And as you get further down in the table, the stronger the bases get. The hydroxide ion would be a much stronger base than an iodide ion would be. All right, now I'll move on to strong bases. And these are strong electrolytes that are formed from the metals of groups 1A and 2A, and also include this list of compounds: lithium hydroxide, sodium hydroxide, potassium hydroxide, barium hydroxide, and so on. And because they're strong bases, they will completely dissociate in water. And these are found in very common household products, such as cleaners and things you'd use to unclog a drain. So, say Windex, Drano, Cheer, all those will have some very strong bases. Now, weak bases are weak electrolytes, and these will be very poor acceptors of hydrogen ions because they produce very few ions in solution. And a good example of a weak base is ammonia. So you have ammonia being dissolved in water. We'll give you ammonium ion a little bit and then hydroxide a little bit, but for the most part NH3 will stay together. So again, anytime you see the terms strong and weak, whether it be in relation to an acid or a base or electrolyte, strong is always a reference to it being able to completely dissociate in water, and weak means it doesn't completely dissociate. All right, here are some common examples of strong and weak bases. Strong bases: lithium hydroxide, sodium hydroxide, and this whole table here. Some bases that are found in household products, both strong and weak: window cleaner, Windex, ammonia, bleach, laundry detergent, toothpaste is actually has a form of a weak base inside it. Baking soda, laxatives, those are all have a form of a weak base inside. And a strong base that you would find in a household product: oven cleaner, drain cleaner. All right, now we'll move on to dissociation constants for acids and bases. And what you see here is these are the ball and stick models of the compounds right above it. So this right here represents this ball and stick model, which is the same thing as this, HCHO2. And this ball and stick model is the same thing as CHO2 minus. And what the dissociation constant is a expression to show how much an acid or a base has been broken up within a solution. And those values will vary depending on each acid or each base and what they're being dissolved in. So it's a reflection of relative concentrations of the ions produced compared to the compound that hasn't dissolved yet. Dissociation of a weak acid: when a strong acid dissociates or breaks down in water, it is essentially a completed process. There's nothing left to do. So this is not considered to be an equilibrium process. But for weak acids, they only partially dissociate. So an example that you're given here: formic acid being dissolved in water will give you hydronium ion and formate ion. Because remember, this is a weak acid. It will not fully break apart, so you'll still have mostly formic acid left over, with some hydronium ion produced and some formate ion produced. And next we'll talk about the dissociation of water. Now this doesn't happen all that often, is fairly rare. But what you have is water molecules combining with each other and then quickly breaking down before they rejoin and form water again. So this is a reversible reaction. So you have two molecules of water here. They briefly will combine, forming hydronium ion, H3O+, and also hydroxide ion, OH-. But then these two quickly will join together and form water again. So this process is not all that common, but you are still getting technically water being broken up and dissociated. For pure water, the ionization of water molecules produces small but equal amounts of both hydronium and hydroxide ions. And we look at the concentrations of both of those in pure water, you get this molarity, 1 × 10 to the -7. So they are both equal to each other. So pure water is a neutral compound. That's what it's showing you here. Hydronium ion and hydroxide ion. In pure water, is a completely neutral solution. Now, acidic solutions. So adding an acid to pure water will increase the concentration of the hydronium ion in that solution. So this will cause that concentration to go up. It will also cause the hydroxide concentration to go down. So when you add an acid to pure water, you are forming an acidic solution. This concentration goes up, this concentration goes down. And the opposite of that will be true for basic solutions, also known as alkaline solutions. When you add a base to pure water, that will increase the hydroxide concentrations. It will also cause the concentration of hydronium to go down. This solution would be considered a basic solution or an alkaline solution. Hydroxide concentration goes up when you add a base, and hydronium will go down. Alright, here are the last three charts all on one. We start off with a pure water solution, a neutral solution. Concentrations are equal to each other. When you have an acidic solution, hydronium ion will be much higher at concentration. When you have a basic solution, the concentration of hydroxide ion will be higher. Alright, in this table you have the concentrations and the molar concentrations of various solutions. So for neutral, they'll be equal. 1 times 10 to the negative 7 molar for both. If it's an acidic solution, that value will increase, become more positive. So instead of being 1 times 10 to the negative 7 molar, you get an example of, say, 1 times 10 to the negative 2 molar. That's getting more acidic in solution. Same thing here. You are getting, because of the higher concentration, you are increasing this value. For solutions that are basic, you're increasing the hydroxide concentrations, so this value will go up. Instead of being times 10 to the negative 7, 10 to the negative 6, negative 5, negative 4, and so on. Now the way to measure the strength of acids and bases is what's called a pH scale. Now the pH scale ranges from a value of 0 to 14. A completely neutral solution like water is dead in the center at a pH of 7. Anything less than that is acidic. So 0 to 6 is acidic. And higher numbers, 8 to 14, are basic. And here's that sliding scale from 0 to 14. Like I said, the lower numbers will be acidic. The lower the number, the higher the strength in the acid. So an acid that has a pH of, say, 1.6, like gastric juice, is stronger of an acid than, say, coffee with a pH of 5. Really, really strong acids here. You get a little bit weaker, a little bit weaker, a little bit weaker. 7, which is neutral. Then going up, you get, these are weak bases, a little bit stronger, a little bit stronger. And the strongest bases are on the higher end. The extremes on either end are the strong acids or base. The strongest base would have a pH of 14. And you get a little bit weaker, a little bit weaker, a little weaker, really, really weak, and then neutral. So strong base here, strong acid here. And there's some common examples of what would be represented by various pH levels. Say a carbonated soft drink would have a pH of 3, oranges 3.5, coffee 5, urine is 6, so it's a very weak acid. Dealing with bases, bile 8.1, seawater 8.5, bleach 12, and sodium hydroxide 14. A very, very strong base. Right, because the pH scale is not just values of 1 or 0 to 14. It's a mathematical scale. It is a scale based on logarithms. So a change in 1 pH unit is actually a tenfold change in strength of acidity or strength in the base. So even though the numbers sound small, say a difference between a pH of 2 and a pH of 3, that's a tenfold difference in strength. Then going from 3 to 4, that's another tenfold difference in strength. Even a small change in a pH value indicates a fairly strong change in strength. Alright, move on to reactions of acids and bases. Gastric acid, the acid found in your stomach, contains hydrochloric acid, which is incredibly strong. And this is made by the parietal cells that are found in the stomach. For hydrochloric acid, a pH reading of about between 1 to 2. And this is so strong it can give you a chemical burn if it touches your skin. So it's incredibly strong, which is what you would want for your stomach to help break down the food that you're eating. So as food enters the stomach, this hydrochloric acid is produced by these special parietal cells until the pH gets lowered to about 1.5 to 2. That's also why if you've had heartburn before, that's why it burns so bad, because you have the stomach acid that should be contained within your stomach leaking back into your esophagus. Right here. So that's why it's called heartburn. It actually feels like your heart is burning, but what's really happening is your esophagus is being burnt by the hydrochloric acid. Move on to reactions of acids. Now, acids will react with metals to produce salt and also hydrogen gas. And acids will react with bases to produce salt and water. And acids will also react with bicarbonate and carbonate ions to produce carbon dioxide gas. And when I say salt, I don't mean table salt, sodium chloride. I mean the generic definition of a salt. So a salt is a ionic compound that does not have hydrogen ion as a cation or hydroxide as the anion. Here's some common reactions of acids reacting with metals to produce hydrogen gas and also the salt of that metal. Potassium plus hydrochloric acid will give you the salt of potassium chloride and then hydrogen gas. So this is the salt, not the compound salt, but a salt as a class of compounds, because there's no hydroxide as the anion or hydrogen ion as a cation. The metal zinc, when it reacts with hydrochloric acid, it gives you zinc chloride and also hydrogen gas. This would be the salt here. When you have acids reacting with carbonates and hydrogen carbonates, this will produce carbon dioxide gas and water and also a salt. So hydrochloric acid here reacting with carbonate will give you carbon dioxide gas plus the salt, calcium chloride, and also liquid water. The acid hydrochloric acid reacting with bicarbonate will give you carbon dioxide gas, the salt of sodium chloride, and then water. Alright, now we'll talk about when acids react with hydroxides, you'll get what's called a neutralization. In this kind of reaction, you'll get an acid reacting with a base to produce water and also a salt. And the salt formed is the anion of the acid and a cation from the base. For example, a very strong acid, hydrochloric acid, reacting with a very strong base, sodium hydroxide, will give you the salt of sodium chloride plus water. So the anion from the acid here, and then a cation from the base. Alright, now we'll briefly talk about a very well-known indicator when it comes to chemistry labs, and it's called phenolphthalein. Now this is used to indicate if a reaction has completed or not. And depending on what type of solution it's in, it will be a different color. So if phenolphthalein is in a solution that is acidic, it will be colorless. If it's found in a solution that has a pH of 8 or higher, it turns to pink. So this is a good indicator of a basic solution. Alright, now we'll talk about buffers. When you have either an acid or a base added to water, you will change the pH of that water dramatically. Buffer solution, what they do is they maintain the pH. So the pH doesn't change all that much whether or not an acid or a base are added. So for example, if you have a beaker filled with plain water, if you add an acidic solution, the pH will go down. So instead of being 7 like water normally is, if you add an acid, the pH will become more acidic. So it will go down to say 4. If you add a base, instead of being neutral at 7, it will go up, say to 10, 10.5. But with a buffer solution, when you add an acid, you get a very slight change, going from 7 to 6.9. If you add a base, you get a very small change the other way, 7.1. So buffers are used to minimize the impact of an acid or a base. And something like this is critically important when it comes to your body and digestion, for example. We talked about before on the previous slide how the pH of the hydrochloric acid in your stomach is incredibly strong, a pH of, say, 1 to 2. You can't have that kind of material entering the first part of the small intestine at that strength. It will just tear through the small intestine. So you have a variety of other chemicals, other enzymes, other buffers that are added to it to help neutralize it. So what basically happens is you have a very strong base added to that strong acid to help minimize the effect. Otherwise, you'll get ulcers within the small intestine. And buffers work because they resist the changes in pH from the addition of either an acid or a base. So in the body, they will absorb the hydroxide ions or the hydronium ions from food or from other cellular processes, various enzymes, various proteins that are used. Now this is important because it helps maintain the proper functioning of blood in various cells. The pH of your blood can only handle a very small window of change in pH. The pH of your blood should only be between 7.35 and 7.45. If it gets lower than that, you're going to have serious problems. If you have a pH higher than that, you're going to have some serious problems. So you have these various buffer systems that are used to maintain a really tight window of pH that your blood can handle. Because if you have a change in pH of the blood, this will affect how well you take in oxygen to the cells. Now the components of a buffer solution will contain a combination of the acid-base conjugate pairs, a weak acid, and then a salt of its conjugate base, such as these. And we'll have equal concentrations of the weak acid and its salt. Now in the buffer with acetic acid, and there's a formula here, and sodium acetate, the salt produces acetate ions and sodium ions. That's what you get here. The salt is added to provide a higher concentration of the conjugate base, which is more than what you get normally from the weak acid alone. Here's that reversible reaction here. So acetic acid plus water gives you acetate ion plus hydronium ion. Okay, now we'll start our last chapter of this chemistry crash course, chapter number 12, Organic Compounds. Organic chemistry is the study of carbon compounds. For anything to be considered an organic compound, it must contain carbon. See, organic compounds such as vegetable oil contain carbon and hydrogen and are not soluble in water. As you see in this picture here, you have vegetable oil being poured into a pitcher of water. And when this will settle out, the vegetable oil will be here on the top layer because it's not soluble in water, so it will form a film on top of the water. Alright, an organic compound will always have carbon and hydrogen atoms. There's no limit in how much they can have, but if carbon is found in the compound, it is considered to be organic. And they may also have other nonmetals like oxygen or phosphorus or nitrogen or even a halogen. Common products that you'll find organic compounds: gasoline, medicines, plastics, shampoos, perfumes. And we organize organic compounds by their functional groups. These are how atoms are bonded in a certain way. If they're bonded in a certain way, then they get particular names, like alcohols or aldehydes or ketones and so on. And compounds that are found in the same functional group have similar physical and chemical properties. Some properties of organic compounds. These organic compounds will typically have covalent bonds. They will have low melting and low boiling points. They will be very flammable and will undergo combustion, and they are not soluble in water. The picture we saw earlier, a sample of vegetable oil is a mixture of organic compounds that is not soluble in water. Now, many inorganic compounds have high melting and high boiling points. And inorganic compounds that are ionic are usually soluble in water, but most do not burn in the air. A very common example of a organic compound, propane, C3H8. Organic compound is used as a fuel, cookers and propane tanks, and so on. Sodium chloride, which is a salt, is an inorganic compound that's composed of sodium and chloride ion. Now we'll move on to representations of organic compounds. Now, hydrocarbons are organic compounds that only have carbon and hydrogen. That's why you have the name hydrocarbons. In organic molecules, each carbon can have 4 bonds, or up to 4 bonds. In methane, for example, CH4, you have 1 carbon atom, and it forms an octet by sharing its 4 valence electrons with 4 hydrogen atoms. And you see various ways to represent methane here. And even though they look very, very different, they all represent the same compound of methane. So for the one that's here in A, that's called the space-filling model. Letter number B, the ball and stick model, where the darker color would be carbon and the whites would be hydrogen. So 1 atom of carbon and 4 of hydrogen, so that's CH4. Letter C is where you have what's called a wedge dash model. The solid wedge, like this, is a 3-dimensional representation. This hydrogen atom here would be coming out of the screen, coming toward you, like a 3D movie would be. And if you have a bond that's dashed, like this one here, it is going behind the screen. For letter D, that is what's called an expanded structural formula. Solid lines represent individual bonds. And then for letter E, what's called the condensed structural formula. You are writing this basically without showing how all the things are bonded. So all 5 of these represent exactly the same compound, just in 5 separate ways. We'll talk a little bit more about methane, CH4. The expanded structural formula shows all of the atoms and all of the bonds connected to each atom. So again, you have the central carbon here, and then the 4 individual hydrogens, all bonded by single bonds. There's 1 line, that means it's a single bond. And again, the condensed structural formula, it shows the carbon atoms that are grouped with attached numbers of hydrogen atoms. So instead of writing it out like this, you're just writing, there's 1 carbon, 1 is understood, and then 4 hydrogens. So again, these are exactly the same thing, Just in some cases, it's easier to write it like this, and sometimes it's easier to represent how everything is bonded together. In methane, like we talked about before, carbon will form 4 covalent bonds to hydrogen. So this is considered to be a tetrahedral shape because it has 4 sides to it, and it has the bond angles of exactly 109 degrees. So if you were to take the ball and stick model here, the angles between these hydrogens are exactly 109 degrees. And a hydrocarbon is referred to as a saturated hydrocarbon when all the bonds in the molecule are single bonds. Methane would be a good example of that. All the bonds that are found in a whole compound are all just single bonds. They're not double, they aren't triple, they're all individual single bonds. So that's considered to be saturated. Alright, we'll talk about another organic compound, ethane, C2H6. Another tetrahedral carbon compound because it has 4 sides to it. It has 3 covalent bonds to hydrogen, and then 1 bond from a carbon to the other carbon, because there are 2 here. Again, these are the 5 ways to represent ethane. The space filling model here, the ball and stick model here, the 2 carbons here, and of course the whites are the hydrogen. So you have 3 covalent bonds to hydrogen from each carbon, and then the carbons are bonded together. The wedge and dash model, the structural or expanded structural formula. Again, 3 hydrogens, and then the 2 carbons bonded together, and then the condensed structural formula. And all 5 represent exactly the same thing, just in different representations. Alright, now we'll talk about a class of organic compounds called alkanes. These are formed when you have a continuous chain of carbon atoms. And they're named using a very particular system called the IUPAC, the International Union of Pure and Applied Chemistry system. There are certain rules and certain protocols that you have to follow in order to name these compounds properly. But a good indicator is they all end in the suffix ane, A-N-E. So methane, ethane, propane, all those are alkanes. If you get 5 or more carbons in a row, you start to use the Greek prefixes to indicate the name of the compound. This table here shows the number of carbon atoms that you would have in the compound, that compound's molecular formula, and then the condensed structural formula. And we'll talk about what these are here in a few minutes. So methane, CH4, ethane, C2H6, propane, C3H8, butane. Once you get to 5 or more, then you start to use the prefixes. Pence for penta for 5, like a pentagon has 5 sides to the shape. 6 would be hexa, 7 hept, 8 oct, 9 non, and then 10 dec. I'll talk a little more about the condensed structural formula. In this type of formula, each carbon atom and its attached hydrogen atoms are written as a group, and a subscript will represent the number of hydrogen atoms that are bonded to each carbon atom. So for example here, expanded, it takes up a little more room, but this shows you individual bonds. But this, CH3, is exactly the same thing as this. C, and there's 3 hydrogens. 1, 2, 3. Same thing here. CH2, 1 carbon and 2 hydrogens, 1, 2. And then the 2 bonds that are left to be formed by this carbon. And this carbon still has 1 bond left to be filled. Same thing, just 2 different ways to write it. On the table we just saw a few slides ago, you saw on the far right side the jagged lines. This is another way to represent formulas. This is called the line angle structural formula. And this shows a zigzag line in which carbon atoms are represented at the ends of each line. So for something like this, each point on that line, or each segment, is considered to have a carbon. So for this one, there would be 1, 2, 3, 4, 5, 6 carbons. This is how you would represent a hexane. The carbon atoms that are at the end of these structural formulas are bonded to 3 other hydrogen atoms, and the ones that are in the middle will be bonded to 2 hydrogen atoms. So going back to this image, propane, there's going to be 3 carbons, so 1, 2, 3. Butane, 1, 2, 3, 4. So every segment of the line represents a carbon being bonded to something. All right, now we'll talk about conformations of alkanes. Carbon atoms in the chains are connected by single carbon-carbon bonds and can rotate, so groups that are attached can move around more freely. And these can have different arrangements, and these arrangements are called conformations. So if you look at this compound here, This is the same thing as this. This methyl group here is able to actually spin around in the circle. That's why it's being shown rotating here. That can rotate and will form different types of conformations. And as they rotate around that single carbon-carbon bond, they will appear at different angles. Talk about butane next. C4H10 will rotate, but sometimes the CH3 groups line up in front of one another, and sometimes they're going to be on opposite ends of each other. There are multiple ways to write butane. Here is the expanded way to write butane. C4, then H10. Of course, all these lines represent individual bonds. The condensed structural formula for butane can be written any number of these ways. These all represent the same compound. These are all C4H10, but in different arrangements, different conformations. That would be correct. Or it can branch like this, or it can branch like that, or that. So all of these represent exactly the same thing. Everything on this page is butane. Whether you write an expanded formula like this, a condensed formula like this, or the line angle formula. Now I'll move on to what are called cycloalkanes. These are cyclic alkanes, and they will have two fewer hydrogen atoms than the open or the regular form would. And they're named by adding the prefix cyclo before the name. There's an example of propane, C3H8. This is the regular open air form. If you have cyclopropane, you have two less hydrogens. So instead of being H8, now you have H6, and they bond to each other. So you're forming a cyclic or a circle-shaped compound. That's why it's called cyclopropene. Instead of being open like this, it closes itself off. And by doing so, you're going to lose two hydrogens. Now here's some formulas and some representations of cycloalkanes. Cyclopropane, with the ball and stick model here. And what we just saw on the last slide here. If you're drawing the line angle formulas, you just write a standard triangle because it forms a triangular shape compound. For cyclobutane, it has four sides to it, so it looks like a square. And the way you would draw it is literally a square for the line angle formula. Cyclopentane, penta means five. There's going to be five sides to it. You're drawing a pentagon. And cyclohexane, you have six sides, so you draw a hexagon. All of these are the same thing. All of these are the same thing. All of these are the same thing, and then all of these are the same thing. Multiple ways to represent exactly the same compound. Now we'll talk about alkanes with substituents. When an alkane has four or more carbon atoms, the atoms can be arranged so that a side group, called a branch or substituent, is attached to that carbon chain. And the first part we'll talk about are called structural isomers. These have the same molecular formula, but with a different arrangement of atoms. Like we saw with butane a few minutes ago. We saw examples of the same compound, but written in multiple ways depending on how it was branched. So this is what we're talking about. So you still have the same number of atoms, but they're just bonded in a different order. So C4H10, butane, has two structural isomers. The straight chain, like this, where it's end to end to end, and then a branch chain, like this. Still C4H10, but that is branched here and it's not branched up here. So exactly the same thing. Now substituents are atoms or groups of atoms that are attached to the carbon chain and include alkyl or halo groups. For alkyl groups, these are groups of carbon atoms that are attached to carbon chains, and they're named in the IUPAC system with the ending YL or IL. And then halo substituents, these are halogen atoms that are attached to the carbon chain and are named with that IUPAC system by adding fluoro or chloro or bromo or iodo in front of the name. So for example, the formula name for methyl, the ending YL, methyl, CH3, and then ethyl here, propyl, because you have three, and then the formula name fluoro, chloro, bromo, and iodo. And these are some pretty common substituents that you'll find in naming chemical components. Now we'll talk about naming the haloalkanes. And the haloalkanes are alkanes with a halogen atom that replaces a hydrogen atom. And these are named by putting the substituents in alphabetical order. And you have the halo group numbered according to the carbon where it is attached to the alkane. For, say, this one, CH3 bonded to Cl. Well, that's a halogen, chlorine, so that would be chloromethane. That would be the IUPAC name. And the common name, methyl chloride. These all represent the same thing. CH3 bonded to CH2, and then bonded to bromine. Well, that's another halogen, so that would be bromoethane, or ethyl bromide. You have the halogen fluorine bonded here, so that would be fluoro, and it's attached to the second carbon in this chain. That's why it's 2-fluoropropane. and propane because it's three of these groups. It can also be called isopropyl fluoride because the fluorine is isolated. But again, that name and that name represent the same compound. Now we'll talk about melting and boiling points. Alkanes have the lowest melting and lowest boiling points of organic compounds, and they only have the non-polar bonds of carbon-carbon and carbon-hydrogen. And the alkanes will also only exhibit weak dispersion forces in the solid and liquid states. And the longer the chain is of the alkane, the higher the boiling point gets. And if you think about it, it just makes sense. The more bonds there are, the more heat will be needed to break up those bonds. So the boiling point has to go up as the size of the compound gets higher. So for example, methane is only one carbon and four hydrogen atoms here. So its boiling point is negative 164 Celsius. If you get a little bit bigger, ethane, more bonds are involved, so it's a larger structure. So now the boiling point goes up to negative 89 Celsius. Getting a little bit bigger, propane, boiling point is now up to negative 42 Celsius. Butane, getting bigger, 0.5 degrees Celsius. And then pentane, boiling point is now 36 degrees Celsius. Pentane is much larger than, say, methane. So as the size increases of the alkane, the boiling point will increase. Now for branched alkanes, these will have a lower boiling point than the straight chain version of it. These tend to be more compact, therefore reducing the points of contact between the molecules. And they do not have linear shapes and cannot line up close to one another. So as you become more branched with an alkane, the boiling point decreases. So for this one, hexane, there's going to be 6 carbons all in a row, or 6 carbon groups all in a row. Its boiling point will be 69 degrees Celsius. When it starts to branch, you have 3-methylpentane. Boiling point is now 63 degrees Celsius, so you're going down. And then here, 2,3-dimethylbutane. Boiling point is now 58 degrees Celsius. These all represent the same number of carbons in the compound. So for hexane, there are 6. 1, 2, 3, 4, 5, 6. For this compound, 1, 2, 3, 4, 5, 6. And for this one, 1, 2, 3, 4, 5, 6. So the number of carbons in all three of these examples are exactly the same. But because it's becoming more and more branched, the boiling point will go down. For cycloalkanes, these will have a higher boiling point than the straight chain version of the same number of carbon atoms. And these have limited rotation of carbon bonds. They tend to maintain a very rigid structure, so they can easily be stacked closely together, which gives them many points of contact and attractions to each other. So here you can compare the boiling points of straight chain alkanes and branch alkanes and cycloalkanes. All these examples here have 5 carbons in the compound. So everything in this table has a compound that has 5 carbons in it. When it's a single end-to-end form, the straight chain form, it would be called pentane, a boiling point of 36 degrees Celsius. If it starts to branch, 28 degrees Celsius. If it becomes more branched, it becomes even lower, 10 degrees Celsius. And if it's a cyclic alkane, 49 degrees Celsius. So the cyclic version will have a higher boiling point than the straight chain version. Alright, now we'll talk about combustion of alkanes. The carbon-to-carbon single bonds in alkanes are kind of difficult to break, which makes them the least reactive family of the organic compounds. But alkanes will burn readily in oxygen to produce energy and water and carbon dioxide. So here's that generic equation. An alkane gas plus oxygen with heat added to it will give you carbon dioxide as a product, water, and energy. Alright, methane is a common natural gas that's used to cook food and also to heat homes. And the equation for the combustion of methane, CH4, is written here. CH4 gas plus oxygen added together and then heated will give you carbon dioxide and water and energy. And another alkane, propane, commonly found in portable heaters and barbecue cookers. And here's the equation for its combustion. Propane plus oxygen heated will give you carbon dioxide, water, and energy. Alright, now we'll talk about the solubility and the density of alkanes. Alkanes in general will be nonpolar. They'll be insoluble in water. They'll be less dense than water. They'll be flammable in the air. And it's something very commonly found in crude oil. Just like the example we talked about at the beginning of the chapter with the vegetable oil. It will float at the top of the water and form that film on top of the water. It's the same thing when you have an oil spill in the ocean. The oil will, because it's less dense than water, it will float to the top of the water and forming that film on the surface of the ocean. Alright, now we'll move on to alkenes and alkynes. Ethene, or commonly called acetylene, commonly used in welding, because it reacts with oxygen to produce flames with a temperature in the range of over 3,000 degrees Celsius. And the big difference between alkanes and alkenes and alkynes is the number of carbon bonds that are formed. Whenever you have a double bond between carbon and carbon, you have an alkene. If you have a triple bond, like you have here, that'd be an alkyne. Alright, first one we'll talk about, ethene, C2H4, commonly called ethylene, is an important hormone that's found in plants because it helps the ripening of fruits. And like you see in this picture, you have a very large number of bananas. Ethylene will help break down cellulose, which is a complex sugar in plants, which causes flowers to wilt and then the leaves from trees to fall. Alright, naming alkanes and alkenes and alkynes. Now the rules for naming alkenes and alkynes is very, very similar to the process for alkanes, but you are replacing the ending with -ene and -ine instead of A and E. So for example, ethane, these are all single bonds here, but if you have a double bond between the carbons, it's now ethene. If you have a triple bond, ethyne. The same thing with the line formulas. If you have a double bond, you write a second line. If you have a triple bond, you write 3 lines. But all 3 of these represent the same formula. All 3 of these represent the same formula. Then all 3 of these represent the same formula. Right, a guide to naming alkenes and alkynes. For one, you name the longest carbon chain that contains a double or triple bond. The double or triple bond is assumed to be the first bond between carbon 1 and carbon 2. Step number 2, you number the carbon chain starting from the end near the double or triple bond. Then you give, or step number 3, you give the location and name of each substituent in alphabetical order and as a prefix to the alkene or alkyne name. For example, we'll go over naming the cycloalkene. It's a cyclic compound, so it's going to form a circle as an alkene because there's a double bond here. So what you do is you assume that the double bond is between the first and second carbon. So when you're naming this overall compound, you know it's going to be a cyclic compound. So cyclo is going to have to be in the name. It has 5 carbons. It has to be penta because if you see a double bond, it's going to be a pentene. So you know it's going to be cyclopentene. But then you have to factor in how to name this. You always start at the double bond or triple bond, and you want to give this location with the lowest possible number. So this is assuming that's the first carbon, 1, 2, 3. That'd be 3-methyl cyclopentene. If you were to start here and go the other way, 1, 2, 3, 4, 5. 5 is a higher number than 3, so you always want to give the lowest possible numbers when naming substituents for a compound. And now we'll talk about cis and trans isomers. When you have an alkene, the double bond is rigid and does not rotate, and so it holds attached groups in very fixed positions. So this will form 2 geometric isomers called cis and trans. It just depends on where everything is located in relation to that double bond. And when you're naming these compounds, you must include cis or trans as a way to reflect the structure of that compound. So cis and trans isomers will have different physical and different chemical properties because they are arranged differently. Even though you have the same numbers of atoms present, because of their arrangement, they may have different traits to them. These types of isomers cannot occur when 2 groups are on the same one of the carbons. And so comparing these 2 here, these are both 2-butene. This is cis, this is trans. Cis means they're on the same side of the carbon or the double bond. Trans means that they're on the opposite side. These 2 here, same side, and one up here, one down here, opposite sides. In the cis isomer, the alkyl groups are attached to the same side of the double bond, and the hydrogen atoms are on the other side. In a trans isomer, the groups and H or hydrogen atoms are on opposite sides of the double bond. So some more examples here. All of this here is 3-hexene. These groups are on the same side. There'll be a cis 3-hexene. They're on opposite sides, like here and here. That's trans isomer. These all represent exactly the same numbers of hydrogens, the same number of carbons, but how they're arranged will impact how they're written in the structural formula, and also their chemical and physical properties. So if you were just to name this example as just 3-hexene, that'd be wrong. It is cis 3-hexene. If you were to drop off the name trans for this compound, name would be wrong. The proper name for this compound here is trans 3-hexene, not just 3-hexene. Alright, addition reactions. In alkenes and alkynes, the double and triple bonds are going to be very reactive and undergo hydrogenation, the addition of hydrogen bonds, and hydration, addition of hydrogen and hydroxide to carbons in the double or triple bond. They'll undergo polymerization at high temperatures and high pressure, and these also be easily broken in providing electrons to form new bonds. So for examples, hydrogenation, you have an alkene plus hydrogen. We end up getting as an alkane. For hydration, you have an alkene plus water, and we end up getting as a product of an alcohol. And for polymerization, you have an alkene as a reactant, and what you end up with after high pressure and high temperature, you get a polymer. So we'll talk about hydrogenation first. In hydrogenation, you get hydrogen atoms that are added to the carbon atoms of a double bond or a triple bond. And then you have a catalyst such as platinum or nickel that are used to increase the speed of the reaction. So over here, you're starting off with an alkene, then you're adding hydrogen atoms, the catalyst of platinum. You end up getting a product of an alkane. For this one, you're starting with an alkyne, adding hydrogen. Nickel is used as the catalyst. You end up getting a product of an alkane. So these hydrogen atoms will take the place of one of these bonds. So you start off with a double bond here, end up with all singles here. Start off with a triple bond here, you end up with all singles here. We'll talk briefly about Markovnikov's rule. When water adds to a double bond in an asymmetrical alkene, you have two possible products. So this rule states that the hydrogen from the water will attach to the carbon that has the greatest number of hydrogen atoms, and the hydroxide part of the water adds to the more substituted carbon atom. Alright, now we'll talk about polymerization. A polymer is just a large molecule that has many individual segments called monomers. Poly means more than one. So individual units that are repeating would be a monomer. But you get them end to end to end, then you get a lot of those monomers, so it's a polymer. And many of these polymers are produced by addition reactions of alkenes. And probably the best example of a polymer would be plastics. So plastics, things that you'll find in non-stick pads or plastic cups, rain gear, carpeting, and so on. Some common examples here: the polystyrene for styrofoam cup, saran wrap, as a formal name here, and then Teflon. All those are examples of. Alright, in medicine, you'll find synthetic polymers that are used to replace damaged body parts like artificial hips, artificial joints, pacemakers, teeth, heart valves, blood vessels. So all those are or contain different types of polymers. Alright, many of these synthetic polymers are made by the addition reactions of small alkene monomers. So you usually need for this reaction to happen is you need to have a catalyst, you need to have a high temperature, and a high pressure, usually over 1,000 atmospheres. So in each addition reaction, the polymer will grow longer as each monomer is added to the end. So a polymer is just a monomer end after end after end. It's a repeating unit. Now a polymer may contain as many as 1,000 monomers. An example here, polyethylene is a polymer that is made from ethylene monomers and is used such as plastic bottles, film, plastic dinnerware. And it comes in two different forms: low density polyethylene and then high density polyethylene. The low density, or the LDPE, is very flexible, breakable, less dense, and is more branched than the high density form. The high density form is going to be much stronger and a lot more dense than the low density version, and it melts at a higher temperature than LDPE. Alright, this table has several alkene monomers that are used to produce some synthetic polymers. Here are the monomers listed here. That will be written out in the structural formula and some common uses: plastic bottles, shopping bags, plastic pipes, carpets, artificial joints, so on, Teflon, plastic coffee cups. So these are some very common examples of polymers here. Now the alkane-like nature of these plastic synthetic polymers makes them unreactive. So that causes, or that leads to, some problems. Because they are unreactive, they don't decompose all that easily. They're not biodegradable, so they are a pretty large contributor to pollution, both in the oceans and on land. So for all the good that they offer, there's a downside to them also. Now we'll talk about benzene, which is an aromatic compound. Now an aromatic compound has a ring of 6 carbon atoms, each bonded to one hydrogen atom. This will give you a flat ring structure, drawn with 3 alternating double bonds. And benzene will be represented by 2 structures because the electrons are shared equally among all the carbon atoms. Now, benzene is also represented by a line angle structural formula using a circle inside the center instead of the alternating double bonds. You can write benzene either this way or this way because these double bonds are able to kind of shift because the electrons are shared equally. So benzene can be represented like this with the ball and stick model, or like this. but it's commonly written like this. You have the hexagon shape because it is a ring of 6 carbons, and then the circle in the middle to represent these shifting double bonds. Alright, some other common examples of aromatic compounds that we use for flavoring, such as in cooking. Tarragon is one here. Thyme is another one. Anise is another one. These are all examples of aromatic compounds. Alright, some properties of aromatic compounds. The flat symmetrical structure of benzene allows for interactions between these cyclic structures, which contributes to the higher melting points and the higher boiling points of benzene and all of its other derivatives. There's a table with various compounds and then their melting points. Benzene, melting point of 6 degrees Celsius compared to these other versions. Now, aromatic compounds are going to be less dense than water, but usually they are more dense than other hydrocarbons, but they're still less dense than water. Halogenated benzene compounds will be denser than water. Aromatic hydrocarbons are insoluble in water and are used as solvents for other organic compounds. And only aromatic compounds containing a strong polar functional group, such as a hydroxide or the COOH, will be somewhat soluble in water. And benzene and other types of aromatic compounds are resistant to reactions that break up the aromatic system. Although they are flammable, but they tend to keep their shape pretty well. Alright, that brings us to the end of Chapter 12 and the end of this series of videos on a crash course in chemistry. I hope you've enjoyed it. I hope you feel that you've learned something from it. So thank you for watching.